no cameras, no flash drives, no watches, no calculators, no Bluetooth hardware, no earbuds or headphones, or any other
Last year
electronic
it's
device.
7, not
This is
7
your
fast.
last opportunity. If you have something that you shouldn't have right now, you can give it to one of the staff. From this moment on, it will result in disqualification. Again, a reminder, contestants are not allowed to communicate with anyone other than their team members and contest officials. Any communication with any other person can result in disqualification. If you have about the contest problems during the contest, use the PC squared system to send a clarification request to the judges. If you have problems with your workstation, like the keyboard, the mouse, the computer, whatever, or you need other kind of assistance like a pencil, water, something like that, please do not send a clarification request to the judges. Raise your hand and get one of our staff to help you with it. A reminder, your NAC badges must be worn at all times and they must be unobstructed and visible, readable. Once again, the restrooms are outside team restrooms through the doors you just came in and follow the roped off path. Spectators, restrooms are out through the door you came in and down to the right. There are signs directing you. Spectators, it is very important that you do not attempt to use the team reserved restrooms and that you do not attempt to talk to the contestants on their way to the restroom. Doing so could result in those contestants being disqualified. Teams, once the contest starts, you may adjust the location of your keyboard monitor, but you may not unplug anything. You must, however, be aware that if you move the hardware, any changes you make are at your own risk. You also are not allowed to block your webcams. A reminder to teams, you are not allowed to do anything that would affect another team. Doing so is grounds for disqualification. You also may not do any networking operations. Do not attempt to use your computer to contact any other computer anywhere on planet Earth. Teams are allowed to print only small jobs, a few pages at most. For today's contest, there will be a differently colored balloon for every solved problem, and balloons will be delivered all the way up until the freeze point in the contest. As it states in the rules, the scoreboard will be frozen at an appropriate time in order to keep the final results secret. The default scoreboard freeze time is 1 hour prior to the end of the contest. Teams, there were some changes made to your machines overnight based on some issues that were raised yesterday. In particular, these relate to using the address sanitize option in C++ and to the Kotlin configuration in the JetBrains IntelliJ IDEA. The judges have sent a clarification announcement regarding those two things. So once the contest starts, if you are interested in either of those issues, you should check your clarifications immediately. If you don't care about those, then you don't need to worry about those clarifications. Spectators, it is extremely important that you remain quiet during the contest. We welcome you to have all the conversations you want, as long as you're doing it outside the contest floor area. In particular, go over and check out the coach view stations over there. There will be copies of the contest problems available for spectators both here on the contest floor and over in the coach view area once the contest has started. Okay, in a moment we're going to count down to the start of the contest, and when we do so, contestants, you will be able to open your packets. At this time, I'd like to invite the following people to the stage to release the contest balloons and start the contest. The ICPC Executive Director, Bill Poucher. ICPC Foundation Chief Operating Officer, Melinda Gage, Ann Harris. The Dean of the University of Central Florida College of Engineering and Computer Science, Dr. Michael Georgiopoulos. The CECS Dean's Executive Administrative Assistant, Jennifer Sutton.
Yeah, I was definitely
The Southeast Regional Director of the Defense Innovation Unit of the U.S. Department of Defense, Bev Say. And finally, but not least, Dr. Tony Logar, the North America Championship Contest Director. And at this time, well, let's see, we need to do a status check. And this is messed up yesterday, so we'll see if we can do it well. What is our status? Okay, the judges have already indicated they're ready to go. Let's see, security, Sergeant Slavic, are we ready to go? We're ready to go. Security hosts, are we ready? Okay, we're ready there. Let's see, contest director, Logar, are we ready? We are go. Let's see, that leaves just, teams, are you ready? Yeah! Pretty good, but let's try even better. Are you ready? Yeah! All right. Okay, now we have 13 minutes. Do we want to wait that long? No. Okay. There we go. Okay, an ICPC time warp will get us down to 1 minute. Okay, so at this time, I'm going to hand the scissors to Tony, who I think was going to hand them to Michael. Okay, so.
special spot. It's like looking so important.
If you all.
For this.
Right. Okay, in 30 seconds, we'll start the championship contest. All right. Spectators, teams, and everyone else, help us start the contest in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Teams, you may go.
Good morning and welcome to the 2025 North American Championship. We have one heck of a contest here for you today. You can see the University of Chicago are opening their problem sets just like every other team here. Today we have a host of commentators, but we're starting off with Nick and I, and we'll be starting with the contest. Although our timer says 11 minutes till contest start, we're working on getting that fixed now. Looks like we just got our problem set, so we'll take a look as teams start solving. Nick, welcome.
Welcome to the show. It is great to be here once again in Orlando, Florida. We are all on site at the University of Central Florida. UCF, gracious as always, hosting. We have the top 52 teams here in North America, and they're all competing for world final slots for a trip to Baku in August.
Why don't you come in a little more
so people
can see you.
Okay, sorry.
Great. All right, no, you're good.
Okay.
We got University of Chicago here. This is their first time at NAC for each of these three individuals. They also are big fans of playing a particular type of Brazilian drum. Starting off the fun facts early.
Yes, fun facts.
I thought we'd get off to a nice start.
Yeah, we got started with fun facts. There for returning viewers, we survey all of the teams and we have them submit. Their fun facts, just anything cool about themselves, and we'll see how it goes.
All right,
they've submitted all sorts of stuff. So stay tuned, and you'll hear some fun facts about the team that you're rooting for, or teams in that case.
We have folks feverishly working on the ticker. Lydia, we're going? All right. We'll come back to that in a sec. In the meantime, let's take a look at UChicago's screen here. They're reading your problem. Nick, looks like that might be early in the set. Are these stapled or not?
So the problem. Okay. So for those who aren't familiar with how these programming contests work, so this contest is going to run for 5 hours. These teams have been given 13 problems to work on. And so each problem will have some flavor text. There'll be a little bit of a story, and the teams will be asked to write a program to solve some problem. There are lots of different themes, ranging from stuff like I think like placing like solar panels on like a farm to playing like a game of entrapment. There are all sorts of scenarios. So.
Humans versus AI is one of them.
I heard human versus AI is one of them. The very front of the problem set has a lot of math notation on there. It's
scary. Yeah.
It looks pretty intimidating, but there are 13 problems. The judges have given their predictions for what they think the easiest problems are. They may not be the first ones to get solved, but the judges were just talking to me right before the broadcast, and once we see some submissions, we'll actually talk a little bit. We can start talking a little bit about the problems.
So we'll watch carefully on the floor here. You can see we have a series of balloons attached to the trophy. One of those is this big, beautiful golden aluminum balloon, and that is the first solve balloon. It might be written on the other side of the balloon. I'm not sure if you can read it, but on the other side of the spinning gold star is the first solve text, and that gets delivered to the team who gets what we call the dark green, which is the first correct submission in the whole contest. There's usually a whole procession too, as the coaches and administrators walk that one over to whichever team solves
and the
it.
contestants, they're asked to touch the trophy for good luck. They used to make a joke every year that they're collecting everyone's DNA for in the future when they need it. So they've collected a lot of DNA in the last who knows how many years.
In the age of AI, that may be sooner than we think. Looks like we've got the timer all set, so you can see we're a couple minutes into the contest here, almost 5 minutes in. And we don't have any submissions that we can see quite yet, but we anticipate that will be coming up pretty soon.
Yeah, so every NAC is a little bit different, and I think this year the judges have told me that the difficulty curve is a little bit different from in previous years. So the easiest problem in this case, like the problem that the judges think is easiest, requires not a lot of code. And they were even generous enough to provide some strong sample cases. So in the problem statement, when they explain like what the problem is, the contestants get sample cases, and so those are like small instances of the problem that they can test their code on to make sure that that their problem, as a sanity check, that they've actually interpreted the problem correctly, and their program like could be a reasonable attempt. And actually, the judges told me that all the judge solutions were incorrect on a specific test case that got constructed. And this is such a tricky edge case for an easy problem. So they stuck that test case in the samples. So they were saying, oh, we don't expect there to be any other edge cases, but you never know.
Well, let's talk a little bit about scoring for the moment. The way the teams here are ranked is first by the number of problems they get correct. So every team's goal here is to solve as many problems as they can. But in addition to that, if two teams solve the same number of problems, they're tied by what we call penalty here, which is the total time it takes them to solve all of those problems, with an additional penalty imposed for getting a question wrong that they later get correct. So if you solve, let's say, 2 problems both at 1 hour in, your total penalty is 2 hours, even though your second problem took you basically 0 minutes. But if you solve one problem at 0 minutes and your other problem at 1 hour, your total penalty is 1 hour. And then you'll be placed ahead of the other team. So it's in each team's best interest to solve the problems they think they can solve fastest first. And that's why traditionally you'll have teams scramble to try and find the easiest one in the set. And we're now almost 7 minutes in with the first solved balloon yet to be claimed.
Yeah. So with 13 problems, it does take a little bit of time to read through the problems and to maybe get a sense for, which problems are easy and which problems are hard. The way that the problems are ordered, they're ordered alphabetically. So in other contests, they might say something like, oh, problem A, we guarantee that problem A is like the easiest problem, or it might be like in the easy half of the problem set or something to that sort. At the NAC, the judges don't give any kindness to the teams. They just say the problems are in alphabetic order by title, and there's no other information. And so part of the difficulty is finding the easiest problem in the set. And
we have our first submit, the dark red from UCLA on problem K. Can we take a look at their screen when we get a chance?
So problem K,
It's like it's an instant wrong answer. Didn't even get through many test cases.
so problem K is called SLA tomography. Maybe
SLA
that's
tomography. You can see their screen here. They're coding in C++ as expected in a very short solution.
Oh, another submission coming in. And there's the dark
There's
green.
the dark green. Also on K by The Ohio State University. Folks may not know, but The Ohio State University is a self-organized and self-funded team. They had to pay for their own flight tickets here. They're a little disappointed by that, but
Yeah, and
they're doing great for this dark green.
Yeah, and we need to emphasize it is not Ohio State University. It is the Ohio State University.
The one and only.
Usually when there's the first solve, I expected there to be a lot of applause, but
They'll be getting their balloon delivered soon here. Maybe we can turn up the overlay volume
a little bit. It sounded like there wasn't a super big reaction for the dark green, but congrats to the Ohio State University. Maybe it's a slow start. Maybe these teams didn't have their espresso macchiatos.
Lydia, if we have a chance, is there any way we could get a link to the problems? Are these online? In the description of the YouTube stream. Let's take a look. Anyway, do you want to start with reading problem K here, Nick?
Sure. We can go ahead and I will read the problem. The problem statement's a little long. But so the general idea here is the problem talks about stereolithography, which is a printing technique for...
Check back soon. We don't have online statements.
We don't have the online statements yet?
We'll get them soon, hopefully.
Okay. This statement's going to be... it's a bit of a doozy to read out loud. But so... The flavor text is about stereolithography, or SLA.
I actually have a printer that does exactly this. It takes this very poisonous chemical and turns it into a beautiful piece of plastic.
Yeah, so what happens is, so in the problem you have like this, you take sort of like this two-dimensional like cross-section, and so you have this, you have a 2D grid, and so there are like some columns. The columns start out like from the bottom, and like you block out like some height from the bottom to the top. There might not be anything in a specific column, but like if there is like like if the object is occupying like some grid square in a column, the grid square below it will also be occupied. And so this will form, you can imagine a kind of there being like pillars in the grid a little bit. Maybe you think of it like Tetris. So like the blocks, the columns will always like fall down to the bottom. And so now what will happen is you pour liquid resin into the structure. And so you'll pour in the resin, and then excess resin will drain like off of the sides in sort of, this is actually like a kind of like a standard leak code problem, like trapping rain, like, or something like that, where it's like the columns might like form like little valleys, and then like
so
the resin
you have
contains,
a histogram,
yeah,
and then you fill up the things where water wouldn't be able to flow out
Yeah.
over the sides.
And so what happens then is, so the liquid all flows out and then it hardens. But you can now see like what was originally like liquid and then what isn't. So that's all of the framing for the problem. We haven't actually described the actual. So here's the framing for the problem. So someone has simulated this process, and then they look at each row in the grid, and they see how many squares in that row have resin in them. So they claim that this is the case. And your job is to basically reconstruct this. So your goal is to construct a grid where you can come up with these resin amounts in the rows. So part one is figure out, is it possible?
Should we draw
or
an
not?
example?
We
Would that
probably
be
should
more
draw an
helpful?
example. I feel like I'm waving my hands and no one has any idea what I'm doing.
Yeah, let's do that. Okay, so this was from the practice set, but we can draw something out here. So let's say we have,
Do you want to use the example they have here, or is that too much?
this one here.
Okay, let's do
We'll
this
do a
one.
simplified version. So the requirement is it is a histogram, right?
Yeah, it must be a histogram.
So here we have 2 spaces in this row, 0 in this row, and then 3 in this row. And the leftover resin would fill these the blue X's,
Yes.
there and there. And this is the least wide, in this sense of wide. This is the least wide shape that fills this
203.
203 requirement.
Yes.
So the question is, given this requirement here of like 203 or some other set of numbers, what is the width of the shape that you would need in order to print something that has that much resin left over at each row?
Correct.
And it sounds like any increase in the numbers, so in this case, this 0 to 3 increase, and you can also imagine there's a 0 here, so 0 to 2. Any increase introduces a constraint of that increase plus 1 if everything else is filled, right?
Yeah,
Is that
so
a fair assumption?
yeah, so basically what happens is, so you can assume like for convenience that like you've padded like a 0 like at the top, so the top is like completely empty. So when you carve out like k units, some like you can show that it's optimal to have all k units of resin being adjacent in a row, as opposed to having like, you know, like one and then like another one that's like separated and then like other ones. So like that is like strictly worse than having all k units of resin be like contiguous. So that is like observation the first. And so when the value drops, you can just sort of dig out part of like the row below it, and you don't have to make it longer.
Yeah, so for example, if we had something like this, then we wouldn't have to introduce any new width. We can just carve out this to get this one.
Correct. But then if you have to make it bigger, you cannot make it bigger by carving out more space. You have to just sort of construct a new segment.
Like this. Exactly. Yeah. So you get this, if this went from like 2 to 1 to 4, for example, then you get this one here for free, kind of, because you get it from the previous row. But you have to introduce 3 more. To do that, it costs 3 plus 1. And then you have to pay for this first column, too, right? We got UCF, our host university, with an AC on problem B. That's a dark green. Let's maybe take a look at them if we get a chance. UCF, they tried to, when submitting fun facts, tried to do SQL injection. Of course, it failed because we used Google Forms, and Google is not weak to SQL injection. But you can see they got a dark green here. It appears they're still testing it. Oh, maybe there is problem I or L. Looks like either capital I or lowercase L.tpp.
I'm seeing UCF submission on B is still pending according to the public board.
According to the scoreboard, it's a dark green. And Colorado School of Mines has an AC on problem K, not a dark green, another AC on problem K. Colorado School of Mines, they have a close relationship with Rutgers, I believe. Let me double check that.
Yes.
Yeah, Kelly Dance, who is on this year's Colorado School of Mines team, was last year's Rutgers coach.
Yes, I actually got to hang out with them in Astana. So we were all in Astana together. I know that the Rutgers team was looking for a coach because I think their assigned coach was unable to travel all the way out to Astana. So Kelly served as their coach, and I believe in the Rutgers competitive programming server, his nickname is just Coach Dance.
There you go. You can see in the UCF screen here, we've got just to the left of the person coding is Anderson Fenderson. He's a legend at UCF. He's been here for a while, but he's only 19 years old. He was very young when he first started college, and he's crushing it. This is his third NAC, I believe. Hoping to qualify for World Finals here.
So I will say from the judges' side, so the judges almost universally agree that problem K is the easiest problem in the set.
And so do the teams with ASU with an AC on it and Maryland also. But go ahead, Nick.
But there is some contention around what the second easiest problem is. There are two candidates, neither of which are problem B, and I don't think any team has submitted to either of those problems. So we're gonna hold you in suspense for a little bit.
Johns Hopkins has just gotten an AC after problem K after one incorrect attempt. That gives them a total penalty of 34 minutes because that one incorrect attempt cost them 20 penalty points. They also have one of their team members who's qualified for the NCAA fencing championships every year that they've qualified for World Finals, or not World Finals, for NAC.
Are we sure we're not at the fencing championship?
I don't know. If people bring out swords, you might have to start questioning yourself.
Yeah, so just as David explained, so when you make the incorrect submission, you get charged the 20 extra penalty minutes, but that only happens if you actually solve the problem. So if a team, for example, right now, I believe Georgia Tech has one submission on problem M, and that submission is incorrect, but they don't have 20 penalty minutes charged to them because they haven't solved the problem. If they do eventually solve the problem, then they will get charged those penalty minutes. But this basically encourages teams to actually try to solve the problems. Some ICPC history for those of you who have only seen ICPC in the modern era. Back in the old days, if you submitted incorrectly, you always got 20 penalty minutes, and so there was this interesting circumstance where the team that was in first place, they wouldn't submit because if the submission was wrong, they would get 20 minutes and they would actually go down on the scoreboard.
Stanford University is now on the board with another AC to problem K. They are huge chess fans. They say they've spent more time playing chess this week than doing computer programming contests. They even brought a chessboard with both roughly silver and gold colored pieces.
They're super big on chess. So I'm a Stanford alum myself, and so I went to one of their club meetings and they were like, oh, we're going to talk about ICPC stuff. But I showed up and they were just playing Blitz. And I was like, and when I say Blitz, I don't mean Code Forces Blitz. I mean Blitz chess. I have to make that distinction because Blitz actually now means something a little bit different to those of us in the community. On Saturday, it was maybe Saturday or Friday, Jane Street ran an activity night. And one of the activities was this giant chessboard. Jane Street is our titanium sponsor, I believe. So they're a big part of the reason why this event is even allowed to happen. Their sponsors were on site, gave some cool talks. The activity night was super fun. I think everyone that I talked to was a big fan. They brought DDR in and
Dance Revolution.
And as everyone seems to know, DDR is a bit of a vice for me, so I was asked to play on the machine.
We've got two quick announcements. First, we have a dark green on problem A from BYU. And second, Columbia is on the board here with an AC on K, I believe. We'll be talking to Columbia's coach in a bit. And they are, according to themselves, the least washed team objectively, where washedness is determined by delta from max Code Forces rating of all time to current Code Forces rating. So,
Yeah.
And the most washed team, in case you're wondering, is MIT, who, they have a series of, I believe, international grandmasters, if I recall correctly.
Yeah, there is definitely teams definitely will look at like Code Forces rating to try to get a sense for like how they rank against the other universities. But Code Forces rating definitely is a little bit different from Code Forces contests are definitely different from ICPC contests. So, just because you are like a legendary grandmaster like 3000 plus on Code Forces, that doesn't make you like a legendary grandmaster equivalent in ICPC. For example, I believe at the NAC we have exactly one legendary grandmaster, and I believe that's from
CMU?
I guess there are two then. So there is one from CMU, Carnegie Mellon University, and then there was also one from the University of Illinois Urbana-Champaign. And I think neither of those teams is on the board quite yet, if I'm understanding correctly.
We can certainly take a look to fact check that.
I did post a blog with some of the content. Not all the teams filled out the thing. This has been a long while running, but yeah. So I think CMU has one, and then UIUC has one. Although I heard UCLA may have.
Yes, CMU has one. They also have Fizzy David, who I believe at one point was.
So
and then
former
who's-
LGN.
Oh, yeah, and then UIUC. Yep, exactly.
UCF?
UCF, oh my goodness, into first place with an AC on K. That puts them in a very good spot. Can we take a look at them? UCF, host university. What's up here? What am I looking at? Problem A? Oh yeah, problem A is very scary.
Yeah, but BYU was first to solve problem A.
BYU for solve A. Yeah. Very impressive. All right, UCF though. So it looks like they've got K. They have, what was it, I? B. They have K and B, and they also have something in progress for I. Looks like a 3-dimensional grid, potentially, or something with rows, columns, and height. And it's even being tested, so they are, it looks like, pretty close to 3 ACs.
I will remark that so problem A is deferred to be solved, and problem A was also not a candidate for second easiest problem. So we'll see when the second easiest problem gets solved.
Yeah, I mean, just looking at this thing, if I opened up my packet to this, I would just quickly flip to the next page. This is such a scary sheet.
Also, you don't like number theory, if I recall
I don't like
correctly.
number theory. I don't like Greek letters. I think all of this is perfectly explainable in half a paragraph of text. But I don't know what p sub I to the power of v sub p sub I of k minus 1 means. So this is beyond me, I'll tell you that much.
Yeah. Well, I will say for those who are curious, problem A is called a totient quotient.
The Toshan quotient, yes. We have, is this Richard?
That is not That is not
from
Richard,
MIT?
or
Oh, but he's
the
on
one
the
that
team.
the one who's coding is not Richard, but Richard Chi, I believe, is adjacent. If I had to
That's
guess,
Ben Q's brother, right?
that is Ben's brother.
Ben, very famous in the USACO land.
Yeah. So we were running the North America programming camp, and simultaneously I was also helping out with the USACO training camp, which is running right now to decide the US IOI team. So a lot of contests happening right now.
MIT, they've placed second. This team of 3 people has placed second 3 years in a row in their qualifiers to other teams at MIT. Slime was one of them who ended up beating them. This is their first year representing their school and region at North American Championships, and they hope to do well here. Also, I have a fun fact about Richard, if you'd like to hear it.
Let's go for it.
Richard, personally, I also run Meta Hacker Cup, and Richard has been flagged almost every year for copying Ben's code in Hacker Cup because they use the same hack pack. They use the same book code. So since they have the same massive thing, it flags them as very similar.
Yeah,
They're brothers.
I am somehow unsurprised to hear that. But we can confirm that they are different people,
Indeed.
and you know, Benjamin is most definitely at Yusuko camp right now, and Richard is most definitely here. I see we have Harvard on screen. Harvard frequently competing against MIT at their regional contest.
We were talking to Harvard's coach last year. They said this Harvard is quite a good team. She was pretty confident in their abilities. Looks like they're messing around with VS Code a little bit and trying to solve problem F. We also have a time limit exceeded verdict from Georgia Tech on problem M. Nick, what is the time limit exceeded verdict?
When contestants submit their code, the way that the code gets evaluated is a series of test cases are executed one by one. So if you pass the current test case, then you'll move on to the next test case. And so there are a lot of different failure modes that can happen. So a common one is WA. So WA stands for wrong answer, or if you look at some laptop stickers around here, you might see wonderful answer. And it just means that the program printed an answer that was considered to be incorrect. So TLE stands for time limit exceeded, or if you look at some stickers out there, time limit enough, which is also a pertinent joke. So each program is given a fixed amount of time to run on the test case. And the amount of time that is given depends on the problem. So for example, for problem A, the time limit is 1 second. For problem B, the time limit is 3 seconds. And the time limit can vary per problem based on all sorts of factors. If the program exceeds the allotted time that is allocated for the test case, then the program will be terminated, and then the judge will report back that the program did not actually run in time, and then yield this time limit exceeded verdict.
We have Georgia Tech on the board with an AC on K. Their honorary coach, Jinbang, has spent more time at Universal this week than with them.
Yeah, so Jingbang is he's not the actual coach for Georgia Tech, but I think he's very close with the actual students. And Jingbang is also one of the co-founders of Universal Cup, which is a big contest series for active and retired teams. And so obviously, you know, the co-founder of Universal Cup has to spend all his time at Universal Studios.
Exactly. We also have, in another stream going on concurrently right now, USA 1, which is Tourist, Eknerwala, and Kaysun. Gennady, Andrew, and Kevin are solving this set concurrently when they get access to the problems. I don't know if they've been released publicly yet, but they're trying to stream that and compete for points in Universal Cup. Also, if we could take a look at University of California, Berkeley, they just got a dark green on problem L. In fact, all of the members of their team met each other at the gym before learning they were competitive programmers.
I could believe that.
You can see they're pretty swole here. I
could believe that. They are definitely they're definitely jacked. I would not want to. I've hung out with them quite a bit. I think this team is like recurring.
Oh, this is L. They just L.
Another cute fun fact is they have a great sense of humor. Their team name is Bill Poucher.
Bill Poucher, classic, of course.
Yeah,
does
when
all the ICPC announcements with a gigantic hack.
Exactly. At the Pacific Northwest Regionals, we announced that Bill Poucher won, and Bill Poucher was so proud that he showed up in person. And so in their team photo, you see the three of them, and then Bill Poucher's in the background. So you know, Bill's huge fans of them.
We also have a first solve on problem D from Texas A&M, Team Hyper. I think we haven't looked at problem D either. We're getting a bit behind on problems. Maybe we'll take a look at B next. What do you say?
This is shaping up to be very interesting. I think this was what the judges expected. They are under the belief that a lot of problems are at fairly similar difficulties. And so there being a lot of like distinct first to solves very quickly kind of lines up with that. Unfortunately, in about an hour, we're going to talk about something called the 90-minute heuristic, and that might just go completely out the window this contest.
Because of all the different number of first solves?
Yeah, so in an hour, if you stay tuned, I'll talk about this so-called 90-minute heuristic, and it's for identifying what needs to be done in order to qualify for the World Finals.
So I see some questions in the chat about the tourist team stream. On Codeforces, there should be a link to that. I don't know if they've gotten problems yet, though, so we might not see that.
I can see on my side, it looks like the open contest started roughly at 10, so they probably have problems. We are not actively monitoring for their stream, but
we've got the problems.
They've posted the link to Codeforces, so if you go to Codeforces, you will surely be able to find their stream and be able to tune in. If you want to see teams executing at the highest level, by all means, you should definitely watch the three of them.
Let's take a look at problem B here. This one was solved by UCF, I believe, and it's a tree problem. So your friend has given you a rooted tree, which is a connected graph with n nodes and n-1 edges. One of those nodes is a root. The nodes of the tree are numbered from 1 to n. Yeah, and node 1 is the root. And all of the other nodes are numbered arbitrarily. You've recently learned about Ouroboros, an ancient mythical snake that eats its own tail, and signifying a cycle with a beginning and an end. You dislike the fact that the tree you were given has a very clear beginning of its root and clear ends at its leaves. So you decide to completely change the structure of the tree into a new graph, which you have named the snake graph. To construct the snake graph, you take the leaves of the tree and draw a special leaf edge that connects every leaf directly to the root. If there is already an edge connecting the leaf to the root, you still add this duplicate edge. With this special graph structure, you can now create a lot of different trees by removing some subsets of edges in the spirit of this person. And the leaves and the roots can change depending on which subset of edges you remove. How many different trees can you make by removing a subset of edges from this graph? 2 trees are considered different if one tree has an edge that the other tree does not. If both a regular and a leaf edge connect the same pair of nodes, then they are distinguishable from each other and are considered different edges.
I think it would help to go to the next page. There is a good diagram. I think that makes it a little bit more clear what's going on. I definitely had a little bit of confusion, reading this and understanding the statement. I was like, oh, it goes up, it goes down and around, what's going on?
So to simplify, you have a tree. So let's draw our nodes here. Okay, here's a boring tree. How do you like that, Nick? Good?
Looks good to me.
And then we'll have some arrows that are red that will connect each root back to the leaf, or each leaf back to the root. And now we want to know, erasing some edges here, how many different trees can we get, right?
Yeah.
That's the question. So anytime you have the root connected to the leaf, like in this case here, there are 2 ways of doing this. And this is independent from everything else, right?
Yes.
Same thing for this. There are two ways of doing this.
Mm-hmm.
And the tricky part comes when you have these kind of big chains. So if you have just one chain and it's just one leaf, then in this case there would be 4 ways of doing it, because you can remove the red or any of these 3. But then you lose your independence when you have this other thing coming out partway through.
Yeah.
How can we handle that?
So I think it probably helps to look at this from like the bottom up.
Okay.
So think about like walking this like bottom up and thinking about like how many edges are you taking like up with you as you go.
So I guess at this node, we have 2 different edges that go up, but we can't take both of the. Could we take both? We could. We could erase this and this, right?
Yeah. So you can definitely take. So you can't take both. So you can take both of them, and as long as you like somehow handle other stuff,
Yeah.
you can take one of them and that would also like be okay.
But you can't take 0.
You can't take 0 because then you've disconnected that portion,
And then
like
this
like
node's
locally here.
Yeah.
So you have to, you basically have to kind of negotiate these like transitions, and then it becomes like this sort of tree DP.
Yeah, so then you can do a DP where the state you have for a particular node is like either you're connected down through the bottom. So like if we kept this node or this edge and this node here would be connected through the bottom, which means you have to cut it. Like you don't have a choice, or you have to cut somewhere between it and the root. So either you cut this here, or you go up and you cut one of its parents from the root. Or you could be connected down, but not all the way back up to the root. And that would be if you ended up cutting this red node. I guess that's it. So it's one of those two states. You do a tree DP for it. And then you do this under mod? You do.
Yeah, but
998,
mod is
not
is
very
pretty,
complicated. Yeah.
is pretty standard. So it's not bad at all. Let's do a quick scoreboard update. I think you'll be glad to see where UCF is.
It looks like from the ticker on the bottom, UCF is in first place.
Yeah, they solved A.
With another AC on A. So they have A, B, and K. They're still on either I or L, too. They have some code ready to go. So I wonder if they're getting caught there. It looks like UIUC has an AC on L. And UC Berkeley has the dark green on it, it appears.
Berkeley has a dark green on which one? L, you said? Yeah, it looks like they have the
Yeah,
dark
I
green
think
on
so.
L. So yeah, A, B, D, K, and L. You know, I like this board because I feel like these teams are like they're not like depending on the scoreboard. We talked a little bit about the scoreboard effect at the programming camp and how like you shouldn't just sort of blindly follow the board. So I feel like these teams are channeling this they're like asking the question like, why should we let other people decide when we could be having the time of our lives? Like, they're the ones who they're choosing their own path and they're focusing on the problems they want to solve, and they're not letting the scoreboard tell them like what they should be doing.
Looks like UC Berkeley has an attempt for K, but it's maybe a little bit weird if the answer is 0. They're printing 0.
The answer cannot be 0. There is no, so in problem K, there is a condition that says that is equivalent to the answer will always be non-zero.
Will the amount of resin?
The amount of resin
be
is always non-zero, which
Okay, so
implies
it doesn't
that
matter.
Yeah. The 0 case is not interesting, and depending on your philosophical bent, you could make that a valid test case or not. The judges were kind and said, we're just not going to have that test case be there, so you don't have to reason about it, because maybe there's it could be ambiguous. Like, you can make an argument that maybe the whip should be 1 because the figure needs to exist, or maybe you say it's 0 and you have a 0 whip thing, but
I don't immediately see what's wrong with their code, though. It looks like they're getting wrong answer. I don't see why. Do you?
I cannot read the screen. It's fine.
Too tiny?
It's a little bit too tiny. I could walk over to, we have an analytics machine over there, and I could like take a peek there.
Maybe we'll get a summary of that at like 11:30. What do you say?
I think they'll figure it out. I don't want to spend too much time like trying to pour over code. Like, we got a lot of folks here who don't code, and it's going to be really hard to follow, I think.
Well, real quick, we have a wrong answer from ASU on problem B. They gave a problem to us in the fun fact. Do you want to hear it? It's a quite.
I know what the problem is, but you can read it out loud.
Okay, I'll let you know.
stream.
I was thinking about this for a solid couple minutes yesterday, and I finally got the answer. At first, they told me, I'm like, no way, that's possible. But let me tell you what the problem is. Maybe it's obvious to you. So you're given 2 envelopes. Each envelope has a number inside the envelope, and the number can be anything. It can be a decimal. It can be positive, negative, whatever. You can look in one of the envelope. You get to pick which one you look at, and you can look inside and see which number's in it. And your goal is to pick the envelope with the bigger number. But if you look in one envelope, you can't look in the other. So you have to come up with a strategy where you pick the envelope with the bigger number over half the time without ever looking in the other envelope. And we'll let you think about how to handle it. I was able to come to the conclusion there is a reasonable answer that's not cheese. But it's
Maybe
it's a
it
fun
is. I think some people would argue that it is. I'm trying to think of a reasonable hint to give regarding like how to actually give people like some forward progress, but I feel like any hint that I give will just give away the solution. So
I think I have a reasonable hint.
what is your reasonable hint?
People who have fundamental knowledge about how machine learning algorithms work will perform better at solving this problem. That's my hint.
Maybe that's not the solution I have, because I feel like the solution that I have is based a little bit in like so my very first instinct when reading this was to think about something known as timeless decision theory, and then I realized that wasn't actually relevant whatsoever. But then I realized that like okay, maybe the hint that I would give is like think about like a deterministic strategy and think about what goes well with the deterministic strategy and what goes poorly.
We have UCLA here with an AC on A, their second problem, putting them just at a medal range in 7th place. This is Andy's 4th NAC.
Yeah, he's been an NAC mainstay, I think, for a bit.
And Texas A&M with its submission on H. Oh, it's wrong though.
Yeah, but Johns Hopkins is first to solve H, I believe.
Yeah. Congratulations.
So yeah, we have
that.
six unique problems solved, and we're 42 minutes into the contest. This is it's a pretty wild start, and we're gonna see, how do things continue as we go on.
Johns
into the
Hopkins,
contest.
one of their team is abstract syntax tree. We talked about their fencing competitor earlier, who's qualified for NCAA twice. They also have another competitor who is ranked was ranked in the top 30 for table tennis in the U17 division in the United States. So quite a jack of all trades, that team.
I think we find that a lot of competitive programmers have a lot of other interests that they also excel in. So
And CMU, real quick, they're going for a 4th submission on L, also wrong. Unfortunate. Can't seem to get it.
It's okay. They'll hopefully get it soon. But yeah,
It's gonna be quite the penalty point though.
a lot of competitive programmers have like these like certain interests, and they also tend to excel in them. So it's very fun to see all of the like diverse sets of interests that people follow up, or that people are like engaged in, and it's just really cool to see that these people aren't just like some people will assume like, oh, like they spend like 12 hours a day like writing code or something. Like that's not the case. Like they're out there, they're doing all sorts of stuff.
Waterloo is now on the board with an AC to problem K. They have 2 fun facts. One is their coach is printed as part of their 25-page team reference document. They had some extra space. So they put a smiling picture of their coach to encourage them. The other is they really don't like cactus graphs. So they're hoping there are no cacti problems today.
I think I glanced at the problem set, and I believe that there isn't a cactus problem, but I also did not look super carefully. So, but also like I think cactus problems are very, very hard for North America. So it would be one of those problems that doesn't really affect World Finals qualification. Would be my bet.
Yeah, that's true.
Yeah, looking at the scoreboard, it looks like we have 39 teams that have successfully solved one problem. Maybe we can talk a little bit about the definition of like a perfect contest now.
Yeah. Well, let's have you.
All right.
Definition, Nick.
I will give the often stated definition. It's ironic because I personally do not subscribe to it. But
I do.
I know you do, so that's why I wanted you to say it. But so for the longest time, people had 3 criteria for a perfect contest. So firstly, number 1 is that every team solves a problem.
I'll be right back.
That was the original motivation for starting this like mini thread about what a perfect contest entails, because if every team has to solve a problem, then we want to be tracking how many teams have actually solved.
Can I have a pencil?
Oh, you want the pencil? Sorry. And so we're actually like pretty close to that in the first hour. So we have 40 teams now that have solved 41 teams that have solved the problem. So only 11 teams.
Almost 1 team a minute.
Yeah. So 11 teams still left to get on the board. But
by the end of the contest, 300 teams will have solved a problem.
yeah, exactly. But these contests are not, they're not sprints. Maybe they're not marathons. Marathon also means something a little different in the programming contest community. The second criterion is that every problem gets solved. It sucks when, the judges go through all this effort to, put together like this problem set, and then they've like put in so much like literal like blood, sweat, and tears into the problems, and then no one solves the problem. Because, maybe you could have just removed the problem set, or that problem from the set, and like maybe the results would be different. Like teams wouldn't have been distracted by it, but like they have more time to solve like problems that they actually could solve. And then the third criterion is, so every team solves a problem, every problem gets solved, but no team solves every problem. And so when a team solves every problem, we call that an all kill, or AK. And so if you ever hear people talking about like, oh, they AK'd the contest or whatever, that just means that they solved every single problem. We have not had that ever happen at the NAC, but we have not yet had a, quote, perfect NAC ever. Like every NAC so far has had, I think, like 1 or 2 unsolved problems at least. So we'll see what happens. Some of the judges were telling me they think that the problem set is overall a little bit easier, so maybe they'll get the perfect contest, but we'll find out.
Lydia, can we take a look at New York University's screen? New York University, one of their team members has solved all but roughly 100, all of them, of the LeetCode non-premium problems. They're like over 3,000 LeetCode non-premium problems. So he's about 100 problems away. Unfortunately, it looks like they're still trying to get on the board here. They've been unsuccessful at K and L. So a tricky start for them.
Yeah, LeetCode problems. So for those who don't know, LeetCode is a website that primarily caters to interviews, especially for tech companies. And so some of the questions will have some amount of overlap, so they'll assess some sort of algorithmic or data structures knowledge. But they're not, like, some people might say like, oh, that will just be like a subset of ICPC, but that's not quite true. I feel that a lot of technical questions have these some like somewhat synthetic setups, like you have to implement like a linked list, or you have to invert or reverse a binary tree or something, and those are questions that wouldn't really appear in ICPC.
In addition to the synthetic part, though, it's a different league. It's a much lower league. What we're doing here is harder than solving interview problems.
Yeah, a lot of the problems here, like you couldn't ask them in an interview because, like I would never ask like one of these ICPC questions in an interview because I would not get good signal. The signal I might get is, oh, this person is a competitive programmer, but I wouldn't get like good signal on like how do they problem solve and so on, because sort of the knowledge that is being assessed here in these programming contests is it can be considered a little bit esoteric, and it can be like it's very hard to solve these problems quickly on demand. Like these teams are, as they've been saying, they call them the best of the best, and then at the World Finals they call them the best of the best of the best.
We've been putting it off for a while, Nick, but do you want to try and read problem A?
Oh boy.
What do you think?
I kind of
leave that for the contestants.
I kind of want to do problem L. Problem L has not as many solves, but problem L is considered like possibly the second easiest problem, and I think it's a lot easier to explain to the viewers.
Okay, let's do it. Solar farm. We're gonna bring it up real quick for you guys.
Yeah, there were also some diagrams there, and I think diagrams are generally easier to parse than math notation. If you don't know the math notation, it kind of literally is Greek, but it does look like, some might say it looks like ancient Greek, but problem A does have a lot of sort of formal like math notation, and that's just to make it sort of self-contained and not rely on like any specific knowledge.
All right, solar farm. You're building a new solar farm. The area which you're allowed to build is a circular field of radius r, and solar panels take up a rectangular space of size w by h. You must place all the panels in the same orientation of your choice in a single rectangular array, so that all panels combined, so that all of the panels combined exactly form a single rectangle. Okay. What's the maximum number of panels you can fit in this farm? So it sounds like, but things are big. Okay. So the radius is quite big. The width and height of each solar panel can also be big, but I think the biggest concern is when they're small, because then you have a lot of potential widths that you could place. Although, I guess you only are interested in square root, because one of the sides is going to have not that many.
That's pretty much it. So the optimal size is it's not the right. I think it's not easily derivable in O of 1, or it just might not be known. But you can show that the optimal size has to be within some range, so you can kind of just brute force it, and it ends up working out. The judges feel. There's a little bit of I say controversy, that's not quite the right word, but there is some disagreement about whether this problem is easy or not, and I think that this is a good time to talk about like the scoreboard effect. Actually, maybe while you're up here drawing a rectangle, I'll talk a little bit about this so-called scoreboard effect. So the scoreboard that we've been bringing up intermittently is also accessible to the contestants. So the contestants can see like their rank, they can see which problems they have solved, they can see which problems other teams have solved. And so the scoreboard effect kind of has like two different components. So when a team solves a problem, it shows up as like the green box that you see. And so other teams can see this, and so they can see like, oh, look at that. Like, you know, if we look at the scoreboard like right now, like it's 39 teams have solved problem K. So almost guaranteed the teams that haven't solved problem K, actually most of them have incorrect attempts on it. I see only 3 teams that have not yet submitted to K. So like certainly K is on all of these teams' radars. And so I would expect that, you know, within the next like hour or so, like every team will either have solved it or will have like some incorrect submissions to it, and we'll be working through it.
Let's go to the circle thing.
Yeah, let's go to
Does that work?
circles.
All right.
Yeah.
So here's my idea. So we're gonna have this basically grid of solar panels, and they're required in the problem to be a certain number in a row and a certain number like per column, basically. So you have something that looks like this. Now, one thing is like, yes, okay, there can be a lot of solar panels here. Oh wait, can both the width and the height be big?
So everything can be big.
Everything can be big.
Everything can be big or small or whatever.
Never mind. Square root doesn't work then. So it's going to be close to square root, and that's the answer.
No. So you like you can sort of pick like the arrangement, or so like if I tell you like how many panels are in a row, you can now compute the height.
And do you ternary search that, or?
You don't ternary search it. It's not necessarily bitonic. It's not necessarily bitonic. However, like if you think about the extremes, like the extremes are likely to be quite bad. Like if you can do like,
if you have like a circle,
if you can,
it's like all like this,
that's
not gonna, you're not using very much space in the circle.
And also if you're using like all of them in a column, that's also pretty bad.
So if we had a graph of like this on the x-axis, this is width, I guess.
Yeah.
Like how many there are stacked horizontally.
Yeah.
And this is the area used, which is what you're trying to maximize. It's like low and then high in the middle and then low in the ends.
Yeah, but it's not like strictly bitonic. So like it's not going to be as smooth, like it's like I'm nitpicking the diagram, but it's not going to be like actually smooth. So there could be points where it like goes like up and then it like dips and then goes back up again. But like the general structure is it's like vague. It's like approximately bitonic is not like formally correct either, but it's like in the vicinity of this range, like the maximum has to be like in this like range, And so you just check all the values in there. And so that's why t is actually a little bit small. So if you look at the problem limits, you'll see that the number of limits, it's 1,000. And so the intended solution, I believe, is something like t times the square root of r.
So I still don't understand where the square root is coming from.
Or when I say like square root of r, I guess I mean like you sort of search this range of like 30,000 different width counts.
Why 30,000? Why not?
Why not more?
Why not more? Because if we like look at the circle, the length of the circle here is 2e9.
Yeah.
Like 2 times 10 to the 9th. So 2 billion.
Right.
Can the number of things here be like a billion?
Right. But what we're saying is like we're saying that it roughly goes up and roughly goes down. So we're gonna
guess this.
We're gonna guess somewhere around here and then check a big range, and you can show that it will work basically. Like because it has this structure, you can do this search. It's super hand wavy.
So what is this number roughly?
The judges said like 30,000 works.
30,000?
30,000 is like, yeah. It's like on the order of like square root r basically.
30,000 is the range you check.
Yeah.
Right, in each direction.
Yeah.
But you have to estimate the center somehow, right? How do you estimate the center?
You can do that by so like you can also do that by like just like you can do like sampling, for example. You can just sample a bunch of random values and then you like pick like the biggest one and then you can just like choose them all. Right? Like if we guess that the range is, if it's like this, you just like hit it and then you just sample the whole, you sample to like get a reference point, you like sweep the range and you so like grab
you
one.
Just like check a bunch of places, take the best one and then
but it like it's not exactly the ratio. Like imagine that the panel was square, right? If the panel was square, then the best rectangle will also be like
a
square.
Yeah.
Whereas like if it's like a long thin rectangle, for example, then even if it's like long and thin, like you still have this like baseline basically.
Yeah, you want something that's almost a square no matter what.
Yeah, so W equals H is like kind of like the actual like you want it to be roughly square to begin with because if you're trying to like imagine you're just trying to fit one rectangle into the circle, the maximum area ones are always going to be close to square to begin with.
Yeah.
So you basically want to try to approximate that. That's like kind of the intuition for it. So you can just start with like W equals H as like your estimate and then like pick around that.
I don't know. I mean, yeah, this makes sense, but it just feels like it's very easy to get wrong. I'm kind of surprised by.
I think this is one of these problems which is more like proof by AC and less like and less of proof formally. I like part of it is I think the way that you could prove it is like if you like focus on the like single rectangular case, and then when you think about like the deviation of the area as you like compress it into being like a narrow column or like a thin row, like eventually you'll prove that like it's mathematically impossible to squeeze in like the quotient of area of square divided by like area of like the source rectangle we're given falls below your threshold, and so you can, because of that, that's like the proof. And then the like square root of r bound is kind of just follows.
So Nick, you were mentioning a fun fact here. I think we have to bring them up manually. Lydia, can we get a picture of University of Alberta?
Oh no, not this fun fact.
They said they were self-described Schweiger, which
I
think they wanted me to say that's what they were.
Yes.
I want to be clear, that's what they say they were.
Don't worry. I remember seeing this and I remember being like, okay, I'm gonna have
Can
to
we get
explain
a
this
picture
on
of their
stream.
team photo? Is that an option?
Yeah, we need to get their team photo.
Schweiger, in case anyone doesn't speak Chinese. Am I pronouncing it right?
Basically.
Close enough?
Yeah, close enough.
It means handsome
Gentlemen.
We
don't have team photos?
We don't have team photos for 'em.
No.
Well, okay.
Okay, so
Maybe it's coming soon.
The context. Oh my god, I have to dig up the context for this. so I think like the University of Alberta and like Colorado School of Mines and Rutgers and so on, so they're like all like super tight knit. And I think in like one of the I'm trying to figure out which server it's in because I'm in like a bunch of them. They were like, oh, like the guy basically said like, oh, like they're like really handsome, and I'm like, but the guy like typed it incorrectly. So I literally cannot find it.
The Chinese version incorrectly?
I typed the Chinese version into like one of these servers, and I, for the life of me, cannot find it. I don't know which one it is, but yeah, they were. But I like corrected them. I was like, oh, like, did you mean like handsome gentleman? And then they're like, yes, that. And I was like, wow, that's. And so then they just like embedded that in like the fun fact.
Looking at their picture here, would you say 帅哥 or
oh yeah, for sure.
瘦?
Definitely 帅哥.
帅哥. Okay, there you go.
帅哥.
Well, you needed you for that. Nick.
Yeah. Okay. I is it time for our? I think it's time for our first guest, isn't it? Should I go check?
Yeah.
Is our
we can go get
first
him.
guest here?
I'll hold down the fort for a bit.
If our first guest is here, we should.
No, not quite yet.
Not yet?
We'll go fetch him.
Okay, let's look for our maybe let's look for our first guest because it's their time slot, and then I'll stick around until we find our first guest, and then we'll go from there.
We have Texas A&M. Handsome or not, Nick? What do you say?
Oh my God, I don't think I'm.
We're putting Nick in a real awkward position here.
No. Okay, I told all the teams I'm cheering for all of them, and honestly, all the teams are great. Yeah, asking to rate how handsome all of them are, I'm not here for that.
We got Vanderbilt. Fun fact about them: they have not made it to World Finals in over a decade, so they're hoping to break that streak today.
I'm cheering for them, cheering for everyone, but you know, it's gonna be a good contest. I think we've gotten a lot of very interesting activity in the first hour. We have 6 unique problems solved. The scoreboard is not just like a bunch of green columns. It's actually okay. There's like one big green column in K, but I think that was to be expected. And there's like a sprinkling of accepted everywhere else. Near the end of the contest, they're gonna coalesce into more of those like columns that we're used to seeing. But right now, like I'm really liking this like distribution.
MIT is coming back with their third AC on D, putting them in medal range, 6th place. BYU also had another AC on L. BYU has quite the team makeup. They have a piano player, a 27-year-old, which for the people here is pretty old. Comparatively, we're little old men commentating here, but
yeah.
And they also have the son of the creator of NumPy. You may have heard of NumPy. NumPy is a very, very popular Python package that's used in like every machine learning program everywhere. One of their fathers has created it, or mothers, I guess. I don't know.
Very, very cool.
Son could be either, but yeah, that's their fun fact.
Yeah, so we're now just cresting the 1 hour mark. So we've got a little under 4 hours to go. So you know, teams have sort of hit the ground running. So we've gotten these.
This puts our time a little weird because we started early, huh? So all of our times that are based on
our times are a little weird. I think
schedule's a little off.
I think
we'll figure it out.
Yeah, I think our guests. Our guests are like adhering. Like we slotted our first guest for 11 a.m. and it's 10:53. So we sent out. We're looking for our first guest. We're gonna hold the suspense a bit because they're a big deal in ICPC. This person has a lot of impact and a lot of influence, and they're doing some great work at ICPC. And one of the many people who helps keep ICPC running. Very excited to see what they're going to talk about. And, you know, we're going to have multiple guests on here. We're going to see a bunch of different faces. So, you know, so all sorts of people here in ICPC, coaches, staff, etc. It's going to be fun. We're looking forward to sort of showcasing everyone.
And hang on, UIUC with a dark green on problem F. Let's take a look at that. Can we see the screen here?
seven unique solves, and UIUC is they solve D at 64 and then F at 65. One of those classic
Oh my
examples
goodness.
of you print you like they coded F, but they're like the sample is wrong. They probably printed the code, and then someone else was working on D. Here we have Conqueror of Tourist on screen. Last night, he actually successfully conquered Tourist. There is an epic picture of their showdown, and Conqueror of Tourist did indeed conquer Tourist.
This is Dylan, right?
This is Dilhan.
Yeah.
Dilhan. And UIUC is definitely a team that some folks are expecting to like win. Like they are actually like champion contenders. So
They're off to a great start.
yeah, they're definitely off to a great start. So Conqueror of Tourist is one of the two LGMs at this contest. So obviously, you know, they're putting a lot of
And
you're giving a lot of attention.
And I don't know if you've mentioned this, but one of the things that he's particularly famous for is using Python. So you can see right now he's coding Python. He's coding problem A, it looks like, is their next attempt. Python's a very minority language these days. Usually C++ is the dominant one. Conqueror of Tourist is famous for exclusively Python all day, every day.
Yeah, but the judges expect like Python to be like the correct language to use because there are like integer issues. If you read, oh, here's the picture. There's the picture. So there's Tourist getting conquered and Conqueror of Tourist doing the conquering. But yeah, so problem A is a Python problem. In the problem like statement, there is this like constraint that they say like, oh, the values will be chosen such that the answers are less than 2 to the 63, which is the size of a 64-bit integer. Arbitrary persistent integers are very annoying to have, and the judges here took the stance that they don't want to force the implementation of these of like large integers, but large integers are still a cause for concern. But if you're using Python, it's not a big deal because you don't have to think about overflowing a 64-bit integer.
Fun fact about UIUC, their school actually changed their name recently to remove the word at. Used to be University of Illinois at Urbana-Champaign.
Yep.
Now there's no longer that at, and it caught us by surprise. But apparently it caught some of their members by surprise too.
All right.
Anyway.
Well, our first special guest is here. You're in for a treat. I'm gonna let him introduce himself, but he's a big deal.
Yeah, we'll be right back after this short commercial break. Welcome back. We've got Christian Lim here, coach of Columbia.
Hello.
Columbia's doing pretty well today, right? Let's maybe take a look at their screen. We
Sure.
can see your team live here. I think they were in 10th place a couple seconds ago.
Oh, okay.
We have some fun facts about them too. As I recall, Columbia has only 36 acres of the university.
Is that
Which
true?
is, I believe, the second smallest. The smallest would officially be NYU, who doesn't have a campus.
Oh, wow.
That's what I've heard.
Great.
Yeah.
Yeah.
Here, come over a little bit.
Yeah,
so
yeah,
you're,
sure.
There we go.
Mhm.
Everyone wants to see you. All right, so we got Northwestern with an ACNK. But anyway, let's take a look at Columbia. 11.
Oh, okay.
Let's hear him a little more. see what they're working on.
You gotta type in the password. Where's the password?
Are you able to read what problem this is? D, it looks like.
It's a D, yep. Mm-hmm. I'm making progress on B.
How are your thoughts on what they've worked on today? Looks like they have B and K correct, wrong answer on A, and D's in progress.
Yeah, and I think they were working on F when I left, but I don't think anyone's actually solved F, and so, I don't know whether they're gonna get the first solve, but likely, probably not.
So have you like been watching them backstage?
Yeah.
Split screen for the
Yeah.
teams?
That's
Okay.
right. Like there's a spectator zone where you can actually watch the teams, and they're actually talking about solutions and these things, and so then watching I guess Nick and you talking
Watching
about the
the
problems
stream
here
too,
is
yeah.
actually quite fun.
Wonderful. All right, maybe how about let's take a look at D, see what they're doing, huh?
Sure.
All right. Have you read the problems yet, Christian?
Yeah, just a little bit on some of them. Yeah, I know the topics for most of the problems.
Oh, wonderful. We'll show G here too. Let me just bring it up. Oh, we have an interactive one. It looks like.
Yeah, C is interactive.
Geometry Rush. What a statement. Okay, let me bring it up here.
Sure.
Okay. Geometry Rush. You're playing a game. You're playing a rhythm-based platformer, Geometry Rush. Oh, this is I've played this before, where your little cube dances. It's played on a 2D plane. Your character begins at 0, 0, and every second you must move at a 45-degree angle, either up or down, which takes your character to a position up one and to the right or down one and to the right. You can change which direction you move every second, but not between moves. The obstacles protruding from the floor and ceiling, there are obstacles that you have to dodge. You win the game if after W seconds you reach the line X equals W, so you get to the X coordinate W, and you've never touched any obstacles. The play area extends vertically from negative height to height, and the obstacles are polygonal curves. One curve starts at 0h, the other at WH, and they represent a ceiling of various height. Ends at WH. Okay, so you have like a ceiling and a floor, basically. You have to avoid hitting them. Maybe we have a picture? We don't have a picture. Darn. Okay. And you've played a lot of games, so what's the question? For example, you win the game no matter where you cross the goal line. For what maximum value of y can you win the game by crossing at this y without touching any obstacles along the way? What's the minimum value? So they're asking, you win if you finish at any y, but what y's can you finish at and win? Okay,
And
let's draw a
the
picture
minimum
here.
value is. Yep.
Okay, so you've got the floor and the ceiling here, and each of them have some things like this. Does it have to be a function?
Doesn't seem like it, right? Maybe so. Wait.
I guess if it's
Yeah,
not
yeah.
a function, the first thing you do is take the convex hull, probably. We have. Sorry, what are we looking at, Lydia? UIUC with a correct solve on problem A, putting them into first place.
Wow. Okay.
Well done, UIUC. Conqueror of Tourist is at it again. So we have this floor here, and maybe the floor is really confusing. Let's say that, for example. And then we have a ceiling, which might be... Oh, you can't just take the convex hull. That's not fair. So maybe something like that. So the question is, what y values can you finish in? So obviously, you're going to have to cross this gap here. And when you do that, you're going to want to... You can go here. You can go as high as that or as low as this. So this would be the range you can finish in.
And then you're looking for the mean.
The top and the bottom of this range, basically. Yeah. Okay. So that makes sense to me. It sounds like, I guess, how big are the x coordinates? That's my
X
first
can
question.
go up to 10 to the 5.
And are all of these points on integers?
Yeah.
Okay. So it sounds like we could solve this problem if we had a list of like, for every X, what is the top and the bottom of these polygons? And then we could kind of do a sweep through them and be like, okay, our range is here. And then our range when we step over is the intersection of this range here with, let me do a different color, with this range here. So there to there. And our answer, the range we could actually be at would be this blue to this blue here. Cool. Yeah, so now the main question, which I guess I'll prompt to you, is how would we go about, for an area that's kind of complicated like this, how do we go about quickly finding the range that we can actually be at, like for a particular x coordinate? So in this case, like this would be the bottom and this would be the top. How would we go about handling that?
Probably sliding window, no? Or should we?
Yeah, I guess we could. So the shape here kind of matters, but the only thing that really matters is like we can treat them
vortex, right?
independently.
Yeah.
So if we had like all of these, and we know they're not intersecting, I hope.
Yeah, I don't think so. Oh,
They better not be.
It doesn't say, does it? No, wait.
Oh, it does not self-intersect.
Self-intersect.
Okay,
Yeah,
good.
yeah, cool. Yeah.
So I guess it sounds like we'll maintain some sort of set here.
Yep.
In the sliding window, and we'll have them sorted maybe from top to bottom.
Right, and anytime the event happens, I guess you can add and subtract.
Exactly. Yeah. Cool. So yeah, you can do that, and then you get each of these, and you just process it one x coordinate at a time.
Yep.
Wonderful problem. All right, let's go back to Colombia, maybe. Can we take a look?
How are they doing on the sliding window?
Yeah, I guess we can take a look, see how far they are, see if they're even in the right track.
Yep.
I have an embarrassing fact about myself here. Only yesterday learned that Columbia, the university, and Columbia, the country, are spelled differently.
Yeah, one with the O and one with the U, yeah?
Yeah, the country has an O in it. The university has a U.
Yeah, that's right.
So
it took me some time to get that too.
They submitted the fun fact. They said Columbia was founded 56 years before Columbia, and I'm like, what does that mean?
Yeah, they're the same thing.
I thought one would be like a country and one would be the university, but I'm like, which one's which? And then I didn't even realize till afterwards they had gotten it correctly. All right, yeah, so let's maybe take a look. They're doing...
Are they doing B right now?
I think they had B open.
Yeah, seems like it. Yeah.
They're doing stuff with integers to avoid potential overflow, it looks like.
Precision errors, I guess. Or
Yeah, you don't want precision errors with doubles, exactly. And it looks like this is cross-product stuff, which is nice.
Yeah. Cool.
Yeah,
Probably
very
some
cool.
template code.
Yeah. Looks like they're copying from their team reference document too.
Yep. Seems like.
I guess let's get Columbia's fun facts out here. What do you say? They're 56 years older than the country of Colombia. We talked about their having a very small campus. It's in New York City, right?
Yeah.
In Manhattan?
In the Upper West Side.
Upper West Side. Wow. Yeah. I guess that there's not much room there, so that's why it's got to be 36 acres or 32 acres.
That would actually make sense, actually, because it's small.
And then they're also the least washed team by Code Force's rating.
Oh, wow.
So washed being the max rating minus the current rating.
Yeah.
They have, I think they're all at their max right now. They have a washed
Yeah.
score
Actually,
of
that's right. Yeah.
MIT is the most washed team currently.
Sure.
But they have quite high ratings. So,
Yeah.
Wonderful. All right. Anything you would like to? So you're the only coach we'll have on today, I believe.
Yeah. Really?
Yeah.
Oh, wow. Okay.
Anything about coaching you think would be interesting to share with people? Any fun facts?
Yeah, I think
fun events you've had.
I will say perhaps the coaching is fun. Let's say. Let's start there. But I think the real problem that comes up, or real, like, let's say, topic that comes up is how do you keep your team, good and keep the longevity and try to do it in a, let's say, decade or two or years to come. And one of the things that comes to like the spotlight is once you do well, then year after, how do you actually sustain the strength and how do you well? And I think the I'm not too sure if I know the answer to that question right away, but the way that I've been handling it is to try to do it through crowdsourcing or community, try to build a community around coaching, by which I mean we have curriculum committee within the North America, and also hopefully we can expand it to future to a little bit larger scope, and also internship that I am now directing within the ICPC context, so that we have more community members to join us. And I guess a lot of different initiatives, and try to make sure do the things that actually I'm passionate about, but at the same time try to make sure if they are not working out so well, then dump it quickly and then iterate. And that's kind of the mode that I've been operating on. Whenever I see things that are going well, try to do more of it. When I see that things are not going so well, try to pivot or try something else that actually works out better. So, and I think that I've been actually quite blessed to find that teams like UCF, where I guess you're a part of, you're from, I learned a lot of different things from, I think, UCF's coaching. The fact that you have do you have dozen now? I don't know, 6 to
Quite a few. Quite a few. Yeah.
It's like Arup and Ali, of course. I learned so much from, the predecessors or like the people who have been actually working to build the great community for, I would say, since the time I was actually was born, like 1980s, 1990s, and I think because they've been so successful in their managing of their team and their programs and etc. I am quite fortunate to be surrounded by people who I can learn so much from, and competitors, coaches, trainers, administrators, etc. And I'm hoping that in the years to come, Columbia can learn from the good examples and try to make sure that they do a proper, let's say, investment of the resources so that we can actually push forward in a way that is commensurate. Oh, I think the number one
It
team
looks
changed.
like, yeah, UIUC just solved problem B, and they're pushing forward with problem H.
Carnegie Mellon just got E.
Oh my goodness, yeah, Carnegie Mellon just got E. Wow, so people are moving quick here. It looks like they ended up with a dark green on F, too.
Oh, wow. I see.
So yeah, that's the geometry batch. No, that's D. We're talking about D.
It's a first problem solved, right? Yeah, it seems. Yeah, okay.
Yeah.
Cool. But yeah.
Anyway,
Yeah. So
well
then I guess maybe another aspect that I might do a little bit of a promotion on is there's a CLI symposium or Competitive Learning Institute symposium that I've been actually I guess working on for the past 2 to 3 years since the time of Luxor and Astana and now at Baku. And what I'm hoping for is we can actually as part of the community contribution enlargement and then making sure that we can have a lot of let's say excitement coming through. I'm hoping that we can actually advertise it better, try to make it larger, and then try to invite people like yourself.
And is this so? This is something that happens at World Finals in person?
Yes, that's right. So CLI stands for Competitive Learning Institute, and then there is a symposium, in 3 tracks, and for each of the tracks, we tend to invite anywhere between 3 to 6 people. So educate. There's library, and then compete are the 3, and people like celebrated stars like a tourist, and now this year we have competitive programmer. I think I forgot the names of the people,
okay.
But I think we have a lot of interesting people who are competing, and top competitors in Code Forces who are giving talks, and I'm hoping that in the future we can invite at least 1 or 2 from each of the tracks to give speeches about various different things that they've done to do well in this programming contest. And I'm really hoping that we can actually enlarge the community so that everyone can have a fun time while, during, and really before and after the contest. So pretty much every living moment.
Yeah, awesome. All right, well, thank you so much, Christian. It's been wonderful to have you on. I'm sure you'll probably go back and take a look at whether this sweep is working well or not. But yeah, thanks again. We'll have a quick ad, and we'll be right back after this ad from Citadel.
Cool.
Like all great journeys, it started with one person's vision and the drive to make it real. Empowering brilliant minds who turned ambition into action. We questioned accepted wisdom. We embraced challenge. And together, we changed the world of finance. Twice. Today, we are the most profitable hedge fund manager of all time. And as the next generation capital markets firm, we reimagine markets every day. But for all that we've accomplished, we've never lost the courage to begin again. Because when we act boldly and build together, we transform the impossible into the seemingly inevitable. Ideas are born, but impact is made. And it's made here.
Welcome back. We have more submits here from BYU, who's in just moved into 10th. We got UT Austin with a submit on D, and The Ohio State University, self-funded. Submit on D. They have the dark green of the contest, I believe, with an AC, bringing them up to 2 in 20th place. We also have MIT in 3rd place. Ooh, let's take a look at the scoreboard here. Or with a submit on B. MIT, it is running for a while. It's always promising. There you go. Moving them up back into 3rd place with an AC on B. Well done, MIT.
All right, it's time for me to talk about the 90-minute heuristic at the 87-minute mark. Close enough.
Yeah, let's give
Adjust the
MIT a
volumes.
little less volume. All right, go ahead. So yeah, tell us about what is this 90-minute heuristic, Nick?
Okay, so the number one question, well, maybe not the number one question, but I think a lot of people are wondering, like, what does it actually take to qualify to the World Finals? Like, what do you actually have to accomplish? And it's hard to describe this in terms of, like, the absolute, like, skill or whatever of the contestants, and it always fluctuates from year to year. But the 90-minute heuristic basically says, let's freeze the contest scoreboard at the 90-minute mark. And this snapshot here at the 90-minute mark will tell us, like, will give us all the information that is needed to identify, like, what it takes to qualify to World Finals, what it takes to get, like, a bronze, a silver, or a gold medal. So here's how it works. Can we take a look
at the scoreboard real quick, Lydia? If that's all right.
Okay, so what we're gonna do is we're gonna look and see how many problems have been solved. So right now the problems that have been solved are A, B, D, E, F, H, K, and L. That is
7,
8. That is eight problems. The 90-minute heuristic says you need 8 problems to qualify for World Finals. Exactly the number of distinct problems that have been solved at the 90-minute mark. The rationale for this heuristic is something as follows. Each of the problems that get solved at the 90-minute mark, by the 90-minute mark, is reasonably easy, right? Like, teams got to it within the first third of the contest.
And hang on, UIUC about to get H. They just got H, moving them into first on both problems and penalty, which means if it comes down to a tiebreaker, they're looking good. Oh yeah, UIUC is looking really good now. Yeah, there's this head-to-head. I think a lot of spectators were looking and they were thinking, like, they looked at the history of CMU, because CMU has team members who have been to World Finals and won gold medals. So I think a lot of folks are saying that CMU is, like, the odds-on favorite to win. I think it can go either way. I'm personally not, like, betting on anything. I personally think that if you, like, force me to pick between UIUC and CMU, I would pick UIUC. I think part of it is sort of like, I know UIUC has been training really, really, really hard. And I think that when you do train really hard, you're, like, in form. And there is something to be said for, like, being in form. Whereas CMU, I was talking to, like, their coach, and they were talking, like, they haven't been training, like, super hard. And so I think that, like, at NAC, like, being well practiced will give you, like, that little extra edge. But, like, I would not be surprised at all if CMU won. Like, I think that's perfectly reasonable. But if you had to make me pick between those two, like, coming in, I would have said UIUC.
I know it's a little bit late now. Anyway,
Yeah, they're doing well.
but yeah, anyway, so back to the 90-minute heuristic.
So we got 8 problems.
So 8 problems is the heuristic threshold. This heuristic is not bulletproof. In particular, one skewed thing that kind of happens, that kind of happens especially at NAC, is a couple of the teams are like quite a bit stronger than like the remaining teams. So when we talk about teams that we think have like chances to win, MIT is always like a contender. Like I think MIT, the only teams that have won NAC are MIT and Waterloo. And so people never...
Sorry to interrupt you, but Princeton is now our 46th team to get an AC on E. They are one of the oldest teams on average here, with every one of their team members being born in 2001.
Yeah, I also hear they play with mud in the Northeast. That's a reference to their team name. Actually, it is their team name. We play with mud in the Northeast.
Yeah, there you go.
But yeah.
Back to the folks who were born in the 1900s.
Oh my God, I feel so old right now.
We're gonna be fossils soon here, Nick.
We're actively gonna be aging on stream. Yeah, it almost makes you wonder, how much time do we have left together? We never know.
Well, you and I have 40 minutes left.
40 minutes left?
I leave and we get a replacement for me. For my lunch
Okay.
break. Anyway, this is 98. So you got 8. One of the reasons it's not perfectly accurate here is there's a huge variance in skill.
Yeah, so the strongest teams will solve problems faster, and so that will skew the 90-minute heuristic, like the estimate up. Historically, in the past, we've done like we have like evidence from the last NACs. Like the threshold has usually been like 7. Like I think like a fast 7 has been. Fast 7 was, I believe, last year, and I think the year before also something like that. I don't remember off the top of my head exactly what it was, but like I think people going in are expecting like 7 to be the benchmark. With this board the way it is, maybe it is a little bit easier, so maybe it will be 8. If you made me pick right now, I would say like a fast 7 is definitely necessary, but probably it could be 8. It could be like it could be 8 is necessary.
You're calling it right now. The bottom team solving 7 will not make it to World Finals. That's your prediction.
Yeah, I would say that. I would say if you like forced me to, say like is 7 sufficient, I would say no. I think 8 is probably sufficient. It's a lot of work you have to do, and the more problems you have to do, the easier it is for like you mess up on one problem that takes away from your total time, and solving 8 problems is still like it just like takes. It takes a lot out of you. You know, like sometimes, you know, the teams, they could use like a little pick-me-up. Like, you know, what if we like, imagine like midway through the contest, we just gave them all like milkshakes or something. Like that would be amazing, right?
They are given lunches, to be fair.
Yeah.
So they all have lunches at their table. They have 6 bottles of water, scratch pad for paper, fresh pencils, but milkshakes, yeah, I agree.
Yeah. Milkshakes in the middle, that would be great. Like
we have a series of very, very wonderful sponsors. If we get Chick-fil-A up on this list going forward,
Chick-fil-A.
people would love it.
I'm actually just like envisioning right now, like imagine that like halfway through the contest, this like you have literally this person coming in like a literal milkshake man just coming in and giving milkshakes to everyone. Like that would be amazing, absolutely amazing.
There you go.
Yeah. It seems Lydia has walked out.
We've lost Lydia because this is too funny.
Yeah, Lydia is
going to get us milkshakes.
Yeah, she's gonna get some milkshakes for us. That's clearly what's going on. She's been working like around the clock, you know, like
Iowa State also on the board, our 50th team with an AC on problem K. Congratulations, Iowa State.
Yeah.
The remaining teams we have are 2 left: Dordt University and University of Florida.
Yeah, but again, it is a marathon, not a sprint. So, I have complete confidence they're going to be able to solve problem K, and the other team members are probably looking at other problems. So, you know, there's always room to move up.
Dordt University loves corn.
Oh. Is that a fun fact? They just love corn.
It is. Yep. Keep it simple, straight to the point. Waste no time.
All right. Is it time to explain the solution, or at least a solution to that Arizona State fun fact
Yeah,
riddle?
let's talk about that real quick. So
Okay.
this is, earlier we talked about you have 2 envelopes. Both of them have a number in it, but you got to look in at most one envelope. And you want to maximize, or not maximize, you want to make sure that you have over a 50% chance of ending with the envelope that has the bigger number. But you only get to look in one of the envelopes.
So I gave the hint earlier that to think about like deterministic algorithms. And so deterministic algorithms have a little bit of a problem. So a deterministic algorithm basically means that you have you essentially are like more or less guaranteed to have like a 50% chance of success. Like if you're like, for example, like if your strategy is like never swap, then you win like you win like 50% of the time.
If you start with a random 1 and then you never swap, you
Yeah.
win 50% of the time.
And if your algorithm is always swap, then you also win 50% of the time, but it's like the other 50%. And so then the question is like, how do you actually like get above 50%? And if you know that it's possible, you could kind of actually guess that like you randomly make your choice, but then you also like randomly choose to swap. But the randomly choosing the swap part is a little bit tricky. So
basically, you want to make sure that since you're trying to end with a bigger number, you want to make sure you swap more if your number is smaller.
yeah. So the general idea is you're going to use like randomization twice. So like you'll randomly pick like one of them, sure. But then you're also just going to randomly pick a number out of thin air. We'll call this number like T, like threshold
Really
T.
quick, just to give an update on the scoreboard, CMU is now tied for problems with UIUC with their 7th AC.
Yeah, it's definitely competitive between those two. Once Lydia comes back, we'll try to get the head-to-head.
Yeah.
But yeah, so you randomly pick this like threshold T, and then you look at your number and you're like, oh, if it's less than T, I'll swap, and if it's greater than T, I won't swap. And so you can show that this has percentage like probability like slightly greater than 50%. The reason why is if you do swap, so it's like in what circumstances do you win and when do you lose? So you lose if either you picked either both numbers are less than your threshold and you picked a smaller one, or both numbers are bigger than the threshold and you picked a larger one. In those cases, your win probability is 50%. It's still the same. The case in which you now like win sort of like not deterministically per se, but you win if the two numbers like span the threshold, because now you are guaranteed to pick the number above the threshold and not the one below. So you're guaranteed to win in that case, and that's how you get like strictly greater than 50% chance. So that's the solution to ASU's fun fact. And we should find Lydia at some point. But I think one thing that people, I don't know if anyone has asked us in YouTube chat, but I'm sure some people are wondering, can ChatGPT solve the NAC problems?
Oh man, yes, we're just on schedule for that. Let's give it a shot. So, one of the questions is humans versus AI. We thought that we'd put that to the test.
Oh, you're gonna put humans versus AI you're gonna put ChatGPT that try to solve humans versus AI?
Do we know that? Is that too hard of a problem?
Problem E actually has been solved.
Let's take a look at problem E
CMU
first.
and UCLA have solved it at least. Have anyone? Oh, and also Princeton. Princeton's first solve is on problem E.
You find it on paper. I'll bring it up over here. So yeah, we're gonna take a look at the problem humans versus AI and see if AI is able to solve it faster than
in the world of rising AI, James is scared of losing his job. So when his boss asks him to evaluate a new AI model to see how well it performs, he wants to make it look as bad as possible. So to test it, he's going to conduct a series of N trials where a human and AI are given the same task and then scored based on their performance. He's going to send the results of some contiguous subsequence of the trials to his boss and delete the rest. So each
is dishonest
yeah.
science here.
So the AI gets a performance of A sub I and the human gets a performance of H sub I. And so if the basically the differential is the winner gets the differential of the scores. So like if the human got 10 points and the AI got got like 1 point, then the human would win 9 points. And then symmetrically.
Why 9?
Yeah.
Why
Because it's a
9?
difference. It's h sub I minus a sub I.
So the human got. Can you explain the example again?
So if a sub I is 1
Yeah.
and h sub I is
Oh, it's
10,
The human gets.
then the
9
human gets 9 because that's the difference. And then it's symmetrically like it's
per
it's,
round.
Yeah.
Okay, and you just want what are you trying to?
If
get?
so I'm still reading. If the human's total score is greater than or equal to the AI's total score times some constant k, then the humans are considered to outperform the AI. James plans to send the chosen subsequence through emails, but the AI is already all-knowing and all-pervasive, so it intercepts the email and can swap the value of h sub I and a sub I for one trial of its choice.
So the AI can pick one of the trials and change the human and AI score.
Yeah.
That's wild. Okay. So count how many non-empty contiguous sequences of the trial James can send to his boss to guarantee the humans will end up beating the AI.
So the thing is that
So what is that? So you have to beat your score has to be k times bigger than the AI score.
Yeah.
And the AI optionally it gets to choose whether it swaps
one pair.
So
it can swap the
1 or 0 pairs.
Yeah, it will swap the like biggest advantage that the humans get. Basically.
Is humans the first or the second array? First, I guess.
Humans is the first, and AI is the second.
So let's look at the second example here. So 4, 3, 2, 2, 3, 1, 1, 7, 7, 6, 6, 5, 5. So humans win 1 and lose 1, which means they can never. Oh, but they could tie. So 1 is you just have to tie the AI.
Yeah. So basically, there are the subarrays that work in that case are the first one. So the only 4 because you can't swap anything and it's a tie. And then you take the last 4 elements, any subarray of those. Mm-hmm. You can't win if you include the 2, 3 because then the AI will. Then the AI doesn't have to do anything. And if you include both 3, 2, and 2, 3, then the AI can. What can the AI do here?
Well, if you do both of those, it'll swap 1, and then I guess if you include both, it's fine. Is it? Because then if you get 1 point for one, it gets 1 point for the other. Oh no, because humans are already losing this one. Humans are losing the 2, 3. So if if you include the 3, 2, humans lose both.
Yeah.
So then humans will just be worse.
Yeah.
I see.
Funnily enough, the judges think that this problem is quite hard.
Doesn't seem obvious. Like it seems easy if it seems easy enough, I guess, if k equals 1 probably, but then once k is 2, to me it seems like it matters. Like the difference in scores is not the only thing that's important.
Right. Right. Anyway, I it seems that this problem is hard. Like maybe AI could solve it, but I was thinking for our first test, can it actually solve like the we can do 2 tests, right? We can have it do humans versus AI because it would be really funny if the AI could solve the humans versus AI problem.
All right, let's do an easy one. What should we pick?
I think we should just
B?
pick K. We could just pick K.
Pick K. Okay.
Let's
get K.
Do you have judge access?
Do I have judge access?
Or if you don't,
we can also just ask it.
If you don't have the judge access, you can send me the code, and I have access, so I can submit it.
This might not. The formatting might not work.
You can do a screen. You can do like a screenshot.
Just upload a series of screenshots.
You can upload screenshots to 04, and it'll do it. So I would screenshot just like each page, I guess, and I think it'll be able to figure it out.
Give it a shot.
Wait, I have not yet joined this contest. Oh, this is not the mirror. This is the other one. Okay. I will figure out.
Solve this problem, please. All right, let's see how it does. This is 04 Mini.
Oh yeah, we might need to tell it to print code to write code. So let's wait. Let's wait for it and see like what happens. Will it actually print code for us?
So it's thinking about how to solve this. It's looking for rows with hashtags and periods. After printing some cells are marked as something. I think it might be misinterpreting this. This is, to be fair, this is a very difficult one to be given an image for.
Maybe, but
It's also tough because with the tokenization of LLMs, it's like it's a very visual problem.
yeah, we'll see. We'll see what happens. Maybe we do just give it humans versus AI, but
Okay, MIT with an ACN F, moving them into third place with 6 problems, still behind the 2 first place ones with 7.
yeah,
O4 Mini, this is the strongest one they've got, right?
they have O4 Mini High, which will think
Oh.
harder about it, but it might take longer. Like O4 Mini might like quit early. I seem to recall O4 Mini High having like some limited number of usages that it is, or like you can only invoke it so many times in like a period. I guess we could have used it, but I think O4 Mini is probably good enough. Like I don't think the difference between O4 Mini and O4 Mini High is like that big. But this does seem like it is getting a little
It's thinking.
stuck.
It's thinking.
It is thinking. If it gets stuck, I think we should probably tell it like, please write a C++ program to solve this problem, and maybe that will. I don't know.
Oh, yeah, I guess I didn't provide that context.
You might need to.
wait
You might
to
need to.
kill it.
Oh, did it? Something happened. You may
I
need
think
to
it's still
you may need to
thinking.
stop it and then just
Kill
issue the query to write a C++ program. Okay. Hopefully it doesn't require you to re-upload the
Is it
screenshots.
context?
Context should work, right?
All right. Well, we'll see. We'll see. Maybe we'll come back in a bit.
May-
I think humans probably had solved it faster. The time between reading and us
yeah,
having
yeah,
the
yeah.
solution. Maybe we hadn't had the code yet, but all right.
Yeah, and then if that doesn't work, we'll put it again. We'll put it on humans versus AI. That it seems only topical.
So yeah, I guess. Well, it's thinking. We'll come back in a bit. How do we even approach this humans versus AI thing? This seems like a fairly difficult problem. So my first question is there any reason for us to sustain a loss in the range we pick?
We
Like,
we have to, right? Like if the AI is allowed to perform a swap.
Well, I guess, all right, first thing is we're given 2 arrays of numbers. The only thing that ever matters is the difference between the numbers. So we can just compress it into 1 array without losing any information.
Is that true?
And it just negates one of them, right?
But
So if the numbers we have are 1, 3, 2, 5, this is the same as us just having the numbers -2, -3.
But how do you encode the
A swap is just, it goes from -2 to 2.
Does it?
Because when you switch these two, you just negate the difference.
Oh wait, you're swapping. Oh, you're swapping. Oh wait, did I miss? I think I misunderstood the statement. You're swapping h sub I and a sub I. So you're flipping the sign. Okay. Sure.
So we were given 2 arrays of numbers, but basically we just have 1 array of positive
Okay.
and negative numbers, right?
Okay. Okay. Yeah.
And we
yeah.
want a big positive sum.
Okay.
5, 0, 3. Like, so let's say this is the array.
Mm-hmm.
So if we were to pick this range here,
Mm-hmm.
we need, it's going to make this -5.
Mm-hmm.
And then the bot will have 5 points. We will have 3.
Mm-hmm.
Okay. Is there any way we can combine our scores into one that's useful?
So, okay. So I think.
Wait. So sorry. I think I figured out how we can do that.
Yeah. So this is so what we've done here is we've basically reduced this to like a data structures problem, right? Like there's some like data structures reductions that are happening here. Like what are the things we care about? We care about like range sum, and we care about range min, right?
We care about, well, hang on. So we're not quite done yet, I don't think. So the question is like, we need the bot's score times a certain number to be less than the human's score. But the score is difficult right now because the score iterates through every element. So we want to make it a simpler way of measuring score.
Right, but but you can just do this as like range sums, right? Like you're keeping the like you're answering like what is the sum of the positive integers in this range? What is the sum of the negative integers in this range, right?
Is that the case? Because if it's something like this, like a bot score of 3 and a human score of 4 is not the same as a bot score of 1 and a human score of 2. Because here, these are not a factor of 2 apart, but here they are.
But I'm saying
the sum is still 1 in each case.
How is
this is -3, this is -1.
Sorry, I don't follow. Like,
so if ignoring the flipping, if you have -3, -3, +4, this has a range sum equal to 1.
No. I'm not saying global range sum. I'm saying just range sum over the positives and range sum over the negatives. So so you have two array. You have the human the human delta array and then the array delta array, the AI delta array. And so you're doing if the human wins, then they get X points for that, where X is the difference, and otherwise you've put in a 0 there. And then for the AI, if the AI wins, you put like Y points in there, and otherwise you put in a 0. And then you're computing the range sums. That's what I have
potentially an easier way to think about it. Can we try that real quick?
Sure.
So my conjecture here is that of this array, it's 0 sum, no matter what the bot chooses. So 2 points are going to be distributed for this, 3 points for this, 5 points for this, 3 points for this. So we know the total number of points distributed for this array will be 13.
Sure.
So we know if a human needs to get double the AIs, we know what that would need to be. Oh, but that's tough because as we expand this range, the target changes.
I mean, I have a smell that there is
All right.
some like persistent data structures here. I mean, I haven't actually thought about this problem because it's like, there's like yeah, I have a sense that there's definitely some like persistent data structure that's like coming here.
So we don't know yet is the answer. We're not smart enough so far.
I think
that's the answer.
I think I could like talk myself. I could like talk through like my thoughts out loud and like try to like construct some sort of solve path, but
Okay.
I'm not well equipped. How's 04 doing?
Let's check.
Oh, it sent code.
An order n C++ solution.
All right. Do you wanna send
that's
that?
very plausible.
You wanna send that to me?
Yeah, let's do that.
All right, send it to me, and I will submit it. And
Send it to you on
Discord. Discord's totally fine. I need to annotate like, provided by 04 mini. I need plausible deniability. In case you know I get accused of AI cheating. Okay, copy.
This looks a little more complicated than it needs to be.
I'm not surprised. This code was written by 04 mini on broadcast. Just gotta cover my bases, cause you know, definitely a little sketchy. This is the problem K. Submit. Okay. We'll at one shot. Oh, actually, people can see this on the scoreboard because the scoreboard is actually like public. It's actually public here. Oh, it did.
ChatGPT got it.
Wow, I got it. Amazing.
It's impressive. I'm impressed.
All right.
Color me impressed.
Did not even look. Okay, now we got to do E. Can it solve problem E?
All right.
I'll let you.
Has
it
E been solved in the human?
Yeah.
Okay.
It's been solved by 3 teams. Like, let me check how many teams have solved it.
Man,
now it's 4.
Nothing
so
makes you feel obsolete like an
CMU,
AI doing
UCLA, UCF, Princeton. I'm sure it's just some data
UCF
structures.
got E.
UCF got E. I'm sure it's some data structures, but right now I have commentator brain on and not like programming contest brain. But my programming contest brain is also kind of broken. People have been asking me what my job is here at NAC, and I feel like I have like, you know, 6 different hats on. You know, I feel like I see colors I never saw before. Maybe I'm a little paranoid and I'm slipping from reality. And it's making me question all that I thought true.
You're just a prompt, Nick. You're just a prompt.
I'm just a prompt.
All right, we're giving ChatGPT humans versus AI. If it can get this, good luck to humanity. Yeah, because this one's tough. So, all right, let's think about it out loud a little bit. So we have.
Oh,
Scoreboard?
Scoreboard?
What's happening? UIUC has 8. They have problem M with a dark green on it, it looks like. Also, they have a dark green on F, M and F, so that's 2 dark greens.
And
Going after, they're writing NTT. It's like FFT, right?
and so I would just like to call out that in the mirror contest, USA 1 has not solved problem M. So you know, UIUC definitely punching pretty hard.
And
This is the mirror.
Kusaga is also doing well.
Oh yeah, Kusaga. Yeah, so Kusaga is the coach for MIT. He's is he
Kusaga
current
has,
LGM?
He has 8.
Yeah,
right?
he has. It looks like it's 8.
And USA 1 has 10.
USA 1 has 10. So USA 1 is
Well,
winning.
yeah.
But you know, UIC solved M before USA 1. That's still an accomplishment.
Well,
It claims.
it claims it's got a solution.
Oh my God! All right,
some-
you just gotta send it to me.
Are we gonna try
Where
Discord again.
if
I guess.
it one shots it, it one shots it. Hopefully it'll upload.
And then at this point, I feel like I've got to go
You gotta go eat lunch.
eat lunch
Yeah,
and then
let's get
like
you a
actually
break.
read what it wrote here because this is a little depressing.
all right. I'm resubmitting. So we are submitting this file to humans versus AI. Submit. Okay. I'm not even reading it. I'm just.
In case others would like to read,
I've got
should we-
faith. Do I have faith? Oh, wrong. It's wrong. Wrong answer.
2-pointer monotonic cue.
That sounds like directionally correct.
I mean-
like without having thought about it. Let me run it on the samples. Let's see if it actually passes the samples.
This is the problem with AI models like this is they are very good at writing things that look right. Being right though is the real. But I like this personality. I don't care about your personality.
This printed. What the hell? This printed like long max or something. What am I looking at?
Well, it's AI slop. What'd you expect, right?
I'm reading it. I'm like, hold on. Did I copy this right? Because it's like it's printing out like some truly nonsensical stuff. Let me I'm actually gonna run it with like sanitizers just to make sure that I've like. Oh, it doesn't have freaking bits. Okay, I gotta paste in my template real quick.
All right. Well, Nick will figure this out as we watch this ad from Hudson River Trading, and then we'll be right back after the break with some new commentators. See you soon.
HRT brand anthem, take 1.
Dream come true.
So I'm not looking at the camera, I'm looking at you.
Hi, Oprah.
What's the makeup department?
Should I like sit up straight or something?
All right, I'm ready. We're mathematicians, we're statisticians, we're data scientists, we're computer programmers, we're engineers.
We're a multi-asset class, multi-time horizon, multi-geography firm.
We are highly quantitative. We take a very scientific approach to trading financial products.
Our algorithmic trading strategies are some of the most sophisticated in financial markets.
We're always innovating, and that has led to some really interesting problems to solve.
The fact that we're able to do so much with a relatively small set of people, I think speaks to our ability to really put automation into practice here.
All of us work together to make markets fair and efficient, and to do so in a really highly automated fashion.
So back in 2002, when the company was formed, we were a proprietary trading shop.
Data science was barely a thing.
Using computers to trade stocks was not definitely going to be a big part of the market. But you know, we've been kind of at the forefront of that journey.
The breadth of what we do now in terms of the types of trading strategies, the markets we trade in has increased, and we've become so much more ambitious.
And today, we have the ability to trade in a bilateral fashion, yet we're still doing what we have always done. So in the US equity markets, for example, you know, we trade over 10% of the volume in that market every day. And that's very significant for a firm of our size.
HRT as a company realized early on that its value came from its people.
HRTers really have a deep sense of community here.
And that really starts at the top, with the partners and the management team.
You're encouraged to bring your true self to work every single day.
I feel like my opinions are very well respected and I have a lot of say over what I work on. That's like a really rare environment to find.
We all share the same values of math is important, engineering is important. We like to work on an interesting project and we like to be nice to each other.
You have coworkers, not competitors, sitting next to you. You can relax and have fun with them. You work with people that you wouldn't mind going on vacation with, because we actually do go on vacation with them.
We're extremely successful in what we do, but we don't take ourselves too seriously. That ethos makes this a really fun place to work.
HRT inherently sees the value in technology and how it can make not only what we do, but how we do it better.
You really get open-ended problems and you get to invent things, and then they get tested very quickly. When you deploy code, it is live. It is trading in minutes.
We essentially drop the silos, drop the barriers between people, and try and promote as much collaboration as possible.
We value each person for who they are and for what they can bring to the company.
It kind of pushes you to come in every day and do your job knowing that what you're doing is going to impact the company as a whole.
If you can work with the best people and work on some of the most interesting problems in computer science,
and you're able to collaborate with people who are, one, incredibly smart, and two, also thinking about all these interesting problems, so that's a fantastic combination.
Hello and welcome back, everyone. Here I am picking up after David is gone for lunch. Hi, my name is Lydia and I'm the ICPC Live Director. Thank you, Nick, for being the insightful trainer, analyst, judge, coach, everything that this broadcast is always missing. I think everyone can hear us well. I think everyone can see us well. Life is actually good. You see, I've just got their fifth problem. I hope that David is actually watching because, hey, Alma Mater are doing so good today in the contest. You see that in the testing queue, their place number is actually colored with that interesting rusty. This implies that if contest is to stop right now, then first place gold medal would go to Urbana Champaign, then second and third places would receive silver medals, and then fourth and fifth places and sixth place will get bronze medals, including UCF. What an awesome result. I had not too many chances to look into YouTube chat, so hey chat, what's up? How you've been doing? Vivan says I'm doing Codeforces round 1027 live right now. You should have been solving NAC mirror contest, but it's okay, the choice is yours. If you want to solve NAC problems online, then follow the link in the description. You need to register for online contest. It usually takes a couple of minutes to go through. Oh, UCLA tries to take over yet another bronze medal, but no, they're still in the same place. Another useful links for you all. We have scoreboard, we have problems PDF, we have another YouTube video on the same channel, on the same ICPC Live channel that you can switch to. You can spam your university hashtag on the second broadcast, and this will show you your team, screen, and webcam. So if you really don't want to listen to us, if you really want to just look at your team, spam that hashtag there. We don't have any timeouts. Just, increase those engagement numbers on YouTube. I dare you. What else are we having? Blah, 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 blah. Oh, reaction videos. By the way, shout out to our wonderful volunteer. Elle has been doing an incredible job in making sure that the most interesting reaction videos are hitting you on both on Facebook at ICPC North America as well as on our dedicated to ICPC North America YouTube channel. So if you want to see all the first to solve reactions, definitely tune in there. And it seems like my software is working. So a couple of days after the end of NAC, you'll be able to find all reaction videos on the website, including reactions from freeze time, which no one will see today because at 4 o'clock mark, we'll have our screens cut off. Hi gaming, but not really. Yeah, we're not gaming here. Everything's really
I
serious.
guess that's true. We are definitely, we're serving a lot of content for all of you out there, and we hope that you're able to find what you're looking for. So We have a question here, which is how many teams will advance to the next round? And I wish I could say, I've got a secret that you should know, but it's actually a secret that I don't know.
Okay, sue me.
Yeah.
I think every region, including North America, is guaranteed 12 places. Absolutely guaranteed. Nothing should happen that this number is lower than 12. But then generous wildcard, as well as places that are decided performance-based, are given out. So our statistical analysis, which has completely zero paperwork under it, but we are just looking at numbers over the last 5 years, says 16 is probably the number, but don't quote me on that. I'm here as your most unofficial gossip source, and yeah, 12 is definitely guaranteed. So it's not just the number of medals, how people sometimes think, because in some of the different regions, you're getting like 12 sets of medals, and 12 teams are guaranteed, so this is somehow connected, but no, in this case, that's not just the 6 teams that are getting medals, but somewhat more. Hey.
We have someone asking why no Caltech? Well, Caltech is definitely here.
Let's look at Caltech. Oh, Dab. Yeah, by the way, so I have all the admin interface buttons to show you teams. So now for the next segment of this fantastic broadcast, you let me know who you want to see, and we'll just look at them. I'm very interested in making sure that all the teams have at least some time that we're showing them on the live stream. And so, yeah, let's find something fun. Oh, by the way, do you want to guess which team was in my interface on a live broadcast the most since the beginning of this contest?
Columbia?
Columbia is definitely, way up there. I think Boston University, for whatever reason, goes a little bit around them. We have an algorithm that tries to figure out what's up in the contest, what's interesting right now, and this part of it is pretty fascinating. So, algorithm was loving Boston University a lot. Let's go look at them. Oh, nice! Here are some boats. Keep them coming. Let's go. Awesome. UCF. We've shown UCF plenty. Are international students allowed in the Harvard team? Well, they are not expelled yet, and you only need to be a student at the moment of a regional contest, which happened in the autumn. So Harvard team is completely safe, at least ICPC-wise. We hope that everything will be solved as smoothly as possible, as soon as possible. We also have submission from, is it MIT? They're trying to go up from their 3rd place. Another problem will surprisingly not move them any higher, even if they get accepted on problem E, which is obviously awesome. Solving problems is the goal.
And
that's what you're trying to do. And they're still in 3rd place. Imagine that reaction video. You started in 3rd, you finished in 3rd. One more problem. Oof.
Well, I'm sure MIT themselves, they're MIT is kind of infamous for having very muted reactions, and they kind of know that people are going to be watching them. So on the one hand, you have people like Radewush, who are a little bit
Shout out to Radewush for the best reaction videos in the history of ICPC.
Yeah, you have people like Radewush who have great reaction videos, and then you have reaction videos from like MIT at NAC 2020, and it's like, wait, they actually did something? Like, they nothing looks different.
Yep, because work. We are now looking at Texas at Austin. Here goes Samir. I think they're doing fine. Like, 4 problems, 9th place, very clean, 0 incorrect submissions. And also, look at that timeline. That timeline is, I think they approached the timeline with, like, a ruler or something. Look at this perfectly identical durations between each problem, as if they're actually of the same difficulty, and it's a Codeforces kind of blitz contest where you just look at the next problem, solve it. Look at the next problem, solve it.
So in the North America programming camp, in the very first training session, one of our trainers, Jingmang, gave a lecture on contest strategy, and he gave his quote-unquote foolproof way of getting into World Finals.
Solving problems? Waiting 2,000 days? Okay, I see.
It's I don't know. Anyway, I mean, it's not my fault. I got carried away, but The strategy goes something like this. So every 40 minutes, you solve a problem until the scoreboard freezes, and then you solve one more problem, and then it gets you 7 problems, and then that's how you do it. So this is the strategy that he advertised. You will note that, like half an hour ago, I was talking about the 90-minute heuristic and how I think that you'll need to solve 8. So, obviously these two things are directly in contention with each other, and we'll see. We'll see if the 90-minute heuristic pays off, or if Jingbang is correct. And I would put more faith in Jingbang. He put a lot of effort into like actually thinking about like how these contests work, and he's like the most out of all of the trainers that we had. He was the most recent to be competing in like ICPC World Finals.
Right.
As a 2-person team, Jingbang and his teammate Yu Gao from Georgia Tech, they got 13th, and that is very impressive to get like they almost got a medal as a 2-person team. Like that is definitely a crazy accomplishment.
Yeah.
And I mean, it's heartbreaking. Like I'm sure he really, really wanted that medal. And it's unfortunate, but like he should still be really proud of like the performance that he and his lone teammate put in.
Well, I have a couple of examples where contestants who thought they have not achieved everything that they ever wanted from ICPC at the World Finals, when they were contestants, moved on to be, 7-time world champion coaches. So maybe Jinban will just, have a proper kickstart to his coaching career. University of Waterloo looks excellent. If you look at the achievement box at the bottom of the screen, sometimes it shows University of Waterloo achievements at the World Finals. And it's not just 2 trophies, but also, what was the number? Something outrageous. Was it 31 World Finals participation? So definitely here at NAC, we have plenty of universities that are like mainstays at the World Finals, and some are just, young, up and coming. So that's a lot of fun. And we also just saw a submission from... What? I'm sorry. I have like a memory of a goldfish. Let's look at the scoreboard for a second.
We have. So we were talking about the bottom of the scoreboard. So there were 2 teams that didn't have any problems solved. The University of Florida, their first solve is problem E, and I'm sure that the judges were not expecting that.
That's sus.
I'm sure the judges are like, they should be solving problem K, or they should be solving any other problem that isn't problem E.
No, hold up, for real. Look at the stats. Like, can you read a scoreboard or something? Like, read a room.
But it is. I'm down for this. Like, I'm down for teams to say, like, you know what? We can't solve problem K, but we can definitely solve this.
They can solve problem K. What do you mean they can't?
But they were like, we can solve problem E, and so they've solved it. And so you know what? That is worthy of balloon. They're definitely gonna get that.
Weird flags, but okay.
That
Speaking
balloon.
of balloons, look at the team area. It's actually so cute. And here we are currently at the UCF, and it's one of the larger ballrooms in the building. And I really love the fact that there is plenty of air to fly those 1-letter balloons. You see A on the left, you see D somewhere in the middle, and then a bunch of other letters are currently rotated.
Actually, we need to step back for a little bit. I realized that we actually did not explain balloons at all. So
OMG, what were you doing?
What were we doing? Again, I'm sorry. I got carried away. But okay, so what are these balloons? So let's imagine that before YouTube existed, you're here and you're at this programming contest, and you're here to watch your team. We're gonna watch Richard stare intently into the screen.
Time limit. Boo.
And so, like, what's going on? Like, is my team solving problems? Are they not solving problems? So, someone had the whimsical idea of let's give a team a balloon for every time they solve a problem. And that's it. that's the
looks
short
really
version.
nice, because before balloons were introduced, teams actually moved around team areas so much. Instead of submitting through a network interface, they wrote their solutions on a floppy disk. Dear spectators, all 176 of you, how many of you were born after year 2000 and only seen floppy disks when there is a solar eclipse. So remember in the old days, people actually inserted floppy drives into personal computers to use it as a data storage. And then you would literally go in person, make some steps through the team area to give that floppy drive to the judges. Then judges would run it. And imagine how many steps would every team put in, every contest, right? Actual sports programmers. Not that, intellectual work, but actual physical work. But now that contest floor became so much more static, balloons are adding this wonderful color and movement, which I just love to see it.
Yeah, but if we pull up the statistics again, and you look at the distribution of like how many times each problem has been solved, this distribution actually looks a little flat, and like that's actually a good thing. So K, the teams have largely concluded is like the easiest problem. We have 51 teams that have solved it. Only Dordt University, they are the final holdouts on problem K. But then after that, like the solve counts here are like pretty close to uniform. You have like what, 26, 18, 16, another 16, 11. Like it's definitely like a little bit of like a flatter difficulty curve than maybe in previous years. And so that's like really, it's really exciting because what it means is teams they'll have a lot to work on. So when the contest has like a less flat difficulty curve, let's say, there tends to be a prescriptive order in which teams solve the problem. So they'll solve them, and then you'll get these like the green column effect. So if we pull up the scoreboard, for example, like there's this big column on K, and like the columns are starting to form a little bit more coherently now. So like A and B, you can kind of see these like clearish columns. H is a little more sporadic. D, you're kind of seeing a little bit. E is like kind of is really funny because like the University of Florida solved as our first problem.
Is Urbana-Champaign actually doing E right now? Dear viewers, so our preview monitor is a little far from us, so can you please assist us in figuring out which problem Urbana-Champaign is currently working on, and then just comment it in chat, we'll be fine. I am a big proponent of the idea of, early game, mid game, late game contest problems. And this contest is, in a way, oh my god, it was so confusing for me. Obviously, K is an early game problem. That's not a question. But then, am I actually supposed to call problem A an early game problem? I don't want to call B, D, and H an early game problems. They were kind of in after the first hour of the contest, like actively for many teams, so really not so much. And then, yes, absolutely, problems E and F and M will be the ones that decide the set of medaling teams. But then if you're actually trying to win NAC, which is actually a lot of hype, you get a really pretty trophy, you can see it in the front of the shot. And also, all kinds of respect and admiration from audience in North America. But like, if you really want to win, which way are you actually going in the scoreboard is super unclear. I think by the 4-hour mark, they'll definitely have all the currently open problems, including the, poor problem M in question, which, who's the other team that tries them? Georgia Tech? Yeah, maybe problem M is actually something that will be on a table even pre-freeze. And then you're left with C, G, I, J. Well, 4 hard problems. It looks kind of scary.
Yeah, so I'm looking at the judge predictions here, and so the judge predictions say that their expected hardest problems were E, G, I, and J. E is already defying expectations.
Yeah.
C is very contentious. So C is the promised interactive problem. So for a few years. For a few years, NAC refused to have interactive problems, and then this year, interactive problems are actually on the table, and there was a lot of rumbling from like the chief judge side where they were like, by the way, here are notes on the interactive problem. There may not be an interactive problem, but just in case there is one, here are the notes. Nudge, nudge, wink, wink. And I think like everyone was expecting an interactive problem, and I mean they delivered, and no one has submitted to the interactive problem, completely unsurprisingly.
No, it's not unsurprisingly. I think first of all, the first interactive problem in a contest ever historically is always a binary search. There are not too many things in interactive problems that can be introduced to like, a wider audience as their first meeting with an interactive problem at a specific contest format. That is not a binary search.
Yeah.
And so like what can happen? Manas, no, Anton is not on MIT team. I'm also heartbroken. Hi Anton, I hope you're watching. We miss you here.
But yeah, so interactive problem. So this one is actually really funny. It's a bitmass DP in an interactive problem, and I'm sure no one expected bitmass DP interactive problem in the same sentence.
Yeah,
so,
that's sus.
But yeah, I'm looking at the scoreboard, and yeah, it's like UI/UC is almost definitely working on E at some level. Maybe they're not coding it per se, but they definitely have.
They should be looking. Yeah.
They definitely have folks who are looking at it. And then so C, G, I, and J have no submissions on them whatsoever, and so these are some like I would fully expect C to be like. I guess in your words, like a mid to late game problem. I think it's implementation heavy. It's not very thinking heavy. I think it is very obviously bitmass DP when you look at it. We're obviously talking about it at a very high level here, but I think the experienced teams will kind of look at it. Some of them are going to run away because the statement is really long. And I mean,
we know that they're typing J, but also like it's very hard to see from that camera angle what are they doing on paper. So yeah, question mark. Can you open the judging prediction again? Like what's with M? It was not on the list of your complicated problems. Are you trying to imply that M will actually get plenty more solves, like on the same level with E?
M is controversial, or M is contentious. I should really internalize the word contentious here. So what happens is, so to be clear about what these judge predictions are, so the judges each submitted their predictions for the percentage of teams that they expect to solve to solve problems. And so, for example, for problem K, the expected number is slightly shy of 100%. Teams are hedging because I think they're evaluating them on some like random metric. After K, the two next predicted ones are H and L. And it's interesting because like H has 19 solves, but A has 27. And meanwhile, L currently has 11. The judge predictions are not about like speed of like solving, but is more about like like you have 5 hours and like what's the general sort of like the general difficulty. So like H and L are like problems that are, let's say, simple in a sense. Like they don't require like heavy algorithms or whatever. It's a little bit of just like, just like one observation or something, and then the implementation is like pretty straightforward, and then you go from there. Whereas I think A and B are like more thinking heavy, and so it is easier to get stuck on them for like longer periods of time if you don't have the right ideas.
Interesting. In the ones that are non-implementation heavy, like non-idea heavy, are you implying that there are not enough opportunities to have a bug and then like debug it for another extra hour?
So I think L is very implementation dependent. Like the idea is fairly simple. We talked about this idea of like you like scan this range of values, and that's what that's just how you have to chase it. And once you scan the range, you are like done, so to speak. But there are two traps. There's like a floating point trap, which they have a case for in the samples, and then also like but you have to pick like a range that's big enough. And I think picking a big enough range is the sort of thing where like it's easy to pick an incorrect range.
Yeah.
And so teams.
But don't you just spam and you'll be fine?
Right. But this gets a little bit into what I was talking about in my lecture at the programming camp. Were they listening? I don't know if they were listening. So I gave a presentation, and the title of the presentation was "What Would Chica Do?" And for those who aren't in the know about who Chica is, you should look up the Love is War anime.
Okay. MIT is now in second place, which is yay, go MIT. But also, I opened a link, one of the links we had on our broadcast, and I had to watch 20 seconds of ads for MetaQuest Civilization 7 that I already own, and it's attached to my Twitch account. So Meta, please stop wasting ad budget advertising Civilization 7 for me. I already own it. But that was the situation. And we have a situation. Tourist Eknerval and Kaysun, 90 minutes in, question mark. Okay, apparently 109, but I'm not sure when exactly they have started because there are no extra early submissions. Are 2 problems down. I think the only upside of the screenshot that we're currently looking at is, hey, they haven't solved problem M. But on the other side, hey, we know it's solvable, so probably danger.
I'm surprised that... Wait, the implication here is that C is like actually hard. So maybe the judges... Maybe we're all wrong, and this problem is actually secretly impossible. But... On the plus side,
have you missed saying it is like 109 minutes into the contest?
Yeah. But like on the plus side,
okay,
very soon we might be able to be joined by these folks on stream.
Yay! More volunteers for live broadcast. So yeah, Manas, in some sense, tourist team is doing mirror round, but also in the other sense, they're almost finished, which is good. Good contest. Kids will be happy to get their insight. And UD Texas and Dallas go up solving their 4 problem. Good job. That's a very nice progress in the scoreboard. Again, they are currently in 15th place, and we kind of think that 15, 16 is somewhere around, the threshold to advance to the World Finals. So yay. Who else do you want to see? Hey, chat.
I will let chat say that, but I heard a rumor over like last night about people doing the mirror contest, and someone was like, oh yeah, we'll just spend 2 hours and then we'll be done. And I've been told they're a little overconfident, and maybe that'll be their downfall.
Yeah, we'll see. Who am I to tell?
Yeah, if you know their names, then keep it a secret.
Yep.
We're not gonna talk about them.
Yep. MIT screen, we saw it a little bit. So yeah, let's look at Wisconsin Medicine. They're currently at 1 problem, but they have 3 problems already attempted, and it looks like they're like really working on them. So I would not be surprised at all if Wisconsin Medicine would, even though with somewhat rough penalty time, end up in like a range of teams advancing to the World Finals. Again, 4 problems solved at this point, and we are hitting the middle of the contest mark, literally right now. Sorry, 40 seconds later.
Yeah,
when you are looking at this video, we've already hit the middle of the contest mark. And it's been a very interesting tempo for the contest. I think, again, dynamically, the beginning was probably my favorite part in a way that so many problems were open. I usually see teams blindly following scoreboard, and here at NAC, well, kudos to trainers, I believe, because there's been plenty of talk about strategy. Teams are actually solving the problems they can solve, as opposed to just, OMG, let's follow whatever other teams, and then end up telling the NAC champions, oops, I guess we overestimated you. You skipped these easy problems and went for these more complicated ones, even though it would be more optimal to solve them in right order. So yeah, don't follow other people's path. Choose your own. I wish to see Zhang Lian and Devin one, but I see them in Asia round someday. Yeah, advance to the World Finals, and we'll try to bring Zhang Li and Devin one as our either contestants host for broadcaster stuff. Zhang Li streams a lot, so yay everyone who streams competitive programming. Good job.
Can we show UC Davis?
Absolutely.
I'm lurking in their Discord, and there's some poor. There's like one kid that's awake at 9:18 a.m. in California.
Good morning, California.
And they're like, can we please like get more people to spam UC Davis? But they're competing with the East Coast. It's noon here. Everyone's wide awake, and so I figure, let's put them up on the main broadcast. I'm sure someone out there will be glad to see them.
My pleasure.
UC Davis has been helping us do a lot of beta testing for
OMG
Blitz.
Submission on J.
Oh, they submitted J?
And Carnegie Mellon F? Huh?
Oh.
Huh?
UIUC on J?
Which buttons should I click? I click this.
UIUC on J? We're gonna try to get the live reaction.
I'm doing something. Who's the other one who submitted?
Carnegie Mellon. They got F.
Let's go. Can we do something like this?
Oh boy.
Drum roll, everyone. Is it a time limit? It takes a little too long. Oh my god. Would they actually hit a 9 problem?
Is J?
Oh my god, that's a first to solve.
Yeah.
That's crazy.
J was the 15-second time limit problem.
That's a huge lead for Urbana-Champaign. I mean, honestly, mad respect. That's such a strong performance. Very dominant, very clean. Look at those. Only 2 incorrect submissions on the contest, including one on problem M, which we feel like incorrect submissions there are like fine. And now very, you like just you stand up, you stand straight, and then you click submit button. And then you open a new problem. And actually, am I crazy? Okay, again, potential gossip. Maybe it's not actually factual information. But at some competitions, may or may not be NAC, you're getting monetary prizes for solutions. And in that sense, Urbana-Champaign is absolutely dominating the field. Good job. I think that's awesome. Which team has most LGMs? Carnegie Mellon, right? Is it?
So I think in terms of most LGMs, so I think there were only 2 current LGMs here at the contest.
Conqueror.
So we have Dilhan from UIUC, Conqueror of Tourist, and then we also have who is this?
We would like to extend our
CMU?
Thanks to everyone in the community who contributed to this Codeforces post. Which features, as usual, teams going to the 2025 ICPC North America Championship. Go and upvote. Nick will get some nice rating points for that. And there you can see that, we have plenty diverse set of contestants, but CMU and Illinois to Urbana-Champaign as the only ones who have LGMs.
Yeah, so CMU has so Fizzy David was formerly LGM. So I guess if you want a tie break, CMU has 1 point epsilon LGMs, whereas UIUC I guess technically only has 1. But just because you're LGM doesn't mean you're automatically guaranteed to go to World Finals. Earlier today I was chatting with, or not earlier today, last night I was talking with some folks from UCLA, and they were talking about how they had an LGM on their team who failed to make it out of regionals. And the reason is because the reason that was given was that the regional contest was tested more like implementation skill than like the algorithmic problem solving side. And this is a big difference between, say, IOI and ICPC. So like
you
IOI,
need to be good at both.
IOI you need to be especially good at algorithms, but also like implementation does come up. in ICPC, implementation skill matters like quite a lot. Like definitely more so implementation, and so like to get to LGM on Codeforces is definitely a lot of speed required, and a lot of like speed is not necessarily the same as like implementation. Like Codeforces doesn't give you like 300 line parsing problems ever. Like that is a thing that all our Blitz participants are now discovering.
In a very rough way.
But you know, it's just like so like Codeforces rating doesn't capture that ability, and the LGMs on Codeforces are not practicing on 300 line parsing problems. But people who are practicing on parsing problems, I think they mentioned that like one of the people on the team that did make it to NAC, like they did a lot of Advent of Code. And Advent of Code is in some sense like a sort of like an orthogonal skill set. Like there is a little bit of like algorithmic solving, but there is a ton of parsing. Advent of Code is especially well known for having a lot of like different sorts of parsing. And so because like those individuals were training like those specific skills, they actually like hit like an interesting win condition. Like they focused implementation, and so that's why they were able to get out of their regional, and frankly like they deserve it. Like they knew what the regional was like infamous for, and then they like practiced for that, and so at the end of the day, like if you're practicing for the wrong contest and you don't do well, the outcome just like necessarily follows. So good on the actual NAC team for sort of practicing like for what they expected the set to be.
I strongly disagree.
That's good.
Like,
that
stop
means
locally optimizing for a single contest. Just get good. Actually get good. Don't try to, be faster than AI agent in solving Advent of Code in under 3 minutes. Stop writing library code to read integers from a string. Like, that's bullshit. You need to just be good at problem solving. There is no reason to try and make sure that you're excellent at coming up with complicated solutions and ideas. But then figure out that you're actually bad and can't type thing that's longer than 200 lines. That's not what we're about. Like, that's the beauty of ICPC. You know that at the World Finals, the problem set that awaits you will be so diverse, will be culturally unique in a way that, like, you just need to get good.
Maybe.
And that's why my hot take is first place at NAC is, like, awesome and stuff, but it's not really the goal. The goal is to really perform well, to feel like you are not stressed or something, to match your skill set. Let's take a small peek at some of the teams that had a little more of a rougher start, I'd say, famously last year's MIT, obviously, at the World Finals. Go look at them. But here, like, timeline of even current MIT team at NAC kind of says, ooh, first 40 minutes were, like, not great. But then it was fine. Everything was fixed. Team got back on track. And that's a skill that it makes sense to build. Which, sure, to build your resistance to tilt, playing Blitz is great. Solving problems that need to be solved in a minimum amount of time is awesome because you build resistance, because you know for a fact that you can come back no matter what. But, like, optimizing for a team of 3, making sure that every topic is covered exactly by one person so you can try harder and improve in your own topics. What you gonna do when your 2 attempts are gone? Nah, I'm not having this. You can tell Lydia is right in chat, or you can say Nick is right in chat. But in the meantime, we'll take a glance at the scoreboard, because Carnegie Mellon University just broke through. They got their 8th problem, and their penalty time is better than MIT's. Why their penalty time is better than MIT's? That's what I just explained, because MIT had very rough first 30 minutes, and CMU will have that edge over them for just a little bit more. Easy, right?
But-
That's like if you can be calm, collected, and start the contest right away, you'll have that advantage over those who need another 30 minutes to get yourself together. Hey.
I see Lydia is making it impossible for me to do the work that I have been assigned. She keeps ruining my pre-prepared lines, so they will just vanish and be regurgitated at some point. But for those in the know, like if you have to ask whether she's right or whether I'm right, technically she's my boss, so she's right. So that's the correct answer.
No, hold up. Everyone's allowed of their own opinion, even if it's incorrect. You
Right.
see?
So to summarize what she just said, she's right, and that's the end of that. I think we have a guest up and coming, so let's
Awesome. The next guest that you'll see in the studio is not just a very well-known competitive programmer in our community, but also one of the people who currently wears the most in color at this NAC. And I'll show you some teams in our spectator area so you can have a guess on which color that t-shirt he has. And we'll go on a short break. Maybe. Probably. No. Let's go on.
Like all great journeys, it started with one person's vision and the drive to make it real. Empowering brilliant minds who turned ambition into action. We questioned accepted wisdom. We embraced challenge. And together, we changed the world of finance. Twice. Today, we are the most profitable hedge fund manager of all time. And as the next generation capital markets firm, we reimagine markets every day. But for all that we've accomplished, we've never lost the courage to begin again. Because when we act boldly and build together, we transform the impossible into the seemingly inevitable. Ideas are born, but impact is made. And it's made here.
Welcome back. We have Karoni here. No, sorry. We were supposed to have Karoni. Now we have Kusaga. I'm sorry, Kusaga.
Okay, I was surprised, yeah.
Kusaga and Karoni are teaming up right now on...
on the mirror contest. So we were trying to I just came here in the morning and I saw Crony and I was like, hey, you want to do a mirror contest? And he was like, yes. So we're pretty chill about it, not trying to be so serious. But then we solved a lot of problems and then we got serious about it. So now Crony is solving C. So that's why. So and there's nothing to do for me because I guess C will take quite a long time. So the meantime, I'm just doing some interview as we are supposed to. Yeah.
Yes. Lydia, do you know if we have a link to the standings for the mirror? No. Okay, that's fine. In the meantime, we will talk about some of the problems that Kusaga's been solving. Let's start with problem E. We were talking about this earlier, and there was a lot of interest in it.
Mm-hmm.
So we're going to bring up our little whiteboard here. The idea behind the problem, as I'm sure a lot of folks know, but I'll explain very briefly, is you have two arrays. One of them is a pretty simple array. So let's say you have 1, 0, 5, and then 7. And then the other array, this is the human's performance on 4 tests. And then you have the AI's performance, which might be 2, 0, 3, 1. And you need to pick a sequence of these elements that's continuous. And the AI will then swap the best human score, the best human minus AI score. So in this case, it would be these two. And now the AI will have 6 points for this. So the AI gets 6. And then you get 2 points for winning this. And then you both get 0 points because you tied for this first one. And you want to see how many ranges you can pick where your score will be at least k times the AI score, where k is a constant that you're given. It's between 1 and 1,000 or something.
Right.
So the first observation that we made is that dealing with 2 arrays is a little complicated. It's easier if we turn these into 1 arrays, which is just the difference array.
Right.
So for this example, the thing we'll consider is just -1, 0, 2, 6. and then we can ignore thinking about these. And now the operation the AI does is it gets to make one of these things negative if it wants to.
Right.
Okay. So now we have this array, and we want to know how many ranges can we pick where the sum of the positive numbers is k times the sum
of the negative numbers as an absolute value. Yeah.
And then there's also the computer gets to flip one thing.
Yeah, right. Yeah.
Okay. So this is where we got. I feel like this is probably correct.
Yeah, that's correct. Yeah.
The next thing that I would love to get rid of, the complicated piece of the problem, is that you have this like times k multiple.
Yeah.
Is there a way that you're able to get rid of that, or is that something you have to really work around?
Well, in my solution, I did a couple of abstraction that does get rid of this k thing. I mean, not entirely, but like okay. So I'll just get back to I'll just get to it. So for the negative numbers, so I have this like difference score where like for each positive number, you just take it as is. For every like negative number, you take it multiplied with minus k.
Oh, I see. So for -1, if let's say k equals 2 here.
Yeah.
So for the -1, because you need to score 2 times what the AI does, you just multiply all the negatives by 2.
Yeah, exactly.
And then this is just -2, and now you just need a sum of 0 or more.
Yeah, but not exactly when you're not doing this flipping thing, then we are just finding a sum of segments that then we are finding the number of segments that sum to 0 or more than that. But here, like, you can like flip something, which could be a little bit tricky. But for me, the idea was like this. So if you fix a subsegment, what the AI will do is just to like flip the one that the humans are scoring the best. So you take the one that humans are scoring the best, which could be like, I think here is 6, right?
Yeah.
Yeah, here's 6. So the AI will take 6. Sure. In this subsegment, the AI will take 6, and then it will turn it into their own advantage by multiplying by minus k. So then the advantage the human had disappeared in here is k plus 1 times the 6, which is 3 times 6. So basically, if you just reduce it, like so what you have is like you want to have a segment that sums to at least k plus 1 times the maximum that appears in the array.
This is like 3k because the human lost the 6, the AI got 2 6s.
Yeah, exactly.
So really, it's like an 18 penalty.
Yeah, right. Yeah.
I see. Okay.
So now here, like what we are trying to compute is like to count the number of subarrays that are like in a sense, like you're trying to count a subarray that its sum is greater than a maximum. But the array that you're taking the sum and the maximums are different, kind of like
maximum times 3, right?
Yeah, maximum times 3 here. But here you have to be careful that because like if it might not be that important, but like for here the maximum you're taking is only taken for the ones that the humans are taking advantage of. Like for example, if everything is negative, then the maximum is 0 here. So it's a little bit different. I'm not sure whether you have to use a different array, but I did use a different array. So I have an array where one of them has this sum of like different scores, as I said earlier, like -2, 0, 2, 6, or stuff like that. And there's another array where I have this advantage that could be taken by the AI in when it flips an element. So here, like,
and that would be like you make all of the -1, 0.
Yeah, so here, like, given this array like 2, 0, 2, 6, I guess the array that I'm taking the maximum is like 0, 0, and -6.
4. Oh, -6, and then
negative
18.
Yeah, but I actually take the positive because we're doing the maximum here. So I'll do 6 and like 18. So yeah, so
this is like how much advantage you get.
Yeah, exactly. Yeah.
And
so
this is the human score.
Yeah. So now this is basic idea, and it gets a little trickier from here where I use some little bit of an advanced technique. So here the technique I'll use is the Cartesian tree, which
oh boy. Okay.
Okay. Maybe I'm going too fast, but I hope I convinced that this gives a pretty like simple like n square solution, right?
So the n squared would be for every range.
Yeah.
We would look at the sum of that range and the max of that range.
Exactly.
And
Yeah.
check if it works.
Yeah. Right. Yeah.
So now we have to somehow not look at every single range and only
Yeah.
look
Exactly.
at certain ones.
Yeah.
Okay.
Yeah. So here, I'll just say it like so. So you take this maximum array, and what you're doing is a sort of a divide and conquer stuff where you take the maximum over that array, like over this blue array.
Okay.
And you consider all these subsegment that contains this maximum.
Okay.
What here it means like all the subsegments that contain this 18, like really.
Yeah. So,
So
it'd be like this one.
Yeah.
This one. This one, and just this one.
Yeah. Here there's 4 such subsegments. Yeah.
Maybe a
and
more interesting example would be if 18 were somewhere in the middle.
yeah, that would be more better.
So
Yeah. So
we have an 18 here and like a 4 and then like a 0 and a 2.
yeah, something like that. Yeah.
Yeah, these should all be multiples of 3, but whatever.
Yeah.
So you take this, and then so you're interested in ranges that are like this one, this one, this one, and then
there are 6 of
this
them. So
one,
yeah.
this one, this one.
Yeah. Right.
Okay.
Yeah.
And how do we process? Surely we don't process all of them, do we?
Yeah, we have to do all of them, which is not an easy task to begin with, because if you take a middle here, then you have to take like n square like subsegments. So it's still not really efficient. But here the idea is like the maximum is fixed over them. So what I'm trying to do here is to use some data structure. So given that taking the advantage that the maximum is fixed, I'm hoping that these 6 subsegments can be like processed efficiently. But I'm not telling you how to do it. But yeah, I'll get back to that. But basically, I want to find the maximum. I want to enumerate all subsegments that is greater than 18, and then what I want to do is to recursively do the left part and the right part, and to solve the rest of the problem where it does not contain the maximum.
Okay.
Yeah.
So the problem we're trying to solve is like how many of these blue lines that I've drawn have a range sum that's at least positive 18.
Exactly. Yeah.
And in this other array.
Yeah.
And then once we do that, we'll divide and conquer. Okay.
Yeah.
But the runtime for doing this has to be order whichever side is smaller, right? So
Exactly. Yeah.
In this
yeah.
case, we need an order, I guess, 2.
Yeah.
Right. For an 18 solution.
Yeah. Indeed, it is a pretty cool trick. But like, if you do it in the order of like smaller times like log, or like small, like if you do it like, for example, if you do it for like order of like log smaller times log n, you can actually prove that the total time complexity is like n log squared n. This is kind of a like fun argument, like kind of resembles the HLD in this like this recursion tree, which seems pretty like scary, but it, like in a sense like you can think like this: for each element, you're computing the number of it that is considered in these like sub problems. Then for it to be considered, it should be small. So there are like almost like log n number of elements that is contained in like this sub problem. So that gives you a proof of like why is n log squared n.
So is like the approach for doing this, we literally just iterate through everything in the smaller side.
Yeah.
And then we do some query saying like for this to the end,
Yeah.
how many have some at least this thing?
Yeah, exactly. So yeah, for here, like without loss of generality, we will just assume that the element is a little bit closer to the left side, which I think it is, right? Yeah. So we are fixing the left hand point, and for the right hand point, we want to use some data structure to solve the problem. If you write it down, like I think the formula will be like this. So you have a cumulative sum of the right part minus the cumulative sum of the left part that is greater than 18. That is at least 18.
Okay.
Yeah. So if you fix the left side, left side, you want to basically compute the sum of the rights that are like at least like 18 plus the sum left minus 1.
Okay.
Yeah. So this is a range query, which is actually not very easy to deal with. Like I mean this is not just a segment tree, as in like we are just not counting the sum, but we are counting the number of elements that are greater than something, right?
The number of so we'll look at the prefix sum array and we see how many in this range are greater than this.
Yeah, which is by itself not an easy problem, but
like this is what the data structure.
Yeah, this is what the data structure should do. So let's.
But the range though is always a suffix.
That's
right?
not true. That's actually not true because if you're recursing down, you cut up some of them. So this is just like range stuff.
Okay, so in like an LR range.
Yeah, exactly. Yeah. By the way, if you fix the right sum, then it's actually like how many are smaller than something. So it's an inverse problem, but that can be just done in the identical way around. So
I guess so this is true. However, I don't think it matters too much because if we have an LR range, we can just ask the question twice.
Exactly.
Right.
Yeah.
Okay.
Yeah. That trick actually I use it in my code. So yeah, that's kind of helpful.
So I guess to explain that, so to simplify the problem once more, we have a series of elements here, and we want to know in this range how many things are greater than or equal to 18, we'll say. And what we can do is, because having two of these things is a little annoying, we'll say in this range how many greater than or equal to 18, and then in this range, and we'll subtract out this.
Yeah, correct.
From our answer.
Yeah.
Okay.
Yeah, that's correct. Yeah.
All right. So now the problem is simplified to, in an array, and this is a very classic problem, in an array, how many things in some suffix are bigger than a certain element?
Exactly. Yeah.
And
the way I'm gonna try to solve this problem is to
I'm not
using it. That's kind of like I can use it. I can use persistent segment tree to do that, but I really don't have to. The thing is like you can just think about the problem where you're just given an array and just given such type of queries. Then the easiest thing you want to do is probably to do it offline. You want to sort the arrays in the increasing order of this one endpoint of the range, and then you're sweeping it from left. Like if you're doing the suffix, it's sweeping from right to left actually. So if you're sweeping from the right to left, you're trying to add the element, and you want to count the number of like elements that is like in a certain range.
Oh, so we're just gonna be like go from here and then here and then here. And as we go left, we'll maybe add it to like a Fenwick tree or something.
Yeah,
and then we just query how many elements in the Fenwick tree are bigger than 18.
Yeah, right. Yeah.
Okay.
So that's the solution we are trying to use it when we just have this count problem. And here it might be tempting that you want to like respond it online, that you want to just know the count immediately, but you actually don't have to. You can just store these queries in a separate array, and like you can then rewind back, or like after the end of the recursion, then you're trying to figure out the actual number by just sweeping from right to left, which is same in the time complexity manner, but it's faster, and also it's much easier to code.
Okay.
So in that way, the implementation isn't like really too hard actually.
Awesome.
Yeah.
All right. Well, thanks so much. Yeah, that's a wonderful solution.
Yeah. Thank you.
I just called you Corona again. I'm so sorry, Kusaga.
No worries.
All right. Let's take a quick look at the scoreboard. Scoreboard check. UIUC and CMU are both up to 9 problems. MIT following close behind with 8. Chicago with 7. And then U Central Florida has just dropped out of medal range, but they're sitting there with 6, which is double what they were last time I looked. So they're still making progress here. They've got some wrong answers on L. I think in the meantime, it would be awesome if we could view a head-to-head dashboard of UIUC and CMU, the two 9-problem teams. Now, UIUC has gone so fast here that they have an absolutely wonderful penalty point advantage. They're up 200 penalty points, which is hard to overcome at this point unless someone goes absolutely nuts with wrong answers. So CMU basically has to win on problems here. Unfortunately, this is very tiny. Let's take a really close look. Looks like this is G.
The problem G. Okay, yeah.
Is that also G? Are they both on G? E. G. E.
I see.
So UIUC, we're told is on E, and then CMU's on G.
Yeah, this way I think UI usually has an advantage because E I think is one of the like easier side of the problem that UI usually can do. So I guess they can do it pretty quickly.
And E was what we just talked about.
Yeah, exactly. Yeah.
So none of that is something that is prohibitively difficult. There's just a lot of steps, but each of them are.
Yeah, exactly. Yeah. G, I think I have an idea, which I'm not sure. I think if I go back there, I'll probably try G.
Go think about it, but too much to do live.
Yeah. That's right. Yeah.
And then right now, my understanding was for the mirror, C and M were the only two that USA 1 had not yet solved. Both of these teams have gotten M, which is impressive. I think there's probably some agreement then that C is the hardest of the set. So it's good that neither of them are working on that. Lydia, would you mind if we take a look at UCF here just to see how they're doing? UCF's my home team.
Yeah, cool.
So I'm kind of a little
and we are at the UCF right now. So
we're at UCF, the host university. Exactly.
Yeah.
We've got some implementation here with some C++ macros.
Looks like problem F, it seems.
Yeah, looks like F.
Yeah.
What was F? Was F a difficult one? Misplaced
F, I would say it's easier than E, actually.
Okay. Do you want to talk about it real quick?
Oh, yeah, sure. I solved that problem in the mirror, so I can talk about it. Yeah.
Let's take a look at the problem set. Sorry, let me just make sure we're not going to be interrupted here. Okay. Sam, Jerry, I think, is coming next. Jerry? Do you want to get Jerry ready? Jerry, okay. Thank you. We'll finish up this one, and then we'll let you get back to the set.
No problem. We're good. Yeah.
All right. So this is Mob Grinder. Let's take a look at the problem. This is E. We want F. Let's make it a little bit bigger for people to be able to read. Okay. In a certain popular video game, probably Minecraft, one can build a structure called a mob grinder. A mob grinder consists of N by M rectangular grids of tiles. Monsters known as mobs appear continuously at random places in the grid. The goal of a mob grinder is to move all of the monsters to the top right tile of the grid, no matter where they originally appear. To accomplish this goal, each tile on the has a conveyor belt, like water, with a specific direction, up, left, right, or down. A monster on the conveyor belt gets moved in the direction of that tile. Your job is to place conveyor belts on each tile so that no matter where a monster appears on the grid, it will get moved to the top right corner after a finite amount of time without ever leaving the bounds of the grid. However, there's a limit on how many conveyor belts you can use of each orientation. Your final design must have a certain number of each type. Exactly. You're asked to design multiple mob grinders, each with a specification for how many conveyor belts of each type you're allowed to use. Design a valid mob grinder that meets each specification if possible. Okay, this is a nice visual problem. So, to summarize, you have a rectangle here. That's not a rectangle. You've got a rectangle. And let's make it 3 by 2. So you're trying to get everything into the top right, they said?
Yeah.
Okay, so this is your target. And do you put a tile there or no?
I do not put a tile in the top.
No tile
top
in the
right.
top right.
Yeah.
Okay. Yeah. So one way of doing it, for example, could be you could go up, right, down, left, up. But you could also replace this one here with like a right. Okay.
If your count allows.
Yeah, if your count allows. Yeah. And you're given the counts for each of them. So you're given the number of rights, ups, and downs. Okay. The first observation is, I guess there are two things that you have to do.
Yeah.
You have to not ever hit anything outside of the grid. So you can't hit any of these squares.
Correct.
And you can't create a cycle.
Correct, yeah.
And if you do those two things, you should be okay.
Yeah, right, yeah.
Because everything, ultimately, it's going to end up, like, it won't be in a cycle, and it's going to have to end up at the only space here.
Yeah, in other words, we have to just create a tree that is, like, rooted over there, and, like it's directed towards the root, yeah.
Yeah, okay.
Yeah.
So it sounds to me, how big are the bounds? Kind of big, but it sounds to me like it's promising to be a flow problem, maybe? Oh, but then you have cycles. Cycles flow doesn't handle.
Yeah.
Do you have to print the answer?
I have to print the answer. Like, Yeah, this one I have to print the answer.
What is just you put things in each spot?
Yeah, I just put like URDL in the grid and like just print.
Okay, so my initial observation was that each cell has a series of options.
Yeah.
And you have a count for each direction. So you have to like match them with directions. So you have your 4 directions here, and then you have your cells here, and then maybe this is the top left cell.
Yeah.
So it can go right or down. This is gonna run into issues though, because you can do a matching. You can match these with these, but you can have a cycle.
Yeah.
And then if you have a cycle, you're in trouble. Okay.
Yeah.
So maybe let's not do that, and let's try something else.
Actually, I would recommend doing something simpler. Actually, this one, the limit is like very linear, like maybe like even like deceptively like linear, like lenient in a way that to like overcomplicate or like stuff. But this one actually have a very like clean like linear time solution.
So then my next solution, or my next idea, would be maybe something greedy, because the constraints we have are very predictable.
Yeah.
We know the only things that can't go down are these ones here. So
That's
if we're
correct,
able to fill these up with anything that isn't down, then down we can just like put in our piggy bank and use anytime we need it.
Yeah.
As long as we don't create a cycle.
Yeah.
Again.
Yeah.
So, okay, let me think. Maybe there's just some simple construction.
Or else the way I want to like the way I did tackle this problem is to first like tell when it's possible or impossible. There's the impossible case is kind of easy to distinguish, like kind of simple to distinguish. And could you figure out how to see if the answer is like possible or not?
Well, let's see. So, how many rights do you need? You're always going to need at least 2 rights. There's no way of doing it with less than 2 rights.
Otherwise
Greater than or
the
equal to 2
leftmost cell
rights.
cannot go there. Yeah.
Okay, yeah.
Yeah.
You're going to need at least 1 up. 1 up. This could be right or up, left. Could it be, so how many lefts do we need? You don't need any lefts.
Yeah. If you have like all rights and like just that much of a left, then we can construct it. Also same goes for the down thing. So
Yeah, you don't need any
we
downs.
don't actually like need them. Yeah.
I feel like this isn't necessarily possible though, because like there's more constraints that I haven't. Because you can't, if you have 2 rights, 2 lefts, and an up.
Yeah.
You can't do this.
Say it again.
If you have 2 rights, 2 lefts, and 1 up.
Oh, I don't think so. I think you can construct that.
How would you
could
do
you
that?
figure out?
Your up has to be here, right? Oh no, it doesn't.
No, I put the up in
up
that
here,
position and then
right.
yeah, exactly. Yeah.
Left.
Yeah.
Oh. So is that it? Is it just
Actually, yeah, I just talked to you about the like necessary and a sufficient condition. The necessary one, like we explained why it is necessary, but why is it sufficient? That actually you have to prove it with the algorithm that prints the grid.
Oh, I think I see why.
Yeah.
So you can move this over, and then this will handle lefts and rights, and you can funnel everything in.
Oh yeah, exactly. Yeah. That's almost how you do it. Yeah.
So now we can move, and we can do this for every row. So we can handle any number of rights that we need.
Yeah.
And then, all right, we'll be out of here in just a sec. And then the only other question is handling downs.
Yeah.
I guess you can move this down, and then you can handle ups and downs here by pointing into it. But now there's like this little conflict about like, okay,
yeah,
where do you draw that line?
Yeah. Do you want me to spoil it?
Yeah, can you spoil it for us?
So if you start from the like lower left corner.
Okay.
So the thing is we have like n-1 right side and we have like n-1 like upside like arrows.
I'm gonna make this grid a little bigger just for us.
So the thing is you can always draw a path from this one extreme to another.
Okay, we can always draw a path from one extreme to another.
Yeah,
like
this lower left to the upper right.
Yeah.
So we can always draw a path, and we can actually draw any path we want. Cause the arrows, we have just sufficient number of arrows.
First to solve. MIT, first to solve problem C. Ooh, what we had thought was the hardest problem in the set. They've gotten it, and that puts them in 3rd, I imagine?
Yeah.
In 3rd, yeah.
It's 3rd, yeah.
In 3rd on penalty.
Yeah, I'm proud. Yeah, for sure. Yeah.
Welcome.
Yeah,
your team.
thank you. Yeah.
What are they doing next? I or L?
I think it's I. What is the
clearly
I?
have L.
I is the geometry one, right? Like
Is
this
that
kind of a
the up and
geometry.
down one?
It's the geometry.
Yeah. Okay, I thought it's geometry, so then I guess my intuition is correct.
Is
yeah.
that the geometry dash one?
Not the geometry dash, but like
polygon.
yeah.
Different polygon.
Yeah.
All right, we haven't looked at that.
Yeah.
All right, sounds good. Well, really quick, let's finish this and then we will swap out. So you can draw any path you want.
Yeah. Yeah.
And it just has to go up and into the right.
Yeah, it
somehow?
just have to go up and right. And the thing is, you're just putting in the left side, you're putting all the like down and rights, and in the right side, you're putting all the lefts and ups. Then you can just put it arbitrarily, as long as your area allows.
Oh, like this? You said? Sorry, what did you say? In the left
so
side?
So you divide it like that path from the lower left to the upper right will divide the grid. You know.
Oh, so we just pick this path.
Yeah, and you just pick that path, and like in the right side, you're just putting all the up and lefts, and like you can just put it like anyhow you want.
And it'll always work.
Yeah, and then in the other side, you put all the like right and down, and as long as you draw the path correctly so that the count fits, then everything
so
just
you
works.
can move it like that if you need more left.
Yeah, exactly. Yeah, and then like to see why it works, then if you just start anywhere, it will just hit the path sometimes. So
wonderful.
Yeah, which is pretty. Yeah, I like this problem. It's pretty cool. Yeah.
Awesome. Yeah, it is.
Yeah.
All right. Well, thanks so much, Kusaga.
Yeah,
we appreciate having you on. We'll be right back after this quick break.
These competitions help to create and empower a new wave of talents and leaders in digital technology, and they help to grow a new generation of future programmers.
The competitive programming community is special to me just because I grew up with it. I started doing this when I was 12, and it basically kickstarted my whole career.
I think it's important for Jane Street to be supporters of ICPC community because this community is very important for development of many young people who just started their journey with software engineering.
What makes ICPC special to me is that people from many different countries just come together to one place to compete against each other and create a community.
Many Jane Streeters have been involved in the same competitions you're here to take part in. I met some of my closest friends through these competitions, and to this day I still enjoy solving problems with them.
I have been competing in ICPC for 10 years. It was what introduced me to the world of programming, to the world of problem solving.
My experience at ICPC prepared me for my role at Jane Street, mostly in terms of being able to formulate my ideas clearly and implement them quickly.
I use a lot of programming skills I learned during my years in ICPC competitions.
I think Jane Street is kind of similar to ICPC in a sense that we solve a lot of complex and interesting problems in a very quick matter. And I think this experience led to me being successful in my career and having a lot of expertise in what I do.
This is how I've met a lot of friends in high school and in university. We participated in competitions, we share a passion for competitive programming, and now we work together at Jane Street.
You're surrounded by people who care about the same things as you. If I could give advice to someone competing today, I would say make as many connections as you can.
The most important part is to find your friends, gain knowledge, and have fun.
And welcome back to the 2025 ICPC North America Championship livestream. We have yet another guest with us. If you could please introduce yourself.
Yeah. Hi, my name is Jerry. I am one of the judges for this contest. Yeah.
Yeah, and if you know my name, then keep it a secret. So, what does judging entail at the NAC?
So, I think judging is 4 different phases, with 3 of the 4 sort of happening before the actual contest even happens. The first phase being sort of winnowing down this pool of problems that we have and tagging them with like different difficulties and like a subjective quality score. And then from those scores, usually the head judge will pick out a pool of problems to be prepared, which will be slightly larger than the size of the problem set that we want in case we want like backup problems. And then the second phase is taking that smaller pool, and then we'll write solutions, write test data, and just make sure that they are ready to be used. And then the third phase is just verifying that the problems are correct by making sure that we cover enough language groups to follow the technical notes, have enough independent solves, and also have wrong answers to make sure that the test data is strong. And then like the last phase is during the contest, where we just sit in the back room and look at all of the submissions pour in.
So you've been in the back room for like 3+ hours now. What's it like sitting in the back room, like watching these submissions come in? Like how do you personally feel about that?
I think it is very fun seeing the participants try to solve the questions. Yeah, a lot of the judges have like internal bets on like who's gonna solve which problem first, or like, yeah, bets on what problems are the easiest to which ones are the hardest. And many times the participants exceed our expectations in many different ways.
So right now, if we look at the full scoreboard, we can see that almost every team has solved problem K. So was it in expectation that problem K was like the easiest problem in this contest?
Yes, we believe that it was the easiest. I think on our prediction spreadsheet, all but one judge put that every team would solve problem K.
Yeah, I think right now we have 51 solves, so just one holdout, and hopefully they'll figure it out. What has been the biggest surprise so far in the back room?
Oh, there are so many. Where do I start? I think problem E getting solved before the 90-minute mark. That's humans vs AI. Was very surprising to us, because we pinned it as one of the harder questions of the set. And then we also pinned H as the second easiest in the set, with predicting that basically every team would solve it too. But I don't think it's quite there yet.
Looking at the statistics, so problem H currently has, I believe it's 30 solves, and then problem A has 34. I know earlier on we were remarking that problem A wasn't, it was a candidate for like in the like easiest like 5 or so problems, but not second easiest. Why did the judges think that maybe H would be easier than A?
I think with A, it has a lot of mathematical parsing, and that sort of scares away some of the participants, especially I think participants that don't have someone that is as strong at math. And then H we thought was a fairly easy to see greedy, at least with the bounds provided. It sort of hinted towards a greedy solution, and we did not think it would be as hard as trying to parse through the mathematical notation on like your first pass through the problem set, where you're just like scanning for the easiest problems to solve first.
So when the judges are sort of like curating the problems and trying to assemble the problem set, early in the broadcast we were talking about like the perfect problem set and how one of the goals is like, you know, no team will solve all of the problems. So when the judges were constructing this set, did they have any expectations around, do they think like how many teams the winning team would, or how many problems the winning team would end up solving?
I don't think we had that in mind when we were constructing the set. I think we more so focused on selecting problems that we thought were of the highest quality, and also diversified the topics. Like I think in our problem pool, we had multiple problems that utilize the same technique, but we only picked one of them because we didn't want to have like multiple of the same ideas in the same problem set. Yeah.
Is there like a favorite idea that doesn't appear in the set?
Huh. Am I allowed to say? We did have one problem. Our smaller problem pool of problems we prepared was of size 14. So there's one problem that did not make it here. And that topic is also not duplicated in any of these other problems. So I guess that is one topic that does not really appear.
Yeah, let's keep that problem a secret because maybe it'll appear at NAC 2026, and it's always good to have backup problems. Sometimes you realize the night before the contest that the test data you prepared are incorrect, and maybe if you don't have a backup, then you're short one problem. Otherwise, you can just slot in the backup. What's the most rewarding, or like what do you find the most fun about being a judge?
I think the most fun part is seeing the participants enjoy the problems, or at least I hope they're enjoying the problems. But yeah, being able to see them solve them and then also see them discuss them afterwards is like a very rewarding part.
Here we have UIUC. UIUC has solved problem E, so now they are back to being uniquely on top by problem solved. So they have 10 problems solved with 953 penalty minutes. And so they are left with problems C, G, and I. Out of these 3 problems specifically, C, G, and I, which one do you think is the hardest?
I think they're hard for different reasons. C is a very implementation-heavy problem that has many places to make bugs. I think I had to fix my solution quite a few times just from adding test data for writing a solution for that problem. I think would be the easiest one once you see the mathematical intuition to what you're supposed to do for that problem. And then, yeah, G falls somewhere in the middle, I would say.
Yeah, looking at the actual like submission, so MIT is the only team to have submitted and solved problem C. No teams have submitted to problem G, and we have Purdue. They made one submission to problem I, but it was incorrect. I think if we look at the public or at the online mirror, we can see that Team USA won. So they have solved problems G and I, but they have 2 incorrect attempts on problem C, and they also now have 1 incorrect attempt on problem M. So I guess if you ask USA 1, they would probably say that C is hardest, and G and I are not that hard. But if C is just implementation, then actually there's kind of a funny story here. So I think everyone in the competitive programming community knows Andrew, Gennady, and Kevin. And so they each gave presentations. Andrew gave a presentation on monotonicity and DP. Kevin gave a lecture on constructive problems. And Gennady gave sort of a meta lecture on we call it Tips and Tricks V4 because he's already done multiple other Tips and Tricks lectures. And in Gennady's lecture, he specifically was like, one of the tips is like, don't make bugs. Like seriously, just don't make bugs. And I guess he should really internalize that. And I'm betting he's working on problem C. It definitely feels like a problem that he will be working on. MIT definitely showing their prowess. No wrong attempts on problem C. So the problem C has this like this interactive component of like playing this game. Was a testing tool provided for the teams, or are they doing it on their own?
Yeah, I think we did provide a testing tool. But if I recall correctly, it is a Python script that calls a .exc, because we were slightly concerned about participants trying to disassemble or like look into the code if we provided a Python interactor. So disassembling it is a lot harder and a lot more tedious than just coding up the actual solution. But the interactor doesn't make any smart moves. It just picks a random move and then verifies that your move is actually, or the interaction is actually correct.
And I assume it is the case that is the randomly moving, is that actually a good strategy, or is it just awful?
That is an awful strategy in most cases.
Okay, yes. So like it's a good sanity check to make sure that your program is doing like the actual interaction. But if you don't actually have the correct strategy, then it doesn't actually matter.
Yes.
And I assume that the actual like the judge interactor will like, if it can immediately punish you, it will.
So we actually have like 2 different modes it runs in. One does play optimally and will punish you for every mistake that you like make along the way, and the other plays random moves in case there is a bug in your solution that only happens when the judge doesn't play optimally.
Okay. And I'm assuming that the judges actually wrote like an incorrect solution, but it works if the judge plays optimally?
Yeah, funnily enough, when the judge plays optimally, okay, so there's like multiple optimal moves that you can make from like a specific state, but if you always choose the first one that you encounter in like some order, then outputting no always gets you a win as the runner if you can reconstruct the path. Like, that's just a bug, or not really a bug, or just some property of the game. So yeah, we did have that solution, and it popped up from when I wrote a solution that had a spelling error inside of yes, but then it doesn't actually get wrong answer because it always prints no for the runner interactor.
That is certainly one of the more unique bugs that I have run into or heard about in my time helping judge and commentate ICPC contests. But I'm glad that you're actually doing like your due diligence and providing like actually you're providing actually strong feedback, and it's interesting that you're actually able to catch this. Is it actually the case that like so is the random interactor in this case, is it like random and then it tries to punish you, or is it just like random like throughout?
It's just fully random.
I see.
Yes.
And so this is able to actually catch like some like weird subcategory that the optimal one like doesn't. So playing suboptimal, like, so it actually catches like this like weird thing where or like, I guess what I'm saying is it is possible to play optimally against the optimal strategy, but against something random, you might actually do something that's just completely incorrect, and that would be
yes.
Okay.
Like, for example, maybe the random interactor is the runner, and as the trapper, the runner moves into a square that gets it trapped, but then you accidentally continue in your interaction by not like correctly reading the right output.
Got it.
And then you like send extra output to the judge, which is taken as being a wrong answer.
I see. For some contests, we're gonna pivot away from problem C specifically. For some contests, like to release this sort of like cold gulf statistic of like what is the minimum number of lines of code the judges needed to write to be able to solve every problem. Do you know of that metric? Do you have that metric handily available? Roughly?
I do not.
If you had to roughly estimate how many lines of code, is it like 500, 600, or like?
For a solution or for?
Oh, we have first to solve from Purdue on problem I. So that means problem I is 12th first to solve.
Yes.
Where we have Purdue up on screen, shaking their head right after their AC, the typical reaction. Maybe they don't even know that they've gotten AC yet. Oh, no, I think they know. Somehow, maybe. It is a little bit unclear. But problem I has been solved, and we're almost at the perfect contest criterion where if problem G gets a solve, then every problem will be solved, and that would be pretty cool. Did the judges make a bet on like which problem would be last to be first to solved?
Unfortunately, we did not. But I think by our solved statistics, we thought it would be problem J. We thought only 2 teams would solve that, which I think is what we're at right now.
Yeah, so right now for problem J, we have University of Illinois Urbana-Champaign and UCF. Those are the only 2. So this is definitely one of the most interesting scoreboards I've seen in a long while. We keep talking about like the columns of green, and if you look at the scoreboard, you don't actually see columns of green. You see like you just see these like green like pieces here and there, and it's really nice to see. It allows for like some skill expression. Was that like intentional in like from the problem selection, like trying to select a lot of problems that were like approximately the same difficulty, and then letting the teams kind of figure out what they wanted to solve?
I think this might have just been a happy mistake, because I think even during the problem writing process or like preparing the problems, there were a few that changed in their statements and thus also changed in their difficulty. And I think it's just the fact that I think this year's NAC set is a lot more compressed in its difficulty, in that the lower end is higher than it was, say, last year, but also the higher end is lower than it was last year. So there's a lot more problems on the upper side that are approachable to a larger pool of teams, but maybe not all of the problems are approachable to all teams, and so they're able to pick what they're good at and solve those.
Did the judges have a prediction for what they think the World Finals qualification threshold would be?
We did not, but we were watching the stream at the 90-minute mark, and we saw you guys talking about the 8 question limit. We thought that was a bit high.
Yeah, so on my lunch break, I was walking around, and I was talking to like the experienced coaches in the spectator area to get their opinions on what they think, and the vast majority of them are like, yeah, 8 is definitely sufficient, but definitely not necessary. And I think there's the debate right now is going to be a very fast 6 or a not very slow 7, and I think I am when I was last there, like maybe like an hour ago, I think I was saying like, oh, I have confidence that like NA will execute well, and it'll be a not that slow 7 as opposed to like a really fast 7. I think other folks are a little bit more hesitant, and they're like, you know, it's but it's a big question mark, right? Like the fast 6 versus the 7. Is there a reason that this seems to consistently be the threshold in your view? Like 6-7 border-ish?
That is a good question. I don't know if there is too much of a reason for this. I feel like we just try and have a nice smooth difficulty curve, and it just somehow always happens that most teams that do make World Finals just solve like the first half or the larger first half of the problem set, which, because we have 13 problems, is 6 or 7 most of the time.
Yeah, it's I feel that like I think a lot of the times like the median of the solve distribution ends up being somewhere around median solve count. UIUC has we have a nice stat, which is the number of character producing keystrokes so far, and UIUC has been keeping it up quite a bit, but if I'm reading this correctly, it's saying that the count actually dropped like dramatically in the last like 5-ish minutes. Is that, or am I misreading? Okay, it's not. Okay, so this isn't actually a real-time update. So everything after the red is not strictly true. But yeah, UIUC is definitely sort of typing quite a bit. If we can get the same count for CMU, actually, if we get them side by side, that would be. Yeah. So CMU is also like a little. There's like some consistency here. And then what? MIT? Is MIT coming up? So yeah, so at the top here we have UIUC, CMU, and MIT are definitely sort of a step above like the remaining teams. Did the judges consider any? Did they consider these teams when constructing the problem set, or did they just like kind of construct it and be like, eh?
I think we just constructed it. There were some worries on the walk to the contest hall that we would have multiple AKs or multiple teams that would solve all the problems. But I think as the contest went on, maybe I'm too premature in saying this, but it seems sort of safe that maybe we won't get any AKs, but knock on wood.
Yeah, with the pace that UIUC is going at, I think that there is a bit of an, like, I think the chances of them actually solving everything is, it's non-zero. I don't know exactly how high it is because we haven't seen a solve on G. But we do have some like rough estimates. So for example, we can see that MIT probably took 40 minutes to solve C, or to maybe type C.
Yeah.
Purdue took also like, let's say 40 minutes to type I. But they probably already like roughly had the solution or something, so the implementation is factored in. So let's say that UIUC also takes 40 minutes to type C and I. Right now we're at the 3 hour and 35 minute mark. So if they take 40 minutes on each of those, then well, they have 85 minutes left. So that's not enough time. Of course, we do know that one of the team members on UIC codes in Python, and when you're typing Python, you do have a little bit of a implementation speed advantage because your code is usually shorter. So you know, if it shrinks them down to like 30 minutes, and each problem takes like 30 minutes to type, then you know suddenly it looks a little bit more feasible. But you know. We're going to be held in suspense because at the 4 hour mark, we're going to come up on a scoreboard freeze. But we'll talk about that when we get there.
Yeah, I think the likelihood might actually be higher. Just the code for I is maybe 10 lines or like 13 lines maybe. Most of it is in the thinking. So they could code that in like 5 minutes if they have the solution thought of. Which because they haven't submitted, I don't think they have it yet.
Yeah. Roughly, for problem C, do you know roughly how many lines the implementation is? Is it like 100, 200?
Yeah, I want to say my solution is at least 200 lines. But I also don't think I did things the most optimal way by separating the runner and the trapper into two different if statement blocks.
And then what about for G? Like, what's the... I haven't actually looked at G.
Yeah, I think G is just a lot of graph theory. The implementation is maybe 70 lines, so it's not too bad. I think there are deep rabbit holes that you can fall into for problem G, in which your implementation will maybe balloon up to like 300 lines, maybe. There's like a very ugly way to go around solving G, which contestants might fall into.
Yeah. As we have the scoreboard sort of loaded up here, we can see that teams are very like steadily climbing up to like 6 problems solved. So we currently have 14 teams of at least 6 problems solved. Earlier, we heard that Lydia estimated that there could be around maybe 16 slots. So, you know, at the 3.5 hour mark, the rank 16 team has 5 problems solved. So if let's say there were 16 slots, then we would need these teams to solve like 2. We would need at least 2 of the teams with 5 to solve like 2 problems, and then we would need each of the teams at 6 to solve like 1 extra one. So the 6 to 7 boundary is definitely looks like somewhere that we're targeting. But it's also, is it clear, like, I guess it is a little bit clear, like, which of these problems are, like, the most accessible, right? It looks like it's A, B, D, F, H, K, L.
Yeah.
And if it's, like, you solve all of them, like, if you solve all of them quickly, you definitely get in. If you solve them all, like, kind of slowly, like, maybe not. Would you say that these 7 problems sort of constitute, like, the easy half, so to speak?
Yes. And the judges had misestimated M, so that would also be part of like maybe the easy half. I don't know which problem it would swap out, but we definitely thought M was like a lot easier than it is.
Is there a specific reason for that?
We thought that people would try and be Chica and just run and just like submit a brute force, right? Like if you run the brute force on some cases, you can sort of intuit like the worst case like input that you can get, and then from that you can sort of extrapolate when you need to stop your brute force in order to like start this smarter method. and we thought that more teams would be trying those brute force solutions and try and see the pattern. But I guess that is a bit hard to do.
I think, yeah. So for a bit of context here, I did talk about it a little bit, but not actually like fully explain. I gave a lecture where I talked about like hacking weak test data and like choosing problems, and I listed out a bunch of problems that were known to be weak in the past, and like what the intended solution was and the technique that you would use to actually cheese the problem and get the AC. And so one fairly common technique is to actually just like write the brute force and then like optimize it a bunch. And so in this case, like for problem M, like that brute force part is like the beginning of the solution. It's certainly, it's like a necessary component of it. But then after that point, you have to do you definitely have to do like some like work.
Yeah.
And it's not necessarily as easy as like you just write the brute force and then you optimize it. Like I think you have to it's expected that you make some observations and then like you can make it actually be fast enough. And I guess you could have this phenomenon where you kind of like maybe, or like there is one phenomenon where you just like keep implementing optimizations and eventually you implement enough of them that you like get the accepted verdict because you've done enough of the work to get there. And so the judges have a higher like burden of proof, right? Like you have like a proof that like this brute force then like optimize some stuff like actually runs in time, right?
Yes, we have we have proof that our solution runs in time to pass.
Yeah. And so I think one thing that we might have here is we might have I guess there are a couple of things here. One is like you could make the argument that this is like scoreboard effect. But the issue here is we already see that there are like so we already have kind of identified the 7 easy problems, right? We've identified A, B, D, F, H, K, and L. And so for a lot of these teams, like because so many teams have solved them, like let's quickly pick on, I guess I'm going to pick on UT Dallas just because they're a team at 6. They haven't solved problem B. But problem B has been solved by 31 teams. So that's going to be, by the end of the contest, that 31 is probably going to be closer to like probably like 40-ish. And so this problem is definitely sort of established to be like not just like easy, but like very much on like the easier side. So UT Dallas definitely has like some pressure, but they also have some sort of expectation that like they should be able to solve this problem, because it's not like they're the weakest or the lowest place team that hasn't solved it. There were a bunch of teams lower than them on the scoreboard that have solved it. So UT Dallas definitely has a lot of incentive to solve B first.
Yes.
Before even thinking about like, maybe they'll have someone thinking about E as well as M. And so because the scoreboard effect, like we talk a lot about the scoreboard effect and saying like, oh, you should have just like gone and like solved like this other problem. Here, the data are pretty clear. Like it's pretty clear that A and B are definitely like 2 of the easier problems. And so like, UT Dallas, Arizona State, Colorado School of Mines, like these 3 teams are in the top 20 right now and they haven't solved B. And if they're like fighting for world finals, I think we would both agree, and probably the judges as well, that the easiest path forward for them would be solving B and not trying to do, say, like for mines, like maybe not focusing on M. They probably need to solve like B, and they would need to, like every team, most teams that are going to make finals are going to solve all of A, B, D, F, H, K, and L. And so that's where we're going to see them move their attention to. And so, you know, there is a bit over an hour left in this contest, so we'll see what they do. We have some more guests coming up, so we're gonna play another quick ad and bring in another coach. See you soon.
Like all great journeys, it started with one person's vision and the drive to make it real. Empowering brilliant minds who turned ambition into action. We questioned accepted wisdom. We embraced challenge. And together, we changed the world of finance. Twice. Today, we are the most profitable hedge fund manager of all time. And as the next generation,
These competitions help to create and empower a new wave of talents and leaders in digital technology, and they help to grow a new generation of future programmers.
The competitive programming community is special to me just because I grew up with it. I started doing this when I was 12, and it basically kickstarted my whole career.
I think it's important for Jane Street to be supporters of ICPC community because this community is very important for development of many young people who just started their journey with software engineering.
What makes ICPC special to me is that people from many different countries just come together to one place to compete against each other and create a community.
Many Jane Streeters have been involved in the same competitions you're here to take part in. I met some of my closest friends through these competitions, and to this day I still enjoy solving problems with them.
I have been competing in ICPC for 10 years. It was what introduced me to the world of programming, to the world of problem solving.
My experience at ICPC prepared me for my role at Jane Street, mostly in terms of being able to formulate my ideas clearly and implement them quickly.
I use a lot of programming skills I learned during my years in ICPC competitions.
I think Jane Street is kind of similar to ICPC in a sense that we solve a lot of complex and interesting problems in a very quick matter. And I think this experience led to me being successful in my career and having a lot of expertise in what I do.
This is how I've met a lot of friends in high school and in university. We participated in competitions, we share a passion for competitive programming, and now we work together at Jane Street.
You're surrounded by people who care about the same things as you. If I could give advice to someone competing today, I would say make as many connections as you can.
The most important part is to find your friends, gain knowledge, and have fun.
All right, welcome back. We have Karoni here.
Yep.
Karoni is Kusaga's teammate here. Karoni, what's your real name?
Okay, so my real name is Chung, but people online from Codeforces community and gaming community alike call me Karoni. So yeah, you can call me whatever. I don't really care. That's what I always tell people.
So my understanding is in the unofficial people participating in this contest, USA 1 is done with the contest. They've solved everything.
Yep.
Right now we have UIUC at 11 problems. They're missing C and G right now. They've got M. We have MIT has dark green C, and they're the only solve so far, except for Karoni, who's gotten it a few minutes ago.
Yes, I solved it on the online version a few minutes ago. I actually don't know about, except tourist team, right? Except tourist team.
Yeah, I guess
yes,
tourist team, of course.
But yes, yes. We
So let's take a quick look at that problem.
Mm-hmm.
And we'll talk about that real quick, and then we can get back to the contest right before the freeze.
Mm-hmm.
And we have some more guests right after. All right, here we go. So the problem is not F, it's C.
Yes.
Called Entrapment.
Mm-hmm.
Entrapment is an asymmetric two-player game that's played on a 3x3 square grid. The two players are called the runner and the trapper. The grid squares are numbered 1 to 9, as depicted below. Before starting the game, the players agree on a number of rounds that the game will last, and the starting state of the board. Up to 8 of the grid squares can be marked as unavailable. The players also choose who will be the runner and who will be the trapper. The runner then secretly chooses a starting square from among those that are available among those 8, but does not tell the trapper their choice.
Mm-hmm.
Each round of the game consists in the following steps in order. The trapper publicly chooses some subset of available squares and asks the runner, "Are you currently in any of these squares?" The runner answers truthfully, and then the trapper publicly chooses exactly one available square. That square becomes unavailable for the rest of the game. The runner might currently reside in that square, if so nothing special happens. The runner secretly moves from their current square to an available orthogonally adjacent square. If no such square exists, the runner announces they are trapped and the trapper wins the game. If the runner has not yet been trapped by the end of the last round, they prove to the trapper that they answered all questions truthfully by revealing their choice of starting square and the move that they made during each round, and then the runner wins the game. Because the runner's initial choice of the square is secret, as are all of the subsequent moves, the runner is allowed to cheat by not truly committing to a square, so they can like decide what they would have said earlier on.
Yep.
At the end of the game, the runner can produce a choice of starting square and subsequent moves that do not result in being trapped. Yes, so it's like basically, oh, what a long problem. This is like 4 pages. Holy cow.
Yes.
But it's interactive.
The interactions is very straightforward. Like, you are given the original state of the game, and you need to decide whether to be a trapper or a runner. That's it.
And the initial state of the game is just there's one square that's unavailable, right?
No. So the squares are so the trapper subsequently make one more squares unavailable. So like originally there may be multiple squares that are unavailable, and then each subsequent move the trapper makes one more square unavailable.
Oh, so the starting state of the board is like a 1 of 2 to the 9 possibilities for is each square available or unavailable.
Exactly.
And then given that, you want to see, you pick who you are, and then you see can you survive to the end.
Yes.
And then the opponent will play against you optimally, and you have to like prove that you can win, basically.
Exactly.
I see. So basically, the question is, can you force trap the trapper?
Or can you outrun the trapper?
Or can you, or if you can't, then show how you can outrun the opponent.
Yes.
Okay. So first obvious question, is it the case that sometimes each player wins, or is there always one winner?
There's always one winner because
so it's always the trapper or always
Yes. First of all, because the game consists of exactly these many steps that is given as input. So yes, the like both of the players agree on the number of steps that the game will proceed. So if you read the input statement, we have like this 3, 6, and 6 unavailable squares.
Okay.
But the three in front is the number of moves of steps that both of them will make. So they agree on.
So you're making 3 steps.
Yes.
So the question is, can the trapper win trapping 3 steps? I mean, of course, right?
Yes.
Because they just trap all 3 of the remaining steps.
Exactly.
And then...
Exactly.
Okay, so the real question is when these numbers are smaller, what happens? Okay, so in the second example, it's 2, 0, and then you can run away for 2 steps.
Yes.
Because you like start in the middle, I guess, and then do something else.
Yes.
And the only rule is when you're the runner, you can't move into. You have to move, and you can't move into a square that's been chosen.
Yes.
Can you stay in the same spot?
You cannot stay. You have to move.
Okay.
You have to always move.
Gotcha. So I guess the first thing to note here is that we have like a 2-colored problem, right? So we always have 9 squares. And we've got 4 of these here. And then the other 5.
Yes.
And you always alternate between a red square and a white square, no matter how you move between turns.
Yes.
Okay. These are also pretty much independent, right? Like, yeah, I guess not totally independent.
Yeah. It's not totally independent, yeah.
Okay. So, interesting. Okay. And the game is only going to last at most 9 moves.
Exactly.
Oh, brute forcey. Okay.
Yes, very brute forcey. Like I think that most, I guess, I don't know, seasoned or not contestants who see this type of problems, I think most of them, the first thing that will come to their head would be brute force, right?
Yeah.
Like brute force the game and see like how to optimally play this. And if you're like a little bit seasoned about these game stuff, you would do a DP. So like you would DPA something where you would put in the state of the game in somehow, and you would try to win either as a trapper or as a runner. Yes,
Okay.
exactly.
And then your transition would be, oh wait, so the trapper gets to ask about a subset, and then they say yes or no.
Yes. Yeah, each turn there are 3 different actions, right? The trapper asks a subset, the runner says yes or no, and then the trapper chooses a position.
So
you
this
make an
state is a little messy.
Yes.
Because not only is it which squares are available, but it's also there's some information on what squares could they possibly be in.
Yes.
Which might not be what you last asked. It might be smaller or bigger than that.
Exactly.
Okay.
Yeah.
So.
Well, let's put a twist on this game state, right?
Yeah.
Of course, the game state would always the DP. The TP would always can trapper win? Of course, it will win. The question is, how much move would they need to win, right?
Oh, sure. Yeah. Okay.
Yes.
So yeah, fewest number of moves.
Yes, exactly.
And this is at most 9. Okay. So let's put some sort of transition as like try all moves for each player.
Yes.
Which is kind of messy. Okay.
It
So let's
is
put
kinda
some sort of bound on this game state because this is a little scary. So we have at the very least 2 to the 9.
These are the unavailable cells.
Yeah. Unavailable cells. This is 2 to the 9 because you have 9 squares and each one can be available or unavailable.
Yes.
Okay. And then we have some more stuff too. So there's also, well, there's not just what square is he in. There's what squares could he be in.
Yes, what square could the runner be in?
Yeah.
Exactly.
So what squares could the runner be in? And this is also 2 to the 9?
Yes, but
no, 2
the
to the
observation
5.
is the unavailable cells and the cells that the runner can be in are disjoint, right?
Oh, I suppose so.
Yes. No, it obviously
Yeah,
have to. Yeah.
that would be the case. Yeah. Okay. So that would be order 1 amortized?
No, it would mean that the total, like if you add
Like
these 2
these-
states together, it would be 3 to the 9, where each cell could be 0, 1 if it's unavailable, or 2 if it's like you can represent each cell as 1 of 3 bits.
Okay.
Yeah.
Okay. So yeah, I see. So then it's like total we have 3 to the 9.
Yep.
So the 3 things are unoccupied.
Yes.
Definitely.
Yeah.
Maybe occupied. Or
unavailable.
Unavailable.
Exactly.
Okay. All right. So this is not, how big of a number is this?
It's 20,000. That's what I calculated.
Yeah.
Not too
20K?
bad. Not too bad.
Okay. So yeah, not so bad. So now we need to consider our transition.
Yes.
So our transition is as the I guess the runner doesn't really have to make any decisions.
Oh, the runner can make the decision of yes or no if they're in like.
Oh, they can choose whether or not they're in it.
Yes, or yes.
Okay.
Yeah.
But that's not
That's
too bad.
2.
Yeah. Until. Oh yeah. We the scoreboard freezes in a minute. We'll yeah. Okay. One minute till freeze. Are there any teams we should look at real quick? Well, we have a minute left. We can look at screens for 1 minute. Should we take a look at UIUC's screen? Let's do it. Can we see UIUC's screen? See what they're working on next? Nothing.
That's a lot of numbers on there.
Looks like
That's
they have a
C.
brute force for C.
That is a brute force for C. Yes.
Yeah. Okay. All right. So they're working on C, and let's see UCF real quick. All right. CMU. Yes, that's more important. They have I. They're coding I or L. I. They're coding I. Looks like it's not much there yet. Okay. And then UCF in 12th. They are deep in debugging land. Also for C? No, for F. They have something coded for C, but they're working on F. So they've just dropped L entirely, it seems. Finally, we have MIT in 3rd. MIT, as J, or they're working on J.
I think that is J, yes.
Yeah. And it looks like they're also in the process of debugging J. Quite the scoreboard here. MIT, I guess, yeah, MIT's prospects of getting first are very limited in 1 hour. We also now have a scoreboard freeze, so any future submissions that we see, we will not know the verdict of them. We'll see simply what problems they were to. And if a team submits multiple times, we'll see the multiple submits come in, but we won't see whether or not any of them were correct. If you're interested in the final scoreboard reveal, we'll have a reveal after the contest where we do something called a resolver. Everything scrolls up. It's very exciting. There's a whole show of it.
Yes.
That'll be later tonight in a separate stream. But for now, so here's the first example of it.
I am very happy that Austin gets
UIUC. Look at this. UIUC just submitted to G in the freeze. That seems basically like it's intentional to wait till exactly 4 minutes to submit G. So now no one knows whether or not they got it. And you also see Georgia Tech submitting to I. Very interesting. Georgia Tech, they're the dean of their College of Computing. Actually won ICPC World Finals in 1985, I believe.
I see. That's very interesting.
So you hear a lot about previous champs coming from different places, but that's a fun one. All right, wonderful. Well, let's keep going here with this state.
Yes.
So we've got the game state of this many possibilities for what the trapper could be thinking. The trapper needs to pick a subset.
Yes.
Ask the question, and then choose one space to eliminate.
Yes.
The subset is the big one because the subset is 2 to the 9.
2 to the 9.
Roughly, but
Yeah.
some of those don't matter because
yes, that is
you
true.
don't care about any of the ones you've already eliminated.
Yes. So I think amortize, like, like if you add everything up together, I think like the number of states times the number of moves, the first moves that the trapper can be in, can do, is roughly, I would say 4 or 5 to the 9.
Okay.
roughly saying.
A little hand wavy there.
Yeah.
Okay, sure.
Yeah.
But this number is reasonably small. Like we're getting there, but it's it's doable.
Yes.
Okay, and then it's a lot of coding.
Yes, it is a lot of coding. So, in our online mirror that I do with Kosaga, which is the MIT's coach, basically what he did was so Kosaga went on the stream a bit earlier, right?
Yep.
He just told me go code C, and then 250 lines were outputted. Yes.
And then you've recently gotten it.
Yes. It still took a while from when he came back and until I debugged successfully and submitted a correct answer. But I'm glad I submitted correct answer. Otherwise, I would be very, very sad that I coded 250 lines for nothing.
Yeah. Well, there you go. Wonderful. All right, let's do a couple more fun facts here. Who do we have? We have Duke. They have Ian on their team. He's a cellist, and he studied conducting, like music conducting.
Ooh.
Last year. Yeah. So that's a fun one.
Glad to see non-CS people getting recognitions in ICPC.
Yeah. There are a lot of different ones. We also have, you mentioned some coaches, interestingly, right? Kusaga as a coach. Kusaga's a pretty young guy. We have several young coaches among different teams here. University of Toronto has a coach the same age as them. So does University of California, San Diego. Both of those have coaches the same age. And finally, UC Davis, their coach, his name is Theo. Their coach is younger than 2/3 of their team. And he was recently in high school, like 5 years ago or so. When he was in high school competing in IOI, I was his coach.
Oh.
So in a way, I'm kind of UC Davis's grand coach, if you think about it. They also said Theo might participate next year for potentially UC Davis, maybe another team, but he's eligible. Their mascot is also Muna, which is a Pokemon.
Oh,
it's
Pokemon.
a dream eater Pokemon.
Okay, I was thinking of a VTuber there, but we don't talk about that.
Dream Warriors and Dream Demons were their previous two names, and now they're like Dream Eaters, and they're named after what I think is a Magic the Gathering card, but it's too hard for me to pronounce, so I'm not going to give it a shot. But hopefully Theo does well. Does well here. Who's ready? Tony?
Tony and 5.
All right. We'll be back very soon. Let's just see if we'll be back after this very short break.
Hi, I'm Hanel. I studied computer science and math at Harvard, and I've been a quantitative trader at Jane Street for a year now. And what that means is that I spent a lot of time writing algorithms and writing code, doing research to try to figure out what trading strategies we want to try to implement.
So I'm Tudor. I'm a software engineer at Jane Street, where for the past 4-ish years since graduating from the University of Toronto, I've been working on our ultra-low latency trading team, where we deal with all manners of things between fast software to very fast hardware and everything in between. While I was at the University of Toronto, I participated in our ICPC team and I participated in the ECNA regional.
So I'm on one of the algorithmic trading desks, which means that I spend a lot of time with other people who actually have pretty similar backgrounds to me. So just a couple of days before this event, I told some people on my desk that I was going to ICPC, and turns out, I already knew one person had also done ICPC. It turns out there are 2 others who had as well. So I think that it's always a fun surprise seeing how many of us share similar backgrounds and share this love for competitive programming.
I'm not sure about ICPC in particular, but there are many people in the firm who set things like Code Forces rounds or things for local competitions. I myself have set many dozens of problems over the years for Canadian competitions. I mean, it's nice to see the other side of things, on a personal level. And I don't know, I personally feel like the community gave me a lot when I was going through it and building up my skill set, and talking to people and coaches was very useful for me. So it's great to be able to be in a position to give some of that back, and it feels rewarding as well.
So I interned twice at Jane Street. So I did one trading internship. I enjoyed it a lot. I thought it was very, very fun. And I decided to go back for a second summer. And I think, the first part of the trading internship it's very educational. We do a lot of mock trading, and we do various activities that show us what the real job is going to be like. And then it wasn't until my second summer that I got to, actually be on a real desk and try the job for itself. And if anything, that was even more exciting than the internship.
I was previously an intern at Jane Street, and yet again, it's very fun to be on the other side of that and really think about what you are giving to an intern. As an intern, you receive a project that's pretty self-contained and you can solve in the 6 or 12 weeks that you are there for. Spoiler, real life work is not quite like that. Things have hairy tendrils that extend into other teams and other systems. But it's fun as a mentor to sort of put together this snowflake and fun project that you really wish you could work on yourself, and hand it off to the intern and see them be happy with it. We have offices around the world, and interns, if you're from Europe, then you will likely intern in the London office. If you're from America, you're likely going to intern in the New York office. If you're from Asia, probably the Hong Kong or Singapore office. But the work is pretty similar, and there's a lot of cross-collaboration between the different offices.
Yeah, no, it's surprisingly international. I think we actually had a discussion on desk where apparently we have 3 different IMO Gold medals from 3 different countries, each of them. So it's quite international. I think it's very fun just seeing where everyone's coming from and bringing their own perspectives into our work.
I came in just knowing that Jane Street was a finance company, but that was it. Jane Street invests a lot in teaching people things. Among other things, we write everything in OCaml, but we don't expect people to come in with OCaml knowledge. So when people start, they'll have a 2-week period where they go through OCaml boot camp, which is basically school. There's teachers and homework that gets assigned to be done during work hours. But that extends past just OCaml boot camp. We have things like trader training and trader training for non-traders, where you do learn these finance fundamentals, but absolutely we do not expect or even require any sort of finance knowledge going in. Just, a willingness to learn and enthusiasm.
I think on the whole, one question that I get from a lot of people is how competitions like ICPC can be directly relevant for the job itself, because it's pretty unlikely that you're going to be solving shortest path problems as a quant trader or something. But I do think, for one, there have actually been pretty surprising applications of the data structures and algorithms that I've seen, and that's always a really fun surprise. Where I'm trying to solve a problem, I don't expect anything related to ICPC to come up, and then I'm oh wait, there's actually a really cool, clever solution that we can use. So I think that's always a fun surprise. But even when that doesn't happen, which is admittedly most of the time, I think just having this ability to start with the tool set of all these past problems that you've seen, or like algorithms or data structures, and like figure out ways to apply them to whatever the new problem is, I think that's something that these competitions have very well prepared me for.
Our input data are market events. They're not presented to us in like text or like standard input, but we have a very simple stream of, yep, these are the things that are happening in the market. And what we want to output is not to standard output or to a file, but it's like you are sending some some orders that you hope to trade against some other orders in the market. And in between that, like, you get to think and maybe decide to send an order or not. In this sense, it's a lot like an interactive online problem where you can't pre-compute, you don't have foresight of the things you will see in the market, but you know everything you've seen up until that point. Yes, I'm always very excited when I see something at work that resembles like, this is a contest problem. If it wasn't IP sensitive, I would set it as a contest problem and people would have lots of fun. But as it stands, people have to work at Jane Street to see it.
Well, there's your ad for great reasons to work at Jane Street. We have contest director Tony Lockhart here. Welcome, Tony. Thanks for joining us today.
Thank you for having me.
We would love to hear a little bit about the process of setting up the contest. So right now we're in the freeze, which means we can't see anybody's screen.
Sure.
But in the meantime, we were wondering if you could tell us the hardest part about being the contest director.
Well, right at the moment, I'd say the hardest part is being interviewed on live.
Oh yeah.
But if I
stressful.
But if I think about it for another second, I think genuinely the thing that is hardest for me is that we have limited space at the NAC, and we have to draw lines. And every year, there are a couple of teams that I look at and I think, I want those teams to go to the NAC so badly. And it's very difficult to draw those lines and say, this team gets to go and this team doesn't. It's the thing I hate doing the most. I wish we could increase the size of the NAC a little bit, but on the other hand, there will always be a team that will break my heart that they didn't make it. That's kind of the hardest part.
You do kind of want it to be exclusive too, right?
Of course you want it to be exclusive. Exactly so. But there are always teams that are just right on the bubble, and it's tough.
And we're already like pushing like what's possible to do in an event. We have 2 full hotels.
We do.
We have buses going both ways.
Yes.
We're using the entire Grand Pegasus Ballroom at UCF.
Right.
We've got maybe let's take a look at the screen here, or the floor here. We have each of it is like 52
teams.
Yeah.
And then we always have 2 extra spots just in case something happens, so that we can immediately move a team to another station that's ready to go. So we have to have a couple of extra spares. And when you're looking out on the floor there, it's hard to imagine just the logistics involved in producing what you're looking at. It just looks like a bunch of people sitting at tables, but to find the space and lay out the electricity and the internet and lay out the systems and get all of the screens working and all of the AV working and the balloons and the printing and the signage, and we have a huge team of people, all of whom are the best at what they do, but it takes a very large team to make that come off. It looks deceptively simple when you're just looking at that picture, but there are a lot of man hours involved in putting that together.
And each one of these tables has a computer, a keyboard, a mouse, a webcam, a monitor. You have the whole table itself, and none of these tables are part of this whole area here.
No.
These are all set up just for the event.
For sure.
The things the curtains are on are assembled by your team. All of the curtains, obviously, that are there. We assembled this thing behind us, and this was a process on its own. But when you compare this to that whole thing, I mean, there's a multiple of 56 or 54.
Well, right, that's right.
On all these things.
What it takes to do that. And the thing that is actually one of the harder things to do, believe it or not, is balloons.
Well, helium, there's always the helium shortage.
There's always the helium shortage.
And you got a whole team of people running these balloons out every time one's accepted, and you got 56 teams. You got to get the right balloon to the right team.
That's right. Although they're so good at that, but actually the thing that's hard to do is that we have multiple wonderful sponsors, and we put their logos on the balloons, and we have to get all of those printed, and every problem has to have every sponsor on it, and then we have a fairly complicated algorithm for making sure that we have good coverage of sponsors out on the floor, and we get handicaps from the judges of what are the hardest problems and the easiest problems, and it's that is actually one of the more complicated things to do, is getting the balloons out.
If you don't know, I mean, that's totally fine, but I'm just curious, does every color balloon have the same sponsor on it?
Every color balloon has every sponsor on it.
Has every sponsor?
Yes.
Oh my goodness. All right.
Yeah, that's where it gets complicated.
Yeah. Wow. All right. Next question here. We've been at UCF a couple of years now. UCF, absolutely wonderful campus.
I love it.
What is your favorite part of the campus here?
Well, there are two places that I think about during the off season, so to speak, when I think of coming back here. One is I just love that boardwalk outside of the Student Union.
By the Student Union, yeah.
It feels like I'm stepping into the wild wetlands of Florida, and I'm 50 feet from the Student Union. And it's just amazing. I stand there and I listen, you hear the birds and a little bit of water in there, and it's incredible. And that is at the Student Union is unbelievable to me. And the other thing I love is standing in the, in the Student Union, there's a huge rotunda, and when it rains, that is such an amazing place to stand. There's a glass dome, and when it rains, the sound of the rain on that glass dome when you're standing in that rotunda, it's just amazing.
Interesting. Where is this? Is this like on the second floor?
No, just standing where we took the picture, the NAC picture.
Oh, the big hall and
right,
everything.
That big hall. I love that spot, especially when it's lovely to be in any time, but when it rains, it's really special. You get this.
Wow, yeah, that's wonderful. That's a wonderful. So just for people who are watching, UCF, it's like structured as a bunch of concentric circles, basically, and you have like these 3 walkways, and the Student Union is it's right here. So there's like this building right here, and then you've got like different classroom buildings around in these circles, and then you have these 3 circles that you can take paths around. But in this Student Union, there's a little sidewalk around it, and then here there's just like a bunch of woods, and there's a boardwalk that you can walk like through the woods. And they didn't want to like tear down the woods when they were building it, but you do need to get from here to here very frequently, because here's like Memory Mall or whatever. It's a very big open grass space. So they built this thing through the woods, and you have like cutouts for the trees coming out of the boardwalk. It's really beautiful how they did it. So yeah,
it's a gorgeous campus. Anywhere you go, it's going to be a gorgeous campus. But that's a very unique feature on this campus, I think.
Thank you. All right, so one more question for you. Any teams you've been cheering on today?
Well, I love them all equally, but I do have a soft spot for the first timers. So, let's see, who's here for the first time this year? Dort, I believe Ohio State, I believe the University of Florida, University of Georgia, Michigan State, and I feel like I'm missing one. Arizona State.
Really?
Yeah, this is the first time they've been to the NAC, and so I always have I'm always wishing a little harder for them to have a good time and to have a good showing, so that they go home enthused and will build up their programs and be back next year.
We had a fun fact about Dort. I may have already announced it and crossed it off, which is why I don't see it, but I could have sworn I had one. Maybe not.
Well, they're from Iowa.
They love corn.
And they love corn.
That was their fun fact. They love corn.
They love corn. Well, how could they not? They're from Iowa. They're living in the middle of field of dreams, right?
Yeah, exactly. So we're going to do some quick fun facts while we're at it here. We're running a little low on time, and we have a queue of all of the submissions. From University of Virginia, they actually have a different team than last year. Their last team had an Edward L., but they replaced him with Edward L. So different team this year. Northwestern University, one of their teammates is a FIDE master in chess. Might play him against Stanford, because Stanford also brought a chess set this year. UBC, they're solving pizzas and eating problems. That's not a typo. That's what they said directly out loud to me. So there you go. Caltech, 2 of them like this artist named Dominic Fike.
Ooh.
I don't know much about him, but apparently he sings Love Hangover with Jenny. And I've heard people who know Jenny, the singer, Korean singer or something, I think. Iowa State University loves exploding kittens. The card game. USC, they have one teammate representing another school at NAC last year. And University of Alberta, they're the only team who has classes in French.
Oh.
And they had a coach who took a 40-hour train ride to get here. And they found that the file size limit for uploading files to solve problems was accidentally 3 million% too big. It was set to 8 gigabytes. It should have been set to 256 kilobytes. So 3 million% off, but close enough. It's been corrected since. So for this contest, we're set. It's just the practice round was a little too big. Awesome. All right. Well, thank you so much, Tony.
Well, thank you for inviting me. I appreciate it.
Any closing words for people watching?
I hope to see everybody here again next year. People who are watching, keep practicing, and let's get here next year.
Awesome. Thanks so much. We'll, if you guys are heading out, we'll see you for the scoreboard reveal. And we have an exciting remaining 40 minutes of the contest for teams to get their last minute submissions in. Maybe UIUC will submit to C. I guess we'll see. We just talked about the solution, so we know it's a very doable problem. All right. Thank you once again,
Great.
Tony. We'll
Thanks
be
so
back
much.
in just a sec.
And welcome back. Here I am today with one of our wonderful sponsors, JetBrains. Hi Rita, how are you doing? So happy to see you here at NAC.
Hi Lydia, and likewise, I'm happy to see you here too. Actually, I think this year everything goes smoothly. Third time on the same spot as 2 previous years. It's good.
yeah, I agree. It's much easier to organize a contest when you know all the variables, and it's both us have that background in contest organization, but we've did our fair share of, different sizes of contests. It's wonderful to come to NAC and just enjoy it, not take care of it that much, but just look at how precisely correct everything is organized in here. I'm a huge fan. Tony, who we've just seen, is doing an excellent job, right?
Yes,
right?
actually, Tony is amazing. But Lydia, I think you're doing some kind of organization job here with
I'm just
SCPC Live.
helping make everyone see how cool it is here. That's it. Very easy job. When the event is so good, it's very easy to show it in a really nice way. We have another surprise submission from Carnegie Mellon University on I, so let's keep an eye on this. But in the meantime, JetBrains' involvement has been so huge. It's obviously programming tools for all the developers, as well as plenty of interesting talks about your new projects and stuff. Last year, in the same location, I was interviewing Andrei Ivanov, and I kind of I joked that next year, as in today, in 2025, I challenge Andrei to solve some problems using an AI assistant. And again, Andrei is now busy, so yeah, potentially he is solving problems with an AI assistant, but David and Nick together were able to solve several problems using AI prompting today from today's contest. So first of all, oh no, I think I cursed us last year. It was a joke, but then it turned out not to be. But also, I'm really interested in, involvement of JetBrains into evolving yet another generation of programming tools. 20 years ago, when JetBrains was just founded, using ReSharper to automate refactoring process felt like magic, and these days JetBrains still continues breaking all the rules and making sure that there are new frontiers for our developers' comfort. Tell me a little bit about your new interesting projects that are coming out from JetBrains.
Actually, I think, as always, Lydia saw the future a year ago. I think you always should listen what Lydia told you about the future. So
don't listen to what I'm telling you about contest predictions, though. I'm always off because I root for the teams with my heart, not with my mind.
It's different.
That's
it's not about
that's an issue.
future in general.
Right.
So anyway, right now we have our new AI helper Junie that can help programmers do something in our ADAs. So if someone wants to try it, I really recommended it, and it's free for students. They can try it without any pain, anything. So I don't think that with that Juni helper, it's like Juni, like junior helper. So anything that with Juni we may do a lot of new problems and solve a lot of problems, but it can help, for example, do some tests for the problems. And I really hope that it will help judges, for example, with problem sets and etc.
We had judges on our broadcast talk about their problem preparation process, and it is one of the more engineering-oriented parts of ICPC. Without a strict deadline of 5 hours, judges can actually employ some proper techniques to maintain a clean repository, to work as a true team. So this definitely works wonders. I'm sure.
We discussed this question about 30 minutes ago. So I think and for the next ICPC contests, it will help them.
That's awesome.
Yeah.
Another thing that we've been talking for years at this point is that contestants at ICPC competitions of any level are allowed to write solutions in Java, C++, C, Python, and Kotlin. And I know that today marks a pretty special moment. Can you tell us a little bit about it?
Yeah, actually in NAC there is always one team who try to solve problems in Kotlin, and this year is the team of University of Maryland.
Yay!
So my colleagues and I are just rooting for them. Yeah.
And today they had, I think we looked it up, 4 submissions in Kotlin that are accepted. University of Maryland is currently, you can see them on a frozen scoreboard, currently in 10th position, which is a very safe place to advance to the World Finals. So obviously all the best vibes towards University of Maryland team, and we're eagerly waiting for successful Kotlin submissions on the World Finals, right?
Yes,
it's going to be a huge milestone.
And every time after that happens, I thinking about that, try to prepare some special prizes for the team who solved problems in Kotlin and who do the best in Kotlin. So maybe at the World Finals I will do this.
I hope you have Maryland coaches listening.
I
Just,
hope.
it can give that a little push for the team to try that little bit harder to solve more problems.
No pressure, no pressure.
JetBrains is one of the ICPC sponsors who can be seen on contests all over the world. Where have you been this year? What other cool contests have you attended? And obviously, NAC is the contest that selects team for ICPC Baku. Do you already have something interesting in store for Baku?
Oh, yeah. There is a lot of questions in that one. So we've been in the, I don't know, maybe 4th. Yeah, we've been in China in the semifinals in China, in Latin America, in North America, in Europe, of course, and a part of the Northern Eurasia region, we're at Kazakhstan. So it's like 4-5 semifinals where JetBrains were this year. But I think for the next year we will have more plans. It's not at all. Yeah, I forgot the last part of your question.
No worries. JetBrains always hosts JetBrains Tech Track, which is a great way to showcase all kinds of new things that happen in JetBrains life and get our contestants to know more about professional software engineering and development. I'm not asking you to spoil anything, but maybe just a teaser. What do you have in mind for Baku for 2025? What's the hottest new thing?
Actually, it's a really good question because this year we just felt that a lot of good things and great things and cool things we already did, like blind coding, like tourists on the stage and solving Kotlin heroes rounds and etc. So this year is kind of challenging for us to find something new and something interesting for participants. But I think we definitely should do something with AI, with our Juni. We'll see.
Right. And again, tune into our live broadcast, and Baku will definitely live stream Tech Track as one of the events of the World Finals. So you don't really have to advance to the World Finals to get all the interesting ideas from JetBrains team. You mentioned Kotlin Heroes as one of the projects that you also organize to make sure that competitive programming community knows Kotlin. And can you tell me a little bit about other projects that Kotlin hosts in the area of competitive programming? I heard about training camps, contests, so many fun things.
I think the main things that we have is Kotlin Heroes actually, but we're trying to do something. To be honest, not a lot of people solve problems in Kotlin in the competitive world. So we're trying to think something a little bit. For example, during the World Finals and all of our regionals and semifinals, we're trying to do like Kotlin challenge. It's 3 problems that participants that we already wrote in Kotlin. So participants have to find some bugs there. So and of course after that we give them prizes. So we're trying to do something like not so big, but to arrange this meeting participants and Kotlin. So maybe after that they will find that Kotlin is a really good language, and after their ICPC career, for example, try to programming Kotlin and their work not only at the contests, for example, like that.
Yeah, and as a very non-secret thing, if you ever want to organize a live broadcast, you would need to visit our official GitHub repository, which is github.com/icpc/livev3. And you'll instantly notice that all the infographics that's right here around me right now is actually all backend that works with contest control system is written in Kotlin by an ICPC world champion. So definitely a language of choice for world champions. I'm eagerly inviting all of our spectators to try their hand in Kotlin if they haven't yet. And Kotlin Heroes is a great way to start.
Yeah, actually.
Thank you so much for joining me
Lydia.
for the live. It's always a pleasure to see you. Let's try and make a prediction for next year's NAC.
I think.
Chat, welcome. You're welcome to tell us your ideas. MIT submits J. Interesting. Because obviously AI already disrupted the competitive programming world just so much with significantly more AI-assisted written submissions that we have to disqualify because we only want to accept submissions written by humans. But let's figure out a prediction for next year. We'll see each other at NAC 2026, where we'll obviously see more submissions in Kotlin. That's not a question. That's just, a statistics. But what interesting will happen in the world of competitive programming over that year?
Wow, Lydia, I think this question is actually for you because you're the person who predicts future in our world.
Where are the cool ideas from chat? Hey, it's freeze time. We need to get creative. I'm looking forward to next year at NAC, seeing a team push really close to finishing the whole set. I think it can happen virtually at any moment of time. And I know a couple of people who will probably be participating in the next season. So I'm very interested in seeing this. And then in the AI direction, how many problems do you think would either Junie or any other AI assistant or agent would be able to solve in the next NAC out of, say, 12 problems?
I think 10.
Wow. Okay. That's a really hot take. I like that. Okie dokie, then in about a year from now, tune into NAC 2026. By the way, like and subscribe ICPC Live channel so that you won't forget and that we'll have a live stream. And we'll see if AI assistants can actually do 10 out of 12.
And how many predictions we can do.
Right, absolutely. Wonderful to have you. See you later.
Much, Lydia.
We'll be back. And I am so back. While we're waiting for either Yossi, Ivan, or Jinban Chen to join us on live stream, hey, Nick, come back. Let's take a closer look at the scoreboard. So currently in the first place, at the moment of freeze, we have University of Illinois, Urbana-Champaign. They solved 11 problems pre-freeze, and then they submitted right, like, 2 minutes after freeze, so we think problem G was actually on hold for them, and they were trying to make sure that, the competition is still, has some drama by keeping the last submission a few minutes after the freeze, and they have not resubmitted that problem, so it's been interesting. Oh, hey, you ready? You can come and sit. Then we also have Carnegie Mellon, who have not been idle during freeze. They have 2 submissions on I, but again, 2. So we are not really sure if there's going to be a clean green in the second attempt. And it's very probable that there is still a work going on problem I. We have not seen them really work on the other problems either. But solving that extra problem won't help them go higher, which is probably the worst place to be. Sit down. It's okay. Hi. Say hi. That's Andrew. They solved all problems. You proud?
We're okay. Okay. It wasn't the cleanest. The back half of the contest wasn't the cleanest, but we got there in the end.
What's with M? Slow M. Boo.
Well.
Were you watching the scoreboard of the main contest?
So we started 10 minutes. We started like the mirror started like 10 minutes after the official contest started, and we started 10 minutes after the mirror started because we were setting up our stream.
Yeah.
So we just didn't allow ourselves to look at the scoreboard because like 20 minutes in the future scoreboard is like you get a little much information, especially in the first half of the contest. In the second half we could have looked, but it didn't really matter.
That's fair. I think your chat was trolling you quite a lot on not paying enough attention to problem A, because by that moment we've all already seen both Urbana-Champaign and Carnegie Mellon accepting M, as well as an insight from judges that they did not think M was really that hard.
Interesting. M was M was one of the so Kevin and I were working on M at the end of the contest. So by the end of our contest, I don't know if I have a good way of share. If you want to see the VOD, it's on Twitch, I guess. But you can look it up. But the last 2 problems we had were C and M, and C, I guess Genna was saying that.
Look at the problems. Is that what you're saying?
No, I'll just talk about high level. But like C, Genna said he was like procrastinating until the end of the contest. He can talk more about it if he comes. But you know, so we left that for the end. And then M, we also just like didn't really work on or solve until the end of the contest. M was I don't know. We definitely had some trouble proving that our solution is fast enough. And in fact, we still like only have like most of the pieces of it proved. Like I think our time complexity is actually kind of high. And
I had no idea how to even start approaching M. I read it when I was on my break. I don't even. Do you want to talk about it real quick?
Yeah, we can talk about. Let's talk about the problem real quick. So the problem is that we have a bunch of gladiators, okay, and we're going to do a bunch of rounds, and in each round, we're going to sort them from smallest to biggest, right? Yeah, and what we're going to do is each gladiator from left to right is going to hit the next guy, and it's going to subtract itself from that guy. So the first time you get -0 and it's 1, and then the 1 will hit the 5, and the 5 will become a 4. And then instead of the 5 hitting the 6, it's the 4 hitting the 6. So the 4 hits the 6, and that becomes a 2. And then the 2 hits the 8, and that becomes like a 6, right? And the question is pretty short. It's just you're given a bunch of these guys, and you need to simulate them for a lot of steps.
But the tricky part is after this round happens, these get resorted. So
they do get resorted.
2 moves and the 4 moves here.
Yeah, and that's one of the interesting things. So I guess one of the first insights about this problem is it's about alternating sums, right?
Yeah, so I guess if we make the first thing not 0, maybe that's not too helpful. Let's say we make it 1.
Yeah. That's fine. We can leave the 0. Or sure. Yeah.
Okay. So then this 1, it hurts this guy.
Yeah.
But hurting the second guy,
right,
in fact, helps the third guy.
Right.
Because the second guy now hurts the third guy less.
Right.
And then it hurts and then helps.
Yeah. So one way to think about this is that kind of just think about the alternating prefix sums, right? So the first, if you start at 0, right? And I like to draw these graphically, right? So the 0, and then you go up you go up to 1, right? And then you go down by 1, and then you go up by 5, right? And then you go down by 6.
Up by 5?
Yeah, the alternating prefix sum. So we're going to do 1 minus 1 plus 5 minus 6 plus 8.
Okay.
Yeah, because that's like kind of the negative of, and then like plus 8.
Plus 8, so like here. Okay.
Yeah. And one property of like alternating sums of increasing sequences is that like the upper bounds and the lower bounds are also increasing and decreasing.
Yeah.
And the numbers that we get are just like the upper numbers and the lower numbers, like, and then like the absolute values of all points on the sequence.
After, wait, sorry, what are the numbers you get?
So the first one just stays a 1, right? Like that's the plus
because
1
of this
yeah.
here. Oh,
and then the next one becomes a 0 because it got killed by 1.
Cool.
And the next one becomes a 4, because you can kind of just think of it as like you have your running alternating sum, and then like that's how much HP you have. Like 5 minus the previous guy is like
the next one. Why does the next one become a 4?
The next one is a 5,
It's
right?
a 5. Okay, so it's 5. Okay.
Yeah, and then it's a
like
negative 1, which is the 6 minus the 5, right?
Yeah.
Oh, and then the 8
7?
is 7.
Okay.
Right, because it's the 8 minus the negative 1. Which is,
oh,
which
cool.
Is what
I see. Okay. Wonderful.
So this is just a visual interpretation, but it tells you that like as you zigzag bigger, like because the zigzags only get bigger, like the top and the bottom are still increasing, right?
The top and the bottom are still increasing. Like the top goes up and the bottom goes more down.
Yeah, exactly.
So you get something that's like this cone shaped.
Yeah, exactly.
Okay.
And so when you resort, like kind of you can kind of interleave the top and the bottom. But the other thing is like these guys are still like subtracting themselves from the next guy, right?
Mm-hmm.
And so the main insight is in some wishy-washy way, like this shouldn't go on for very many rounds.
Yeah, I kind of felt like that was maybe the case, but I don't know.
Yeah,
So
and
do we think it's log or is it?
And the
just
answer is
something?
it's actually a little bit complicated. So it actually is possible for it actually is possible for it to go on for quite a lot of rounds at a time.
Okay.
But
it won't change by much. Like you'll have 0, 0, 0.
Yeah, it is possible. So it is possible for it to go on for a while without anyone changing order.
Okay.
Changing the order. But once someone changes their order, like swaps, like becomes smaller than the previous guy, it must mean that like they got like if I swung and hit you and then you became smaller than me, then like you must be like now like you must have halved at least, right?
Yeah.
Because you subtract this guy and now you're smaller than that guy, right? So you at least divide it by 2, which means you can't have that many times, right? So as long as you're able to simulate like a bunch of operations that don't change
without
the order,
changing order.
Quickly enough, then it just works. And there's actually like a lot more to like that only gives you like an n squared log n bound on like that gives you like an n log n bound on the number of like interesting rounds, but that's still not good enough because it takes linear time to simulate a round.
Yeah.
So I don't know. We just did some stuff.
So did that. And
we just
it worked?
simulated what we ended up doing is we just simulated until there are almost 500 people.
Okay.
500 non-zero people, and there are some like arguments for why.
Naively until there were almost 500.
Yeah, exactly. And there are some arguments for why that takes them as like log rounds or something.
I see. Okay.
We were like kind of unsure about a lot of these things as we did the whole problem, which is why we like kind of left it till the end. I don't know how much the teams proved when they submitted this problem.
Interesting. Yeah.
That's how we approach it.
It's a question for later, I guess.
Yeah. And the other thing that you had to deal with is when you're trying to do a bunch of these operations at once, we did some stuff where we binary search to find the next operation to find like how many operations don't change the order. So how many operations you can do that don't affect the order, so that you just do them all at once. For instance, if there's just like one guy with a 1,
Mhm.
like there's a 1 and then like a 5,000, right? The one just like hits the 5,000 times,
Yeah.
right? So it's like you don't want to simulate it or like 1 and then like a trillion, right? Like you don't want to do a trillion, like you don't want to simulate a trillion times. So you do have to
binary search
jump
that trillion.
So we binary search for the trillion, right?
Yeah.
But we had to be really careful to not integer overflow while we were doing that. And so we spent a while like thinking about how to avoid that as well. But maybe if you just like throw it at some like black box structures, or like maybe you just throw it into big num, and then like you don't worry about integer overflow, and you just trust that the numbers will stay small enough.
Good enough, yeah.
So yeah, I don't know what approaches the teams took, and I'm actually pretty curious what they did.
Really quickly, I want to talk about your beautiful solution to the cycle problem, and then we'll let Gena on because I'm sure people want to hear from him too.
Right.
So here's the problem was basically you have a series of cycles, or a series of like rings, right? And then you can take an edge in the cycle. So let's say you have like this edge here, and you can glue that to this edge here,
right?
And basically you
can kind of just draw them as like
pull
overlapping
over one of these.
Yeah, exactly.
Okay, and then you can join these again like that, where they share an edge.
Right.
But you can't have these rings form a non-tree. So like you have
So you have this like tree of rings, right? And then the rings are like kind of tangent a little bit, right? And then but the thing is you're not given the rings at the start of in the problem, right? You're only given like the final graph.
And it promised the rings existed before you got them.
Yeah. And so and the question is like, what's the longest cycle in this simple cycle?
In this case, what we're looking for would be, something like this probably.
Probably something like that, yeah. And the edges are weighted, so it could be like something else.
If
one of the edges was really off. But it's probably something like that.
And each of these edges are only once in the graph.
Yes. You're not given two copies of the edge. Yeah.
Okay.
And so the question is just like, is how do you find this? And this is the only problem that hasn't been solved before the freeze. The one team has submitted it after, and or at least one team, maybe more at this point, but at least one team has submitted this after the freeze, and they also haven't resubmitted it, so maybe they're done. Or maybe it's correct.
UIUC?
UIUC, has submitted
problem G.
it.
Yep.
Yeah. So there are a lot of ways of recognizing graphs like this. Graphs like this, like they go by some different names. These are like one way you can describe these is these are outer planar graphs. Like there are subdivisions of outer planar graphs. Those are just like words that I can say because I know them. But like they're pretty much like you have if you think about it, it is kind of just like it's a planar graph for sure, right?
Yeah.
And there's kind of an outer face, right? Which is just like you just trace the outside, right?
Yeah.
And then each of the tangencies is like a little path that like kind of diagonalizes the planar graph that cuts the planar graph. So it's really just like an outside plane and then a bunch of diagonals, like a triangulation of it.
Very cool. Yeah.
And recognizing it is kind of hard, but it turns out that this is a member of a type of graph called series parallel graphs.
Okay.
And series parallel graphs are formed by you take an edge, you kind of like take two series parallel graphs and you attach them together at two edges. So you have like at a vertex, right?
Yeah. So you've got one graph over here, and then you combine it with another graph on an edge.
On a vertex. Sorry.
Vertex.
It's like I guess a series parallel graph has like one entrance and one exit.
So this is the graph here. It's like the
no.
Inverse?
Sorry. It's like the one way of thinking about it is like if you have a bunch of tangent edges, right? The tangent edges are like
this is the tangent edges here.
Yeah. These? The tangent edges are like kind of like a bunch of edges glued together, like a bunch of like single edges glued together in like a chain, right? So a series graph is just like a chain of two other graphs, and then a parallel graph is like two graphs glued together. And it turns out that these graphs are all series parallel, and you can do the inverse, which is you just take any vertex which has degree 2, and you like contract it. So you combine its two edges, and you can take any two parallel edges and compress them. And it turns out if you do that, then the graph like eventually becomes just a single edge. And
so real quick,
you
just
do
to
the
summarize,
DP as you do it.
The two operations to collapse this is if you have something that looks like this,
right?
You can just make it one long edge.
Yeah, that's
and then add the lengths of the two.
Right.
The other thing you can do is if you have something where you have like the same node here and here, and you have two edges.
Right.
There's only two things you'll do with this. Either you'll make this loop.
Yeah.
Or if you don't want to make this loop as the longest loop, you'll just take whichever one's longer.
Yeah, exactly. That's right.
And then you can keep just collapsing it down.
That's right.
And you end up with
Yeah. And so it's kind of interesting. This solution like uses a formulation of the graph that doesn't actually like directly correspond to what you're given, the guarantees you're given. And actually, this solution actually works for any series parallel graph, which is a slightly bigger set than the graphs that they're described in the problem. And I'm not entirely sure what the judges intended, like if they intended for this kind of approach, or if there's some other approach that works like even cleaner for just these outer planar graphs. But you know, we just did the contractions.
Awesome.
Yeah.
Well, thanks so much. Congratulations on your performance. We have one last guest, I think, for the last 10 minutes here, which is, I think, probably the crowd's favorite. We got the one and only tourist. Welcome, Gennady.
Hello, hello.
How's it going? How's your contest today?
It was good. It was good. I was a bit frustrated when I got some wrong answers, but that's normal. That's what happens all the time.
Were these wrong answers primarily on C?
I got 2 on C, and I think there were just some logical bugs, but basically I just wrote like 250 lines of code, and then I don't know if there's anything simpler, or for example, this problem was solved by MIT at 3-hour mark, I think, from the first attempt. So it's pretty pretty impressive. I could not get a clean solve, so you know, and there are 3 more teams trying it in the freeze, and we'll see how it goes.
We saw a lot of teams had code for it, and then I guess it was just too much. They didn't put it there.
If you start typing it and you give up, that's pretty bad, I guess. But maybe if you have nothing to do, you can start trying it, and then at some point decide that you have something better to do. That's fine too. But I think it's this problem. I looked at this problem in the first 10-20 minutes. I think it was because like we kind of split the problem set at the beginning. I look at the beginning of the problem set usually. So I looked at it, I was like, okay, so we have a 3x3 grid where we have 2 players, they like block cells, they move somewhere, and then since it's only 3x3 grid, we basically, you know, the state, we can represent the state by some just bit mask or something like that, which cells are blocked, where the player can be, and so on. So it's like you kind of know what the solution is going to look like from the get-go, but the implementation could be tricky. But
we were talking about it with Karoni and Kusaga. They were working on it too. Karoni's like entire contest was just doing C.
Yeah.
We were trying to get him earlier. He ended up coming later, but yeah, he was able to get it.
Karoni can afford it. I hope that teams... Well, the teams cannot afford it. They
Yeah,
cannot just
yeah,
start doing
exactly.
C and then like, I'm just going to see this content. I just came here to have fun. Well,
So we heard you hadn't spent much time looking at the scoreboard. Do you want to take a look now? See what you thought about the team strategy? Did it align with your own?
we have not looked at the scoreboard pretty much at all until after we finished. But yeah, it's interesting. I think overall it's a bit more, you know, So there are like a few problems which will decide the advancement to the finals, right? I guess there are 7 problems which are easier: A, B, G, F, H, K, L. Everyone submitted them in the top 20, right?
And this is the optimistic standing.
The optimistic
so this is assuming
standings, it's pretty
everyone
clear.
gets everything they've submitted right.
So here it's pretty clear. There are 7 problems which are everyone tries pretty much. If you want to compete for the world final spot, you probably need to get those 7. You could replace it with some other problem though, right? So you could maybe do the E instead and not get one of those accepted. And then there are C, G, I, J, M. Yeah. So basically, I think it's a good mix that you can choose one of the remaining problems, and
So it looks like E might be almost required for medaling, or pretty important at least.
I think
oh my goodness, look at this. UIUC had their final submission.
UIUC submitted. Maybe they just finished. Yeah, would be pretty great.
That'll be a great scoreboard reveal.
Oh yeah.
Check out the Resolver later today. We've got a separate stream for it. It'll be in a couple hours once we, I think, have dinner and head over to the other room.
Right. Like if you look at the submissions of other teams, like so far no one even submitted more than 11, right? So with the current state
to see, you mean?
Yeah. So with the current state of scoreboard, even if everyone passed everything but UIUC did not pass anything, they would still win.
Oh yeah. So I mean UIUC almost, they've got it in the bag, but they've had a very good penalty.
No, but like a wise man once said, a contest is not a competition between teams. It's a competition between teams and a set of judges.
Yeah. For a perfect set.
Exactly. Yeah.
Well, you certainly showed the problem setters who's boss. So well done. How long did it take you guys to solve the set?
I took about 200 minutes, I think. So it's like 340.
Just over 3 hours.
40 minutes.
Okay, yeah.
Something like that. Yeah. Yeah, it was easier for us at least than last year. Probably for the teams as well. I think there were fewer problems which we got stuck on.
What do you think was the most difficult one? Scoreboard says G. Do you agree?
I did not do G during the contest. During the contest, my teammates just discussed it and then just solved it, and then it was there. I did not even look at it. They told me the problem statement after the contest. So the solution doesn't seem too hard.
Did you look at E at all? The humans versus AI?
Well, I did implement it for our team. So yeah.
And did you do persistent data structures or an offline?
I did online square root.
Online square root. Oh my goodness.
Well, online. Sorry, what do you mean online? I guess like. I mean, the problem.
So, do you want to go through it real quick?
Do
we have time or no?
Well, sure. Like, what's? I guess. Do you have any? Oh,
yeah. So we can find it actually. So the.
Oh yeah. Okay.
Yeah. This was what we started with. So the idea was you're given. Is this it? I think
it looks like this. Yeah.
So you're given 2 arrays.
Yeah.
You first collapse that to one array.
Yeah,
the difference array. The computer gets to make 1 negative.
Yeah.
When the computer makes 1 negative, that hurts you by 3 times the potential.
Yep.
So you need to find, are there ranges where the sum of the range is now bigger than 3 times the max in this other array?
Right.
So we did that by finding a data structure where you can query range sum, which is obvious, and then also query the max in a range. Query which ranges have a sum or have a max. Hang on, I forget. So count for in an LR range how many things are bigger than X.
Yeah.
And to do this, we did this with offline queries.
Yeah, maybe that's one way to do it. I did not think about how to reduce to this, but basically I had a similar type of query, but I also had updates where like I had to add something on a like my operation. I need a data structure which could add a value on a range.
Oh, because what we did for that is we took the 18 as the biggest, and then we did it in order smaller half. That was our approach.
Smart. Okay, I see.
And then we split it, and then we said, okay, now only consider ranges that don't include the 18.
I see. Yeah. So it's like I see. Yeah. I was thinking about divide and conquer, so you like choose the biggest, but then I see. So it's like going through the smaller part is smart. I did not think about that. But yeah, so I did not fix this biggest number. I just went left to right, and then basically I had a stack of like maximums, and then like basically I just reduced it to I have a linear number of updates on the range.
And then
and then also the query is how many numbers are greater than something.
Okay, and you were able to get square root.
But you can just split the array into subarrays of square root size.
Okay,
and then you do a reparation in square root or square root times log.
Awesome. Awesome. All right, thanks so much. We have a minute left in contest. Can we get any audio? No.
There's also Discord.
Let's check Discord here real quick.
For a quick announcement.
All right, the online judge will go offline. So announcement time. An online judge is going offline shortly, but problems will be available for upsolving on Caddis. Open Caddis. There you go. Sorry. Okay, are we doing a separate video for G, or do we want to do that now? What do you think, Lydia?
It will be part of the live.
Okay.
After a short video break for the remaining videos, if we have any.
Sounds great. All right, we're gonna do a short video break. Actually, let's first do the end of contest. We'll wrap it up. We have 15 seconds left here.
Yep.
We'll see the flood of submissions coming in. UCF, another submission on L.
So UC actually submitted G again, which means their first submission was not correct. Which they made like 40 minutes, 50 minutes ago.
Yeah, that's some drama. UCF also submitting on L, which is a little scary. They would really like that, and they've been working on it all contests. They had it like an hour in, they were working on it, and they're still trying to get it through.
Okay, and it's
And that's it.
over.
Welcome. I hope everyone had a wonderful contest. We'll see you very shortly with a submission to problem G, and then in a couple hours for the scoreboard reveal.
Yep, stay tuned.
Thanks for watching.
Thank you.
So, hi, I'm
These competitions help to create and empower a new wave of talents and leaders in digital technology, and they help to grow a new generation of future programmers.
The competitive programming community is special to me just because I grew up with it. I started doing this when I was 12, and it basically kickstarted my whole career.
I think it's important for Jane Street to be supporters of ICPC community because this community is very important for development of many young people who just started their journey with software engineering.
What makes ICPC special to me is that people from many different countries just come together to one place to compete against each other and create a community.
Many Jane Streeters have been involved in the same competitions you're here to take part in. I met some of my closest friends through these competitions, and to this day I still enjoy solving problems with them.
I have been competing in ICPC for 10 years. It was what introduced me to the world of programming, to the world of problem solving.
My experience at ICPC prepared me for my role at Jane Street, mostly in terms of being able to formulate my ideas clearly and implement them quickly.
I use a lot of programming skills I learned during my years in ICPC competitions.
I think Jane Street is kind of similar to ICPC in a sense that we solve a lot of complex and interesting problems in a very quick matter. And I think this experience led to me being successful in my career and having a lot of expertise in what I do.
This is how I've met a lot of friends in high school and in university. We participated in competitions, we share a passion for competitive programming, and now we work together at Jane Street.
You're surrounded by people who care about the same things as you. If I could give advice to someone competing today, I would say make as many connections as you can.
The most important part is to find your friends, gain knowledge, and have fun.
Well, actually, I have no idea.
There you go. Welcome.
Okay. This is an explanation of problem G. It's a most scenic cycle, 2025 ICPC North American Championships, just in case that part is cut out. And so in this problem, so there's a graph given, and each edge in this graph has a weight associated with it. And there is a special connectivity constraint about this graph. It's what the problem calls robustly connected. So pretend these are nodes. Every node in the graph is not only has a way to get to another node, but has two distinct paths to get to said node. So another way of saying this is bi-connected, that the graph is bi-connected, and that was not part of the problem statement, but that is a way of saying it. And the other constraint is what it's called regionally connected. And this has 4 parts to it. There are 3 bullet points, but there are 4 parts. One is that there exists a set of regional cycles, and the first constraint is that there are E minus V plus 1 of these regional cycles. Every direct railway line in the transportation network belongs to at least 1 cycle. So every edge you see here is part of some regional cycle. Also, if 2 regional cycles share any direct railway lines, then all of the railway lines and stations shared by those cycles. Oh, I'm mixing up graph theory terminology with the problem statement. So stations are the nodes, and railway lines are the edges. Sorry for that mess up. And you see me drawing cycles that are sharing one edge, but you can also have something like this, where the cycles don't have to conjoin at just one edge. They can join at any number of edges, actually, 0 or more. And when they do connect at an edge, then they need to their connection needs to be contiguous. But note that it can also be the case that you can have regional cycles that can join at two nodes, but not an edge. Like this one and this one do not share an edge. They do share these two nodes. So there's that too. And the fourth really constraint. So for each subset, little f of the set of regional cycles I meant, each subset of the set of regional cycles has at most size of little f minus 1 pairs of regional cycles sharing an edge. So what these basically mean is that this graph is a tree, or it's not a tree. It's a plane, like the graph has a planar representation whose dual graph is a tree, is a short way of saying this, except if you look at the Wikipedia definition of dual graph, then my explanation has to ignore the fact that the dual graph might have duplicate edges somewhere. So ignore duplicate edges of the dual graph and also ignore the outside node of the dual graph. Just ignore those two parts of the fact that it is a dual graph. So for the sake of explanation, I'll call this a biconnected, regionally connected graph. And again, biconnected is the same as robustly connected. Now, and a key observation about this problem is that this graph has leaf cycles. In the same way that a tree has leaf nodes, this graph has leaf cycles. So in this graph, this is a leaf cycle, and this, why did I draw the cycle like this, is also a leaf cycle, and this is also a leaf cycle. And it would be nice if we could process a leaf cycle and then not need to deal with it anymore. But what would also be nice is if we not need to find these regional cycles. And that's basically what the judge solutions go with. So what we're going to talk about basically is a dynamic programming solution which stores optimal paths in edge weights. And it's going to be a destructive algorithm which relies on repeatedly oversimplifying the graph and simplifying it again and simplifying it again. And we're going to get the solution with that. So let's call G the original graph. Was this the color that was used? Yeah, close enough. G is the original graph, and G prime is the graph that is originally G, but is going to be modified. So there are two operations to this. So the first operation is a contraction. If we have a node that has degree 2, ignore this and ignore this. A node of degree 2, then the node and its two edges can be replaced with a single edge. So don't ignore these two edges actually, because these are where they connect to the node that used to exist. And where's the erase on here? Pretend I didn't just scribble this out. So if one edge had weight A and the other had weight B, then this resultant, did I just call these nodes? If one edge has weight A and one edge has weight B, then the resultant edge has weight A plus B. All we're doing is just saying, yeah, let's just merge these edges together. And there's another operation. So that was contraction. The other operation is a merge. So when two edges share the same endpoints, what we're going to do is, let's say, we already used A up here. Let's say this edge has weight C and this edge has weight D. So what we want to do is say, okay, yeah, these edges right here, they have a cycle between them of C plus D, but we're going to get rid of whatever edge is less weight. So if D has the lesser weight than C, then we get rid of it. Pretend that's a C. And we continue. So again, contraction, node of degree 2 gets replaced with an edge. And merge, just take out a duplicate edge and say that there's a cycle length. Did I say what the problem asked for? I forgot. Okay, I did. Thank you. Just making sure. So there's some stuff that this does to the shape of the graph. So remember how I talked about leaf cycles? So these leaf cycles are basically all nodes that are of degree 2, except for 2 endpoints. So what contractions will do is it will simplify the leaf nodes, leaf cycles, until it just looks like a duplicate edge. Which, this doesn't look very clean, does it? But yeah, pretend that this path right here corresponds to this right here, and pretend this blue path here corresponds to this edge here. And so you've contracted a leaf cycle into 2 duplicate edges. And you still have the weight that was made to build it. And what you can do now is just take it off, because that's what a merge operation does. And there are always going to be leaf cycles in the graph we had. Neither one of these operations stops our original biconnected, regionally connected graph from still being a biconnected, regionally connected graph, except in 2 cases, which we'll talk about. They're actually the end cases of our algorithm, which we'll get to. So in this way, the edges in G prime, they no longer represent simply just an edge weight for themselves. They represent the longest path for an entire subset of nodes and edges in the graph. So if, let's say, this edge here ended up being the edge that we don't delete after this merge operation, that would make this edge, which we would have in G prime, represents this entire subset of the graph. And we would keep doing this we would keep contracting and merging edges as we find, or contracting nodes and merging edges as we find that nodes and edges can be contracted and merged, respectively. And just so we're clear, duplicate edges are a thing that this algorithm will just handle. What do I mean by duplicate edges? So sometimes you have more than 1 or more than 2 edges to a node. Pretend this just continues and this just continues. So does this. And the reason why this is not a problem that needs to be handled with a special case, I mean, you can if you want, but you don't need to, is the same reason that if you take a running maximum on an array of integers, eventually one of the pair of integers you compare will be the biggest integer and second biggest integer. And when we want to find a potential biggest cycle here, obviously if multiple edges share the same endpoints, the particular endpoints that have the first biggest and second biggest edge weights are going to be what we want to consider. And the first biggest, you'll just find it somewhere, and the second biggest will either come before the first biggest or after the first biggest and won't be canceled out by anything. So you will meet them eventually. Also, if you have like internal paths in this graph, or that just look like this. This is also not a very big problem because these will just get contracted into like a single internal edge. So neither of these two cases are stuff that needs to be handled especially. So eventually we'll end up with one cycle remaining in this graph. How am I doing on time if I need to worry about that?
Probably want to wrap up soon.
Okay. Either the cycle will not, or either our best cycle will not loop through the last cycle in the graph. It'll be somewhere out here, or maybe it will share an edge, but it will remain out here. In which case, we've already recorded the best cycle, or the best cycle could just go somewhere around this last remaining cycle. We won't need to give this any special handling unless the end case of our graph is a particular way. So there are two end conditions for this. Either you end up with two nodes and a single edge. You already recorded the best cycle in that case. Or you'll end up with one node and a single edge connecting the node to itself. In which case you'll have to check the edge weight of the last edge along with the stuff that you already checked. The highest cycle length you encountered is the answer. It's like a tree DP, except it's on a biconnected, regionally connected graph. Oh, and finding the what nodes you can contract in which you can merge, you can get in order one after doing a contraction or a merge what other components of this graph are eligible for a contraction or a merge. So you can use like a queue to keep track of contractions and a queue to keep track of merges, and maybe a map to keep track of which edge which edges share each other. But yeah, once you set that up, this is an order E solution, or it can be an order E solution. So
very nice.
Thanks. Hopefully that wasn't too long.